Good morning, GNU Radio conference. So let's get this morning started. So before we introduce our keynote speaker today, there are a few announcements, as you can guess. First off, if you're looking for any information, once again, that's the URL where you should find everything. If it's not on there, the help desk is also open. And today, it's Thursday already. And tonight we will have our dinner social, so everyone socialize, please. A few more announcements for our speakers. It would be really, really great if you could upload your slides as soon as possible. I know you're all very, very good speakers and you already prepared your slides way before. You just forgot. So please, thanks. Besides, there are workshops today again. There's the Getting Started with GNU Radio in the Classroom workshop. It's in 301C, starts at 1 p.m. And the second workshop, Introduction to RF Processing for Satellite Constellations, that's in 301B. It starts at 3 p.m. So if you're interested, you know where to go. Besides, we have a women's social lunch that's around lunchtime in the Rotunda room. That should be over there in the corner. Feel free to join. I'm sure you're very much appreciated to join. Besides, there are still open slots for lightning talks. You know, you won't be struck by lightning, so please submit your ideas and make this an even nicer conference. Finally, there is the Capture the Flag going on. I just saw people are still very much involved. I'm having a hard time to read any of this from here. But yeah, it seems to be like people are very successful in gathering points, and I hope you're having fun. Always looks amazing. All right. In order to better socialize, there's also our chat server. So if you did not join yet, this is another reminder where to find it. And even if you're not at GRCon, it's a good idea to connect there all year round. There's always an active discussion. It's an open environment. People are friendly, so we hope to see you there too. I already mentioned the social dinner tonight. It will be at Maple Hall. We start at 6. There will be dinner, there will be drinks, and there will be bowling. Don't feel pressured, yeah, it's just a short walk from here, so it should be easy to get there. And yeah, see you there. Finally, I'd like to introduce today's keynote speaker, Philip Erickson. He is the director of MIT Haystack Observatory, and I already asked him. He is very happy to introduce himself and tell us more about what he's doing. So, welcome our keynote speaker. I hope this one works.
Number 2, right? I was told number two, right, Barry? Number 2, right? Great.
Okay.
Okay, that's working. Thanks for the introduction, Johannes, and thanks to Josh and the committee for inviting me to do this. This is a nice opportunity for me to expose some of the things that I we're doing at Haystack, but really in a lot of places around the world. It all has to do with using radio, either passive, so that's radio astronomy, for example, or active radars for looking at the ionosphere. And I really enjoyed Sharia's keynote yesterday. He was looking really small. He was talking about ASICs and small things. So I'm going to kind of reverse that. I'm going to start really big and then kind of gradually come closer to the planet and then go down to smaller things that I hope to end with a little bit of stuff that in fact has GNU Radio in it and that has opportunities for people who are interested in radio and information transfer to actually participate in. So we'll see how this goes. So I come from Haystack Observatory up in Westford, Massachusetts. This is a overhead helicopter shot of our little hill. We have 1,300 acres, which is a large amount of land in eastern Massachusetts that's still undeveloped. And as part of that, we've been there since the 1950s, doing essentially fundamental, either radar or radio, in this case, and in these days, both observations. You will see from the size of that photograph that we have some reasonably large antennas and large systems up there. When we were put together up there, this was where people from Boston went to have their summer homes, if you can imagine, given the density of population in Massachusetts. So it was built in a place where there weren't too many people around, so if you had loud transmitters, and I'll talk about loud in a minute, you didn't really bother them. Of course, now we have people living all around the observatory, but that was the reason it was established. In the upper right-hand corner, you're going to see a little diagram with kind of two arrows. Essentially, Haystack Observatory is operated by MIT campus, which of course is not out in Westford, Massachusetts. It's about, 50 kilometers away from the Cambridge campus where, all of MIT's activity, or most of it goes on. So we do fundamental research, we publish papers, we talk to folks here, we give conferences, and we operate the site. But on the site, there is also that right-hand arrow, which is MIT Lincoln Laboratory has a bunch of radar sensors there. And the way MIT works is that, sensitive classified projects are segmented off into Lincoln Laboratory, which is in Lexington, Massachusetts, about midway between Cambridge and Westford. And that is the site is part of the Lincoln Space Surveillance Complex, which does things like keep track of objects in the catalog, in near-Earth space, and geosync, and a little beyond. So we do a bunch of different things there. And of course, just to be confusing, there's a lot of different names there that for the different pieces of what is really Haystack Observatory. As I mentioned, we actually do a lot of different things that essentially are applying radio science or radar science to remotely sensing the universe, to Earth, and you can see some of them on the left-hand side. Really, the left-hand side is the science research we do, and the right-hand side is the fact that we also concentrate on a lot of technology, which is, of course, is married with the science application. I'm going to talk today essentially about radio astronomy to start with, and then some atmospheric science, essentially ionospheric measurements, but I could give another talk on geodesy, which is how you figure out how the Earth is oriented and what the clocks are on Earth relative to the celestial sphere. Space science, we're doing some flight projects these days. Polar science, I have a colleague who's doing cryosphere work and looking at ice breakup in the Antarctic and that sort of thing. It's obviously all underpinned by data science and informatics, which is, of course, the lingua franca these days. And on the right-hand side, you can see the technological places that we concentrate on. Radio arrays, very long baseline interferometry, something called incoherent scatter radar, which I'll talk about in a little bit, and then, of course, as I mentioned, space science. Obviously, we're all here at GNU Radio because we enjoy using the electromagnetic spectrum at radio frequencies, and this is just a reminder of the fact that, science is using that whole stretch of electromagnetic spectrum, but of course, it isn't just science, and as everybody knows in this room who's been playing with communications, for over 100 years now, this spectrum has been heavily used for human purposes, for communications. These days, precision navigation, timing, distribution. And so we're actually fitting our science in amongst all of these. As you go up higher in frequency and you get to, centimeter wave and millimeter wave, used to be that that was fairly empty except for science use. Of course, now with the advent of devices that work at those frequencies, there's a bit of a coexistence issue developing, and that's one of the reasons why science actually has to work very closely with the technical community to sort of cooperatively share the extremely precious electromagnetic spectrum. And this is just one reason why we might want to pay attention to that. It turns out that if you look at, for example, a galaxy pretty far away, that's the Whirlpool galaxy in the middle. If you look at it in the middle in optical, well, there's a lot of dust. And so you can actually see the spiral arms of the Whirlpool galaxy, but it's a little hard to see what's actually at the center. As you go to longer wavelengths and you get into microwave, for example, and in the infrared and into radio, the spiral arms of the galaxy begin to represent themselves, and you can start to see where matter is coming out. And if you combine that with even shorter wavelengths than optical, like ultraviolet or X-ray, the point is that the combination of all of these different wavelengths or frequencies in the EM spectrum is the way that you can synthesize the life cycle and the physics of the object. So it's important, I'm going to concentrate on radio, but it is important to look at all of these different wavelengths and talk across communities to figure out fundamental information about how these systems are created, how they evolve, and how they die. There are, as I mentioned, there's natural sources of radio emission everywhere. If we think about radio astronomy, Jupiter is the loudest thing in the solar system at decametric wavelengths. And the sun, of course, is a very bright radio emitter. You go out to the Milky Way, you've got star-forming regions, old stars, things blew up, supernovas and remnants. You really can see now an enormously varied bunch of stars, white dwarfs, distant suns, infant stars. All of these are generating, for example, radio at some point or another. You go beyond our galaxy and you're getting into quasars and radio jets, which, as we'll see in a moment, are a very, very powerful remote sensing tool. And if you like to do astrochemistry and figure out, okay, in the cloud where a star system is beginning to evolve, what's there? And it turns out by looking at the background, cosmic microwave background radiation, and looking at notches in that, you're kind of doing a form of a spectroscopy. And you can actually use those particular notches in your knowledge of chemistry to figure out that, for example, methanol is over there, or ammonia. And in fact, there may be a methanol maser at some point where you actually have a resonator that's producing a particularly bright line with an absorption signature that must be methanol. So you can actually do astrochemistry and explore the universe without having to inconveniently get into a ship that doesn't exist yet and travel, a million light years away. If you'd like to learn more about that, by the way, there's a very nice podcast by my colleague Lynn Matthews at Haystack. I will leave these slides. You can either grab the URL or hit the QR code there. One example, by the way, of all of this is how do you weigh a star without having a scale and a place to put it on? Well, one of the things you do is you look at neutral hydrogen, which happens to have a particular energy transition, which emits a photon at L band. And that gets redshifted to lower and lower frequencies. So you look at the rotation of those emissions in radio, and you can actually work out what the weight of the star would have to be. So quite cool, and a nice example of remote sensing. Here's a really interesting one. How many people have heard of black holes? Of course you all have. All right. It turns out that more than 2 decades ago, people at like UCLA at the Keck Galactic Center Group made this movie I'm going to show you in a moment. There are all of these stars which you'll see with labels. So and the date is in the upper right-hand corner. So we'll start running this. And these are people just measuring the orbits of stars. There's obviously something really, really heavy in the middle that's causing a star to get warped out of its orbit. So that has to be, according to physics predictions, there's probably a black hole there. In fact, we now posit that there are black holes at the center of nearly every forming galaxy. But all we know is an indirect measurement before about 2019. You saw you had to measure this over 20 years. You watched the star slowly evolve its orbit. So the idea was, could you go farther? Well, it turns out that you can. By the way, this is another image of a place called M87. This is Messier Object 87. And if you look at that galaxy, there's actually a jet of material that's streaming out from the center. So something has to have had enough dynamic features to actually take all that material and eject it in a stream. The idea, though, is there must, again, the theory was, well, I bet you there's a black hole there, and I bet you the black hole is squeezing matter so much that it's actually ejecting the matter into this jet. And that could be a fundamental part of how galaxies are forming and how star systems and planets and what have you are forming and how the material is distributed. This is from the Hubble, by the way, in optical. Now, it turns out that a black hole is a really cool object where if you get close enough to the black hole, even relativity breaks down. But if you get close enough, weird things start happening. So this is a nice little video. We're now kind of zooming in here on this particular, I think this is an M87. So here we are zooming in, and you can see that there's material in the interior that's really swirling around something that's, again, massive enough to make it orbit, kind of circling the drain, if you will. You can see that jet stuck there. And if it's so massive that even photons are getting warped out of their orbit. They're orbiting the black hole. They're getting tugged. So from our point of view, if we receive these, for example, photons at millimeter wave or radio frequencies, we're going to see something that looks like a toroid. That's all of the light being bent out from back of the black hole and forming a ring. So, geez, there's something maybe we can detect, right? That's radio emission. It's actually, again, photons and other electromagnetic radiation being warped. So how to do that? The problem is it's really tiny. Really, really tiny. So we can go through angular size, right? There's a protractor. We can take a degree, which is 60 arc minutes, which is 60 arc seconds, and we go to 40 to 50 micro arc seconds of angle. That's, again, like our little apple or orange on the moon as viewed from here. So that's a very, very small object, and you really want me to get some kind of detail about what's happening around that object. By the way, this is one of the closest black holes, the one at the center of our galaxy, Sagittarius star. There's a black hole at the center of our own galaxy, because we're like a lot of other galaxies. So, just to give you a kind of a feeling for what that's like to measure, this image was taken by my colleague Colin Lonsdale. It starts out on a hill. It's about 40 kilometers or 25 miles away from the observatory, and we'll zoom in to show you the scale of what we're trying to measure with this particular something called the Event Horizon Telescope, which we'll tell you about in a minute. So here we are on Pac-Monadnock. There's the Boston skyline. You will notice this particular egg coming up. That's the Haystack Radome with a 37-meter telescope in it. And then eventually, there's my colleague Jason Suhu. Okay, Jason is looking rather nice. It's a nice day. Jason has an eyebrow. Let's go find Jason's hair and his eyebrow. Let's keep on going. Okay, there's what we're trying to measure. Now I'll back out. That's the angular size that this telescope is trying to resolve. Quite challenging, but as, in fact, Sharia said of other things yesterday, even though it's astonishing and we're orders and orders of magnitude, people persisted and said, well, can we do that? So this is the Event Horizon Telescope, which is not one telescope. It's actually a collection of telescopes borrowed for the purpose once in a while. They're not dedicated. All over the planet, and the idea is to form a large telescope array with really good maser quality clocks that lose a second every 10 to the 15 seconds, or a second every couple million years. They're very stable. You have very stable clocks, and you measure at millimeter waves, and you measure a very, very long distance between one telescope and another, like the diameter of the planet. And if you work out, that's gigawavelengths. So this is a gigawavelength interferometer arm translates to a thing that is of the angular size that I just showed you. In fact, this is the highest resolution you're going to get because, again, you have millimeters, and you're able to measure not only amplitude, but also phase. Phase is key to an interferometer, and you're doing it on thousands of kilometers of diameter. So you connect all these things together, and you can form a telescope that can observe the emission from that tiny, tiny thing and even try to derive some structure around it. This is what it takes. 300 members, more than 300, more than 59 institutes, more than 18 countries, North, South America, Europe, Asia, Africa. You can't do this alone. It needs a global community by definition because you're using the entire planet. So if you do that, the EHT as a collective, and Haystack is one part of it, okay, has imaged 2 black holes to date multiple times. The first one is in M87, which is in the Messier object. Now you might think, wait a minute, that's actually 55 million light years away and you're starting with that one? Well, it turns out it's much, much heavier than the one that's closest to us at 6.3 billion solar masses. So think about 6.3 billion times the size of a sun in a very small package. But it doesn't change. It's relatively stable. So as the planet rotates and a telescope comes into view and comes out of view, you can actually image that where it's the picture of the thing you're trying to take on that particular time scale is relatively stable. So they started with that because that black hole is heavy. They moved on to the more challenging one, which is in the center of our galaxy, Sagittarius A star. That's only 4 million solar masses, so we're now a factor of 1,000 lighter. It's only 25,000 light years away, okay? But the emission is variable. The matter around it is actually changing. So there was another set of imaging techniques that had to be developed to deal with that. And down on the bottom right-hand corner, you can see these 2 kind of famous orange donut measurements that were made. These are our best guess at what the image looks like, consistent with the relatively limited number of points we have from this particular interferometer. The key step, and going back to radio processing, is correlation. You're taking 2 telescopes separated by the diameter of the planet with really, really good clocks. You're sampling them at very high rates. I'll tell you about that in a minute. And then you're bringing them together, and the correlation process basically is the thing that not only forms the image, but tosses away all the other signals that were at one telescope or another, but were not the common signal that the telescopes were looking at. And that process is the way that you actually form the image. You could keep going with this. For example, in the left-hand corner there, you first visit, for example, M87 in April 2017, and then you visit it again 1 year later in 2018, and you see that there is some rotation, but in reality, the emission's remarkably stable. So this checked one box about how black holes behave. There's a nice little factoid there that M87 eats 1 mass the size of the sun every 1,000 years. That's actually a relatively stable black hole. Many of them are very messy eaters and eat more than that and dynamically change and grow. Not only if you want to find the emission, but you also want to find out what the magnetic field is like around this really, really intense object. You can get computer people to make simulations, which is the upper right-hand corner of M87, in polarized radio. And you can find out that the magnetic fields should be all twisted up. That's a model. This is reality. So in March of this past year, the image was happening with polarization, which is kind of like climbing to the top of the mountain. If you can keep your telescope's polarization calibrated, absolutely, because this signal, again, is so faint, you do anything wrong to it, it's going to go away. Now you have an image that actually shows you these very intense wrapped magnetic fields. So you're beginning to figure out the features of one black hole. Well, we've imaged 2 so far. There are many, many black holes throughout the universe. There's a zoo of them. Some of them spin, some of them don't. What's the spin? Do they wobble on their axis? What's the mass ratio? How does that relate to the size of the developing galaxy? There's all sorts of things you can find out by taking this really distant object and receiving these really faint radio photons. So we have fun doing that. And in reality, I mean, it's really leading to metric tests of general relativity that are just not accessible to weak field tests like anything we can create here on Earth. Creating 6.5 billion solar masses in your typical laboratory is hard. But here you can actually do that. And so this is really the dawn of a new era of black hole astrophysics. And just to leave you again a scale, that's the M87 image. And you can see there, for example, there's our solar system kind of stuck in the middle where the black hole would be. Remember, that's not the black hole, that's the material circling the drain and getting really hot and emitting all sorts of radio photons. So the scales kind of boggle your mind, but they're there. Now let's talk a little bit about hardware. We have to have very fast recorders. Here, you're looking at a Gaussian random object, so you're actually not looking for a lot of dynamic range. This sampling is really typically done at maybe 1 or 2 bits. But you want to run it as fast as you possibly can, because more bandwidth equals, the bandwidth that you run it is inversely proportional to the fidelity of the image. So higher bandwidth is more capable images. These are some of our recorders, specialized things. You can see the recording rate for the EHT, rather than a 2 to 4 gigabit per second kind of recording rate, which is typical for a typical VLBI experiment, very long baseline interferometry. The EHT is at 32 gigabits, 64 for 28, and the idea is to go to 192 or 256 gigabits consistently. So you can think about a couple of bits times, you know, that much bandwidth on a continuous, a coordinated set of large telescopes. There's about 12 orders of magnitude in the data reduction. You start out with petabytes of raw IQ at a given center frequency at millimeter wave. You correlate it, now you're down to terabytes. You calibrate that, you throw away more information, now you're down to megabytes, and the image itself, it finally is, you know, it would fit on your computer 20 years ago. It's about, you know, 30 kilobytes or something like that. There's my colleague standing next to some of the data arrays. You know, we still ship around sleds of hard drives. It turns out that it's still not fast enough to get it back on networks. We have to, you know, a box of drives on a 747 is the fastest way to get data here per wall clock time. So we still ship stuff around everywhere you can think of, including from the South Pole, which is fun because it takes, you know, 3 or 4 months for the ship to get here with the data, so people get a little nervous. But in any case, you can see the amount of data reduction. It's kind of staggering. I can't give a talk about this. There's a whole, like, literally conferences on this. How do you do this thing? Well, you have this image that you want to measure. You're really taking Fourier domain samples of it, very poorly sampled because you don't have a planet dotted with telescopes. You're forming all of these baselines, which translate into a 2-dimensional Fourier transform of the image on the sky. And then that should have been an animation, but you let the planet rotate, and you let telescopes come into view and then set, and you combine all that data together. So there's a whole special issue on how this is done, and that's still a very, very evolving picture. So this is kind of what's underneath making that image. Okay, we were really, really far away and really, really massive. I'm going to come back to the planet now, so we're kind of at medium scale. My background is actually as a geospace research person. So we do have a neutral atmosphere on the planet. You're breathing it from the ground, and it falls off, you know, through the stratosphere at 7 degrees Kelvin per kilometer, and the atmosphere is getting thinner. And then you get up into the stratosphere where you've got wave activity, and so the temperature goes up some. You then get into the mesosphere, and you get to about 85 or 90 kilometers up, which is the coldest place in our atmosphere. It's actually 140 Kelvin up there. And this room is 270-something Kelvin, so you can think about that. And then it gets hot again as the atmosphere gets thinner for wave activity. The sun illuminates all of that with extreme ultraviolet photons. They're so energetic that they start ripping off electrons from the neutrals, and they make ions. And the reason that we have had transcontinental communications way back to the 1920s is the ionosphere that surrounds our planet. At this planet, we have a weakly ionized atmosphere. There's about 100 times less ions than there are neutrals, but it's a plasma. You have ions and electrons, and they don't just go right back together and form neutrals again. They are separated by electric and magnetic forces. And so between day and night, you get different layers of the electron density as you go up in altitude, and you get different ion compositions. The atmosphere is gradually getting lighter as you go up. And there's all sorts of dynamics in there, and it turns out that that is something that we study at the observatory and in a whole community of people around the world that deal with this from a fundamental physics point of view. But it's not only fundamental physics, there are a lot of applications. As we all know, we're inexorably going to a spacefaring society, and one of the consequences of that is to have to understand the environment that you're in and how it's affecting systems. That environment has weather, it has storms, okay, beyond the climate, much like the weather here on the ground. There are 2 kinds of categories. There's external forcing, The sun emits a coronal mass ejection with accompanying very intense magnetic fields, and we get a geomagnetic storm. The Earth's magnetic field gets disrupted. You might get a burst of X-ray output. That's a solar flare, which ionizes temporarily the D region in the ionosphere and causes an HF blackout for maybe about an hour. There's also internal forces. It turns out that we've realized over the last decade or two that the neutral atmosphere, and literally the meteorology, is actually coupled to weather in the upper atmosphere at well beyond where the astronauts are flying around in the space station. You have to kind of understand the whole system as a coupled unit. So feedback, regulation, all the things that honestly biologists study, we're having to study in this particular environment. And then there's the applications like, okay, did we disrupt GNSS for a little while? Did we manage to tell aircraft people not to fly a transpolar route for the next little while because of enhanced radiation exposure? That sort of thing. So space weather is a societal thing as well as a fundamental physics thing. So in New England, we're conducting this, just in case you need an orientation where we are. That's the map of New England. The little red pointer there is Haystack, and if you went to Google Earth and you looked us up, you'd see an overhead shot of what I showed you at the beginning. We study all of the variations of the upper atmosphere, specifically mostly the ionized part, the neutral part as well, at mid-latitudes. Why mid-latitudes? Well, a lot of people live at mid-latitudes, including this country. It is actually less studied historically. Most of the study, until 3 or so decades ago, was concentrated either on the equator, where there are a lot of embedded irregularities at wavelengths that tend to interrupt communications, or high latitudes where things like the aurora happen and where particle input is coming in more directly from the overlying magnetosphere. This is work that we get sponsored by writing grants to NASA, National Science Foundation, Air Force Office of Scientific Research, Office of Naval Research, other kinds of things. So we're kind of out there slugging it out with the rest of the community to make a compelling case to provide funding. There's a reason to understand it. I pulled that yesterday. That's a website called satellitemap.space. That's actually a nice website. It's interactive. You can drag this thing around, and you could actually put your location in and see what the density is. That's the Starlink constellation as of yesterday. That's 550 kilometers altitude for almost all of it. There are 4,746 active satellites, and there's 6,949. And we could have a whole talk about the commercial use of low Earth orbit. What I will leave you with is that Starlink is licensed for 12,000 birds. They are applying for 45,000, and they are one of about 10 companies that would like to do constellations of this density or larger. So low Earth orbit is getting really crowded, and it's imperative on us as a society to understand what the environment that they're flying in is and how the dynamics of that environment might affect the constellation and vice versa. So what do we do from the ground? Well, at Haystack, we do a rather specialized form of remote sensing using a fairly large antenna. Set of antennas. You can see on the left-hand side there, if you really got really good eyes, you can see the pickup truck parked at the bottom of the steerable antenna foundation. We have a radar at UHF frequencies. It's about 440 megahertz, 68 centimeters wavelength. And we use two antennas. One of them is a 68-meter antenna, 220 feet. So what's a soccer field? About 100 meters. So think about an antenna about 2/3 the size of a soccer field. And then the other one is a little smaller, 150 feet or 46 meters, but it's fully steerable. We can point that from the Canadian Maritimes to Iowa down to little between Florida and Puerto Rico and out into the middle of the Atlantic. So we have a very large field of view. So those are antennas. They're very efficient collectors of radio waves. But we have to make the radio waves because the ionosphere, in this case, that we're trying to sense doesn't really emit it, kind of unlike the radio astronomy I talked about a little earlier. So how do we do that? We use these. These are my transmitters. Those are high-power microwave amplifiers. Those are four-cavity klystrons. Klystrons are developed in the 1930s by a couple of different clever teams. Those put out in tandem to 2 megawatts peak. So we have a 2 megawatt flash bulb at UHF, and it's got a duty cycle of about 6%, so we keep it down to 150 kilowatts average to make sure the tube survives. Those are surplus from the Air Force's ballistic missile early warning system, for which the design parameters were almost the same as to detect the ionosphere. Physics worked out. That's our on-off switch, because you have to take up to 120 kilovolts at 4 amps and apply it to the bottom of the tube or remove it. So you need all sorts of high voltage bus work in an oil tank, 5,000 gallons of dielectric oil, because you don't want to create lightning bolts in the room. And you do all of that to make a very, very bright signal that you feed into one of those antennas. By the way, there's our waveguide. The UHF waveguide is the bigger one. It's kind of like HVAC duct. There happen to be some other ones at S-band and L-band, and one of them at KU-band, I think, in there. And then there's a little tiny one at W-band for comparison, but we use the bigger one. You can do this, by the way, not just with a mechanical antenna, but you can do it with a phased array. Sharia yesterday showed a lithography printed array with 256 elements. This is a UHF array with 4,096 elements at 2 megawatts peak, 500 watts per element, 4,096 element. You can see the people. If you find me in the picture, come find me later and I'll give you a prize or something. But you can see the scale that we're talking about. And the picture is a movie. The beam is scanning right now. I'm kidding. Because you can't see the beam and it's electronically steered. So rather than mechanically having to move the beam around, you can basically do the electrical equivalent of focusing the beam in different directions, much like the phased array that you saw yesterday. So we can use this. In this case, this is up near the border between the subarauroral ionosphere and the auroral zone to do more physics, but it's the same kind of technique that we actually do at Haystack. This is what we're looking for, a really narrow, it's only, in this case, one of the emissions we're looking at is only 10 to 15 kilohertz wide at UHF frequencies, but it's really, really weak. I take a megawatt class pulse and I pump it into an antenna with 42 to 45 dBi gain, so I'm at a few tens of gigawatts ERP, and I get back 10 femtowatts. Why? Because even with a box of electrons, each electron is a tiny, tiny object from a radar scattering point of view. But believe it or not, beginning in the late 1950s, receivers got sensitive that you could detect this. And there's an enormous amount of fundamental physics that you can use to remotely sense the electron temperature, the ion temperature, the velocity, the ion composition, and the electron density by measuring that little double-humped kind of shaped spectrum around the center frequency that you transmitted with your bright flash. So we can do this as an operational technique to actually do space weather or ionospheric measurements. Here's an example of what the spectra looks like. On the left-hand side, you see its frequency plus or minus 50 kilohertz, and then that's range away from the antenna, which in this case, because it's our vertical beam, is equivalent to altitude, and the space shuttle is flying about in the middle of there. You'll notice that the spectral shape does change as a function of altitude. That's because the temperature is changing. The electron density is changing. The composition is changing. You can take all of that, run it into a first principles plasma physics theory, which some extremely clever people with pencils figured out originally, and you get that. That's a map of the electron density above the ionosphere, above the Millstone Hill in eastern Massachusetts, over 24 hours. About sunrise is happening about in the middle. And the top part is the F region from about 150 kilometers to about 600 kilometers. Remember, the space station's flying in about the middle of that. And the bottom is about is a zoom in at about 100 kilometers altitude for a reason I'll talk about a little bit later. So this is fundamental things that I can hand to somebody who is just doing ionospheric physics or ionosphere magnetosphere coupling, and they can take this and then do fundamental physics with it. We do that too, but we also do the remote sensing. So this is really powerful use, again, of radio waves. In this case, okay, we got to make the radio waves that we want to sense their changes when they come back, but it's a really nice way of remote sensing. How do we do this? Well, this is a paper that we published back in 2005, but it was actually something that we began in the late 90s. This is the software patterns that one uses to make not a hardware radar, but a software radar. And so we had an early idea that if we multicast, for example, some of these samples coming off the receiver onto a bus, we could then run various software patterns, reduce the data to some intermediate level, put it back out on the network on a different multicast channel, and then go that way. And so we've actually been using the multicast standard for quite a while. Now, because this was written in the late 1990s and early 2000s, a lot of this was originally written in C. I don't want to tell you how many times I sat there figuring out why a pointer had gone astray. I don't want to ever do that again. But remember, though, that we could do this on workstations because of the narrow bandwidths compared to some of the other bandwidths that we're talking about, for example, for the Event Horizon telescope, which are at a whole nother scale. So very early on, we wanted to think about software patterns, which is exactly what GNU Radio is about. Software patterns, reuse, how can you then trade that with other people and have them do different things with it? So we've been thinking that way for a long time, actually. So I want to end today by basically then going even smaller. So I just showed you this big thing, you know, the electricity bill is about $100,000 a year, you know, the facility takes about $2.5 million per year to run. You're not going to go out and buy that at Target. What if we can do even smaller sensors that still receive fundamental ionospheric information, for example, and do it in a different way than the professional systems? So what I'm going to talk about is the work of my colleagues Ryan Bowles and John Swoboda, both at MIT Haystack. They presented a little bit of this at, for example, the New England SDR conference. So if anybody was there, you might recognize a little bit of this. But the idea is a much smaller system can do really kind of a serendipitous measurement. This is a picture, for example, from a McMurdo station down in the South Pole. If you want to measure the neutral wind in the upper atmosphere, not the ionized part. The ionized part will respond if you send a radar pulse because it's an electromagnetic wave, charges, they accelerate, you get a little wave back. The neutrals don't do that. So how are you going to measure what the neutral, for example, wind patterns are doing? Well, happily, nature provides meteoric dust as we orbit in the lane around the sun. And so every day we get many, many little tiny grains of micrometeoroids burning up. They leave a little ionized trail behind. That trail is a tracer, and it drifts with the wind. So if you can actually get a specular echo off that trail and watch it drift, you can derive what the neutral winds are going in a way that's very, very difficult to do almost any other way. You can try to do this with smaller and smaller systems, and that's one of the things that Ryan at Haystack has been pushing. Why is this important? Well, there's another diagram of just the temperature structure in the neutral atmosphere as it goes up. And you notice two arrows there. That's about the region that these meteoroids burn up, between 120 kilometers and about 80 kilometers. Those trails last for anywhere from a second to tens of seconds, and then they kind of diffuse away, and then another one comes along. This is critically important to understand the electrodynamics of the way this atmosphere goes. Because as we go from way up in altitude, lower in altitude, when we reach 100 kilometers, we reach this magic layer. It's really only about 10 kilometers thick. At that layer, the electrons are still stuck to our magnetic field. We have a strong background magnetic field in this planet, and so the electrons are stuck, but the ions are beginning to collide with the neutrals, enough that they actually get dragged off the magnetic field line. Minus, plus electric field. So above that, both the electrons and ions are magnetized, and they kind of move together. Below that level, both the electrons and the ions are collisional, and now we're back to just collisional fluid mechanics. But in that nice little narrow region, you can get all sorts of currents flowing. So sensing what the neutrals are doing is just as important in that layer as sensing what the ions are doing. But it's unfortunately, try to put a satellite at 100 kilometers and see how long it lasts. Not very long. The energetics are terrible. You can shoot a rocket through it. You get one pass up and one pass down. You can't sit there and monitor it. So meteor trails represent a really attractive way, and this has been known for decades, but now the technology has been evolving such that you can do this multi-statically. And anybody that has looked at MIMO networks, you know, the routers in this room, these are very familiar patterns. You send a phase-coded technique where you make sure that the pseudorandom codes are all orthogonal to one another, so I can send multiple transmissions at the same time and not confuse that transmitter with that transmitter. And you can basically do the cross-correlation between all of the combinatoric pathways, and you can do interferometry. So you can localize that meteor trail, and you can watch it move. And you can then derive the velocity, which is what you're looking for. There are various configurations. You know, you can... If you have very good eyes, you'll see there's SIMO, which is single in, multiple out. One transmitter, put a bunch of receivers out, they're all listening to that single transmitter. There's MISO, like miso soup. You put multiple transmitters in one place, then you have a single receiver, but it can see every individual path from every different PRN code. Eventually, you get to MIMO. You have multiple transmitters, You have multiple receivers, each one that can receive all of the different transmitters, and the combinatorics start piling up, and you can get much more dense information of what's going on. So you can trade off how to implement these things. You know, it's much harder to give someone a transmitter in their backyard than it is to give them a receiver. So sometimes you want to concentrate your transmitters in one place where you control it, and then you can put your receivers out. For example, I've got one in my backyard, as I'll show you here, and I have a dog, and I don't worry about the dog kind of like touching the wire when something is being transmitted. So this is a very flexible and adaptable technique, and it gets to pull in all the MIMO techniques that people, for example, in this room and in other fields and at GNU Radio have seen. So there's a network called Zephyr that Brian is developing, and the idea is, again, do the combinatorics. And the great thing is that you also don't have aliasing, like did that thing come from this altitude or twice that distance. With doing all the combinatorics, you can resolve those sort of ambiguities. And you can end up getting a three-dimensional wind field. So not only is it a function of latitude and longitude, but also of altitude, which is really important for the physics. This has been done a couple of places. There's been a prototype out in Colorado with our colleagues at CU Boulder. The idea is one transmitter site with about a 5-antenna array, and then there's also some other ancillary receiver sites. The thing is working well, and we're also standing one up in New England around that larger radar to be able to, again, put more than one piece of data on the same table and do physics that's consistent with all of it. These are the scientific outputs. I won't go into it except for to say on the right-hand side are meteor counts as a function of time. And you can see that they come and go because the sporadic micrometeors coming in have some patterns, if you think about it. For example, in a day, when we're at 6 a.m., the planet is rotating into the stream of micrometeoroids in our orbit, so that the numbers peak. At 6 p.m., we get a low number because we're wearing away from them, if you think about the way now the planet is rotating opposite to where we're at a place that's going opposite to where the orbit velocity is. This, again, derives stuff that's almost unavailable with any other technique. The derived winds, for example, measurement are given on the left-hand side. That's a square about 5 degrees by 5 degrees in latitude or longitude, or about 550 kilometers by 550 kilometers. You see all that structure? By the way, the left-hand one is one altitude and the right-hand one is another altitude. So first of all, the altitudes are not behaving the same because of some of this coupled dynamics. And the other thing I will tell you is that one of the best meteor wind field has one vector in that entire thing. I would tell you that maybe there's a lot more structure than just one wind vector across that 5 degree by 5 degree box. So this is really fundamental information that you really can't get at almost any other way. So we're trying to apply some of the technology in this community, for example, and others to try to do this more efficiently with small systems. And finally, I'll talk about something that my colleague Jon is doing, which is an active technique. If anybody's heard of an ionoson, this is the way to do active sounding of the ionosphere at HF frequencies. This is literally the oldest radar technique there is. Gregory Bright and Merlo on the left-hand side there basically invented this in 1928. There's a nice paper that shows that. You essentially send a wave from the ground up at HF frequencies, so between 2 and 15 megahertz approximately. When that wave gets to the point where it's equal to something called the plasma frequency, which is a fundamental resonance that's related to the square root of the electron density, the wave basically completely interacts with the background. The index of refraction goes to 0 and the wave turns around and comes back. So it's actually a complete reflection. So that's one of the reasons why it's been done since the 1920s, because it's reasonably easy to detect. You sweep the frequency, and now you're measuring at different altitudes on the bottom side of the profile, and you get funny things like the upper right-hand corner there, which you have to interpret a little bit, because as the wave is slowing down, time is not necessarily range, but you can work out then what the electron density profile is. These systems, again, were fairly large and complicated. You can see the antenna down in the lower right-hand corner there for a very simple CW swept tone. So what if you apply things like phase coding? Can you shrink the size of the system? Can you turn down the power? Well, that's something called emphasis. And the idea is not only can you turn the power down, you can use coding to help your power budget, but if you make something called a vector sensor is 3 electric field components, all orthogonal, and 3 magnetic field components, loops. Any electromagnetic wave, if you've measured all 3 E's and all 3 B's, you have all the information about where that wave is coming from. If you cross-correlate E with B, anybody who's done, gone through your electromagnetics course will know that that's something called the Poynting vector, and in that direction, the correlation maximizes. So on the upper right-hand corner, you can actually localize the return, rather than just grabbing any return and not knowing if it came from there, or there, or there. And so that extra dimension allows you to do the 3-dimensional structure of the ionosphere at the reflection points, which is something that is harder to do. So you then do that in more than one station, and you can distribute these measurements. So you can start making velocity vectors with a much smaller system, with some limitations, obviously, than the larger one I showed you a little bit earlier. So this is something that we're pushing. By the way, the transmit loops down there on the bottom right-hand corner are electrically small loops, about 1/10 of a wavelength, and we're using those as our transmitters. But again, this is common distributed radio technology for all the EDIS fans in the room. Those are, in fact, the SN series software-defined radios. Up on the top there, those are X300s, for example, with some RF plumbing, mini-circuit amplifiers, and an octa-clock to distribute 10 megahertz locked precise time for the sampler. That's the receiver part. On the bottom is the transmit system. Again, one of these sort of loop transmitters, swept in frequency with the tuning operation, and then an N200. Anybody know how long the N200 has been around? A long time. I think it was first introduced in like 2003 or 2004. At HF frequencies, it's wonderful. So we use that as the pseudorandom code generator at the carrier frequency we'd like to use, and then we have a tunable antenna. So the right is the prototype. The left, by the way, are some examples of the antennas out in the field, and you can see that the bottom left one is at Ryan's house in near the coast of Massachusetts. I have one in my backyard, a little bit 15 minutes north of Worcester. And we just receive, all the combinatorics from the transmitters that illuminate the region around New England. But in the middle, though, is where we're going. We're using an, Xilinx RF SoC. You can see the board right there. And we're programming the FPGA using something called the Casper framework, which those of you in the radio astronomy community will recognize that's a sort of an idea to have an FPGA template for doing, for example, fast correlation. And we're basically taking we're synchronizing the samples using 100 gigabit per second backplane. And then the idea is to process that using, at the moment, using NVIDIA Jetson and the whole Holoscan framework. It's been referred to more than once at this conference. But the idea is you can put this out in the field and you can send it back with packets on the Verizon cell phone network, because you like to put that out somewhere. We're experimenting with adding other measurements with some more timing boards, but that's sort of in development. This has been funded. Ryan's funded through a Young Investigator program at the U.S. Naval Research Laboratory, so this is, again, a partnership. Like everything in our field, it's always a partnership. Software stacks, this is what we use. On the top for receiving, I mentioned NVIDIA Holoscan for sort of scale processing. On the left is the Casper logo. That's, again, the FPGA fabric. And on the right is digital RF is a container format which we have released open source that we've been using, which is basically a time-coherent way to read chunks of samples without worrying about which file they're in and doing all the mathematics and the bookkeeping about finding that as the user. You just want to get your samples and get on with it. RadioConda, I'll talk to you about in a minute. That's the receive side. For the transmit side, the stack has GNU Radio in it for doing the pattern generation, and as we mentioned, EDIS radios. And then for telemetry and other kind of metadata, we're using Telegraph, we're using MQTT messages, and we're using an InfluxDB to grab all it. Sometimes Grafana kind of wanders in here to do visualization. That's very nice. So if anybody is interested in playing with this, I will recommend Brian's work on something called RadioConda. This is a very nice packaged installer for GNU Radio and all those other packages that you see on the right-hand side. It works on Linux, it works on Mac, it works on Windows. The idea is, batteries included. You'd like to be able to not recompile GNU Radio all the time. So at least as long as Ryan keeps up with this, which he's certainly trying to do, this will just work out of the box and get you to playing. It's in the Conda framework. You are probably familiar with Conda, one of the many ways to do it out there. Conda Forge is a very nice environment. This is not just for Python. We primarily use it for Python, but it's not just for Python. And by the way, it's Not as slow as you might remember. I know some people in this community tried to work with conduct before, and it was a little slow. It's gotten much better. So the idea with this particular distribution is build GNU Radio so you don't have to. And we are open to contributions. So anybody out there that has an OOT module, write to Ryan, and we might be able to include it if you think it would fit in the radio ecosystem. So I really encourage you to look this up. It's really nice. It just gets you to playing pretty fast. And so the last thing I will mention, and again, small, is what if we could do radio telescopes with that 8-foot C-band dish? Anybody remembers, if you're back a certain long? This used to be the way that people did satellite TV, right, before we got the 18-inch direct TV dishes. If you take that and you build your own feed, which we have instructions for, you can actually end up turning that into a decent radio telescope for doing things like galactic rotation. You can watch the neutral hydrogen in the galaxy rotate. You can see the one Doppler shift going away and the one going toward if you you look long enough. You can measure pulsars, for example. You can watch them blip. You can even do interferometry if you have 2 of them. And it's all a GNU radio flow graph, and behind it, which you can see in the lower right-hand corner, and on the lower left-hand corner is a nice little Python dashboard where, for example, the operator, you can point to a particular source, which is preloaded, and the antenna will go there with a nice little alpha SPID controller and do the work. So we use this for educational purposes, demonstrations, but it's a perfectly nice platform. There's about 500 of these telescopes kind of scattered around, all in various stages of upgrading to this front end. So you go to the QR code or the website, you can watch that space. And finally, I want to give a forward reference to my colleague, Christina Collins over there, who's going to be giving the keynote tomorrow. We're also participating in a very exciting citizen science project that has developed over the last few years, something called HamSci. You can see the goals of HamSci right there. And I know Christina is going to talk about a lot more of the applications that the community has been able to do. This has really gotten a lot of eyeballs at places like NSF and NASA because it's a really engaging way to get citizen scientists to work with professionals. And what community am I talking to? I'm talking to a community that are implementers. You guys are tinkerers. Marrying you with the people who really understand how to do the science and understand how that measurement, like the ones I showed you in the last part of this talk, might be a little different than the larger professional systems, and working side by side with it is really, really powerful. And it is pretty amazing what you can do with a really simple measurement. And again, I encourage you to come tomorrow to hear more about that. But the idea is, we're working together in a larger community. It would be silly just to try to do things over here and try to do things over here and not collaborate. Winding all the way back to the beginning of my talk, the Event Horizon Telescope image would never have shown up if we didn't cooperate on a global basis. This is yet another form of it. So there's a very nice growing community, and I encourage you to get involved in that after you all take your amateur radio license exam, for those of you who haven't, whenever that is. I think that's later. Maybe. So that's where I'll conclude. The whole reason why we're still doing this work, the thought I will leave you with, is that our planet and the universe beyond are quite dynamic. We've been hacking at some of this for more than a century. We're basically at the bare start of discovering the behaviors and understanding what they mean for our society. This is really essential for us to move off the planet into lunar orbit, beyond into the solar system, or even into low Earth orbit, as is already happening as you and I speak today. So thanks very much for the opportunity to talk to you, and I'll be around.
Thank you very much. I think we have time for like a very few questions. Are there any questions in the room? Don't be shy.
Oh, back there. Oh, there's Greg. Hi, Greg.
Ah, here we go.
Great talk. Thank you very much. I'm just wondering if you collaborate with the International Space Station, seeing as it seems to be in the middle of that range.
It does. The ISS we tend to, as a community, we tend to collaborate with the ISS in a couple of different ways. It's a very nice platform to launch CubeSats. You can actually take a little CubeSat in a suitcase, hand it to one of the astronauts, it gets up there, and eventually they go out in an EVA and they launch it. They go like that. and it just kind of flies away. If you like something about in that lane, or in most cases, I hate to say, they try to throw it upwards so that it doesn't really necessarily always stay in the lane. The other way you can do that is the space station is flying around and it's actually going through the electron density at 350 or 400 kilometers. And so if you stick something called the Langmuir probe out beyond the sheath of charges that this station is gathering because it's a charged body, you sweep that. You basically do kind of a curve trace. You sweep voltage, you measure the current coming back. You can fundamentally relate that to the electron density and the electron temperature. That goes all the way back to a guy named Irving Langmuir from the 1920s who pioneered this for General Electric's research laboratory, trying to figure out how to make transmitting tubes more efficient. It's a fundamental property of matter. So we take that data also and use it. The other way that we're trying to collaborate with people that are having things in LEO like the International Space Station is, again, try to understand the environment that they're in and how it's changing and where some issues might arise if things keep on going the way they are.
Thank you. Hey, yeah, thanks, Philip. That was a great talk. Just wondering if you see the INO sound eventually being completely replaced with emphasis, or is it something that, yeah, where are we at?
Right. So what we see, so, ionosondes, as I mentioned, as Greg referred to, have been around for more than a century, but they've been really simple devices. They've been transmit a CW signal, turn it off, wait for the pulse, move on, sweep, sweep, sweep. Using phase codes, okay, and then using directional antennas. I think eventually the community will gravitate toward that, so yes. But it is a bit of a paradigm change, and it's going to take a little while to do that. But we are still woefully undersampled when it comes to the upper atmosphere compared to where we'd like to be. So in some sense, I find it really exciting to have distributed networks of lower cost things that are measuring in a very different and more dense way alongside the traditional ones. So I think it's an and. I think that's where it's going.
Thank you very much. Let's thank the speaker again. We did prepare a little present for you. So here we go.
Thank you very much.
And also this one.
Oh.
Yeah.
Thanks.
And thank you very much. It was a joy to listen to your talk. Next up, we have Ralf Steinhagen. He's with GSI Fair, and he's doing a presentation on GNU Radio 4.0. Ralf, the stage is yours.
Wow, what a talk to follow. Okay, great. Yeah, what a talk to follow. I'm truly standing on the shoulders of giants, and I'm happy that I'm allowed to present here. Whatever is good, I'm just presenting here, but it's based on the people who are listed on below my name that actually contributed to this. And wait a moment, I need my pointer. Okay, thanks you for giving me the opportunity to talk on behalf of our organization and also some of the contributions that we're allowed to share and to contribute to the GNU Radio 4.0 code base. In this presentation, I want to highlight who we are, why we use and invest into GNU Radio, and then a slight motivator why to move towards the GNU Radio 4.0. Mostly showing some of the technical highlights. I have to apologize, I have to keep this very brief. And I can show you just a few highlights, and I have to skip over probably some of the items, but there will be like an answer in a Q&A session this afternoon where you can go a bit more into the details and you can ask me anything about what we did and why we do it and what the next steps would be. So GSI is located in Darmstadt, Germany, and has been a key player in heavy ion research since 1969. And it's part of Germany's major research infrastructure that is funded by the federal government and the state of Hesse through the Helmholtz Society, which is basically the German equivalent of the Department of Energy here in the US. And on the photo you can see on the lower left the existing facility, which is a national laboratory, which will now, or is now also hosting FAIR, the Facility for Antiproton and Ion Research. FAIR is an international extension funded by 11 member states, so we're not just national, but we have mostly European, but also India and Japanese contributions. And its main mission is to provide an accelerator-based fundamental research platform for nuclear, astro, and plasma physics, as well as applied biomedical and material science applications, serving around 3,000 visiting scientists from about 50 countries worldwide. So many wonder what we do. That's our slogan. We explore the universe in the lab, or maybe. And what is meant by this is like we can recreate rare cosmic processes that naturally occur across our universe, like those observed using, for example, radio telescope that you heard earlier about. And our focus is that our accelerators can basically act like giant microscopes and allow us to directly study these processes that occur on a galactic scales using RF signal-based processing and other detectors, but however at a much higher event rates and precision than what you can do with sky-based systems alone. So using particle accelerators, we aim to unravel some of the most fundamental scientific questions. The mysteries of our universe, what are the smallest building blocks of matter, and how, where, and when were they created? And notably, while we and everything around us is made out of regular matter, the big question remains, what happened to antimatter? And we know it exists, so why does nature seem to favor regular matter than antimatter? And we're trying to recreate antimatter and see then the asymmetries between the behavior of all those two. So connecting again to space, we study processes that occur in space on a regular basis, and we also look at processes that created the elements that we see around us today. And by looking at events like supernovae, we explore also those elements, how these elements, heavy elements like, for example, gold or uranium, are formed in stellar explosions. Another key area that we're looking at is matter under extreme conditions, like those found, for example, in neutron stars or processes that occur in black holes. These are some of the densest objects in the universe where matter behaves very differently under intense gravitational forces. And with our particle accelerators, we basically can recreate and explore those extreme conditions, but in the lab. And at GSI, on FAIR, we have the unique ability to study exotic forms of matter in ways that were once impossible. We can selectively produce, accelerate, and store protons, antiprotons, rare isotopes at unprecedented event rates and energies. And as you can see at the plot, that basically like a bit our menu, what we can provide. This is basically like if you unfold the periodic table of elements, you have on the vertical axis the number of protons which define the element, and in the horizontal axis are the isotopes. So they vary only in the number of neutrons that you have in the core. And many users, by studying the decay processes of these isotopes, you can infer certain processes that also occur at galactic space scales. And yeah, basically people come, point, and say, like, please, can you produce this at this rate? And we have a very high selectivity. So when people ask us, which particles do we accelerate? Anything from protons, antiprotons, up to super heavy elements. And also we created 6 of the rarest elements first observed at, in our labs, like funny names like Darmstadtium, named after the city next to where we hosted, or Hassium, named after the state where we're located at. Of course, there's much more to do. We are not just doing fundamental science, but we're also a technology forge. So many of the things that you need in science, also you need to advance technology to be able to measure those very rare effects. And beyond fundamental research, our heavy ion accelerators have practical applications, like, for example, cancer therapy. Developed at GSI, heavy ion therapy has treated hundreds of patients and is now in clinical use in Heidelberg and Marburg and many other facilities all over the world. And it's a great example how basic research can also lead to life-saving innovations. Because we can create such a large spectrum of different particles, we're also working together with the European Space Agency to study space radiation long-term effects on humans. ESA also wants to send people to Mars, but contrary to Elon Musk, we also want them to be healthy and also come back alive. So we see like what we can do about this, and a lot of testing of radiation hard electronics for future Mars missions, but already some of our electronics and ASICs that we designed are now making their mission towards Jupiter as part of the JUICE mission. So just like a few impressions on what to expect in our facility. Some of you have visited us, and we were very, very happy about this. This is our universal linear accelerator, and is the first particle accelerator in that chain. It plays like a vital role in initiating the acceleration process for many of our experiments and many different particles that are required. So it's very, very flexible. And in the middle, you can see Sharp. That's probably one of our longest standing SDR users. And this picture is quite old, so sometimes I wonder whether he was maybe part of the founding committee of FAIR. But yeah, this is very important. Eventually, linear acceleration becomes inefficient, and you start, okay, this is like sorry, I forgot, this is a picture of the UNILAC internally. This is a very rare view from inside, showcasing the massive size of our resonating cavities and the vacuum tank, and just for scale, you can see a human inside an accelerator and inside a cavity, which you don't have often in the world. But this is usually a very rare image, because most of the time, because of this particle, are very reactive with particles in air. We have to keep the extreme high vacuum in our particle accelerators, even less than that you would find in space or on the moon. So, yeah, eventually linear acceleration has its limits, and then you need like to accelerate in ring accelerators, basically where you have the same cavities, but you bring the beam around over and over again. This is the SIS-18. This is our versatile workhorse and ring accelerator. And it provides basically like booster mode to various experiments and applications, and the flexibility of this accelerator is key, and it has to be adjusted in a multi-user, multi-mission mode on timescales of changing the operation mode within a few seconds or sometimes even milliseconds. So with our current setup at GSI, we've achieved quite remarkable results, but in order to meet the growing demands of modern science, we need more. That means like more power, more particles, more precision, and more versatility. And that's why we are upgrading with FAIR. FAIR will increase both the particle intensities 10,000 times, boost the energy levels that we can achieve, and allows us to explore even more exotic states of matter. And this upgrade is essential for us to push the boundaries of what can be studied and discovered, and also to remain competitive in science. This is like a few schematic overview of the FAIR facility. At its heart, you have the SIS-100 ring accelerator, which spans about like 1,100 meters circumference. And this layout is specifically designed for multi-user parallel operation, showing frequent reconfigurations for the facility, accelerator and particle beams to support a wide range of experiments simultaneously. Running FAIR means also what I mentioned is like means that we have to continuously adjust the accelerator settings, beam parameters, and equipment in order to accommodate our users that are operating the experiments at the same time. And yeah, GNU Radio is part of managing this complexity at our facility. This is like a view of how hopefully soon the site will look like once we replanted all the trees. And FAIR provides a cutting-edge infrastructure that pushes the boundaries across multiple scientific fields. And yeah, I forgot to mention, it's about like 2 kilometers in diameter, the whole site, so it's quite impressive. And we hope that FAIR, like GSI, will continue to be a game changer for physics, chemistry, and beyond. Now, if I would get $1 for every time I've been asked why we use GNU Radio, probably I could have funded like another particle accelerator. And many colleagues asked me, both external and internally, why do you use GNU Radio? What is GNU Radio, and why we have chosen to use it at GSI FAIR? And I thought, like, let's break it down step by step. Maybe this is a bit of preaching to the choir, because you all know but I try to put like a small twist why we use it for particle accelerators. I think one of the important cores is because it's a free open source. It's a key aspect, that it's an open source platform, because this allows us to better interact with our visiting researchers and scientists, also with universities across the world, and also to liaison with industry, because while we do certain developments in-house, also like electronics design, we want to engage more with the industry and also enable them to use the technology to put it into real production use in industry, be it automobile, be it telecommunications, be it radar applications or other things. And we said like, okay, I'll come back to that later. There's also like a general society civic duty that we should do and why we follow this up. The other thing is people say like radio. You're running particle accelerators, why do you need radio waves? So at its source, radio is a software-defined radio framework, which originally has been developed for traditional radio frequency application. But and basically when people think of radio, they always think about this dipolar antenna or other shapes that irradiate RF. But we use RF extensively to shape and manipulate particle beams as part of our radio frequency cavities, because we accelerate charged particles and manipulate them also using strong RF fields. So we have a RF power of a few 10 to 20 megawatts to do that in our facility. But also most importantly is we deploy a wide range of diagnostics tools, from very low radio frequency to up to gamma rays, invasive and non-invasive techniques. And as a nice feature is, if you want to do like a non-invasive measurement of particle beams, you basically observe, when you have ever-moving charging particle beams, they drag an electromagnetic field along inside the accelerator, which is proportional to its beam properties. And what we do is, rather than pointing the antennas out and looking for particles in space, we point them inwards, and looking at the properties of the beam, and first of the field, and then can infer properties of the beam itself and the particles themselves internally. Another important aspect is this paradigm under which GNU Radio works. These are flow graphs, and this helps us while we have a lot of people who have the domain knowledge required to operate particle accelerators and people who know how to do their signal processing and correlation and high-level physics. Not every one of them is a research software engineer. So there's a difference between getting the job done to receive your PhD and to be able to maintain and run a software to have a 24/7 operation. And using flow graphs, this is for us a common denominator where we can speak the same language on a high level, but without losing performance due to this abstraction. And this is for us key, and I'll come back to that later, because this enables us not to have a few people who can write software in our facility, but this enables like tens to up to 100 people more to help to make a meaningful contribution to our facility operation. And that alone was the main reason also why my boss said like, yes, please do that and continue on, because that makes a better use of our resources that we have in-house, and the free new resource we can use for other topics that we can advance new detectors. Important is, obviously this is not a self-serving purpose. We want to have high performance computation, and GNU Radio 4, what was important for us, we use this also in our feedback loops. Feedbacks are real-time systems where the answer that we're getting out of the signal processing is not just where the correctness doesn't just depend on the value of the result that you are getting, but also the time in which you get this result, because we want to react back and put those information into the accelerator to improve our performance of the particle beams. And last, certainly not least, we are not alone. And GNU Radio brings a very diverse community and more than 20 years of expertise in terms of signal processing. And now with GNU Radio 4, it's like modernized for today, where we said like we make an active investment rather than reinventing the wheel. We felt that our goals are in line with the vast majority of GNU Radio users, and said like, okay, rather than building up a second ecosystem for our 10 to 20,000 users, we thought like, let's invest into GNU Radio and share some of the opportunities together. And yeah, sometimes good ideas are equally created in different domains, and just by communicating and sharing these ideas, we all get better collectively. So that was an important aspect. So that's basically in a nutshell. And then what I wanted to say, there's a couple of more slides where I can show you some nice examples in terms of pictures. We also do beam forming. We call it bunch merging. For example, what you can see here is where we have like a bunchlets of small individual beams that are gradually shifted together using RF forces on our cavities and then are merged into one bunch. That's one of the examples. This is an example now in the time domain, but we also use like spectrum monitoring. This is one of our fixed displays that our operators are looking and will be looking at to fine-tune the distribution of the particle beams. In this case, this is a Schottky spectrum and shows us the beam momentum distribution, and this is used to synchronize, for example, the properties between the UNILAC, our linear accelerator, and our first ring accelerator, SIS-18. And by keeping a track of these energy deviations, like the center frequency of these carriers, but also the width and shape of that, we can improve the beam parameter performance. Another exciting topic is accelerators by themselves are also used as detectors, because while the particles traverse in their on the circular trajectory in the trajectory around the accelerators, we can do very high precision mass spectroscopy, and for that we deploy very sensitive high gain antennas or resonant pickups that look at the revolution frequencies of the beams that we store in the particle accelerators. And they're so sensitive that they can even detect individual particles. And by measuring the revolution frequency of the different particles, we can make a mass spectroscopy of the different, not just elements, but also of the isotopes and even like excited states of these elements. And because we can measure individual particles, we can also do time-resolved measurements where we can measure nuclear processes in air, in free, which is very rare, as a time-resolved, as a function of time, which is very valuable because most of these reactions, if you don't have an isolated ions, they're typically absorbed in some form of matter, so you can't observe it any other way, just inferred by the secondary process. And this is a direct measurement of a beta decay, which emits the neutrinos. Now, the name of the game is, our upgrade goals is to shift more and more towards from post-processing that was done largely offline to go online, and one of the ideas is also to use GNU Radio as an active component in our decision-making process, where basically you operate, this is an idea by Sharp, where the idea is to use GNU Radio for routine monitoring and recording of the data, but also shifting more of the pre-processing already in the front end. But if we find very rare isotopes, which sometimes are generated only once per day or once per week, that we can select, oh, we found something, using an early detection scheme in the GNU Radio chain, and say like, please stop, don't inject, don't dump this beam, we want to store this beam for a couple of days and do like more detailed analysis. And that is a powerful tool, and that is ultimately worth of generating several millions worth of signs in a day. Yeah, and this is like one of the science applications, but we also use it for just operating our accelerators. Beam-based services are critical for the operation of accelerators, and you can see basically the scientific users are king, and they expect basically a wide varieties of particle beams with several different properties. And in order to achieve these properties, we need feedback loops, and we're using GNU Radio to implement a very flexible signal processing layer that allows distributed real-time data aggregation and sanitization and post-processing across thousands of devices. So we're dealing with 10 to 100,000 signals. And these are then piped to middle-tier services that do aggregate and correlate the data from different detectors and use to feed back into the accelerators to fine-tune the magnets and the RF cavities. Yeah, this allows also like software-based feedback applications. Okay. So this slide's highlight a bit like the integration of GNU Radio within our open source framework, Open Digitizer framework. Open Digitizer simplifies the digitizing signals from a wide range from devices, not just SDRs, but also oscilloscope, network analyzers, particle counters, scintillators, across the GSI fair site with a target number of around 300 to 400 front-end computers or nodes and a couple of dozen middle-tier services that are distributed across the network. And these nodes feed their meta information into into the dynamic name service, which is basically a catalog of roughly 100,000 signals that the experimental users and operators can choose from. And that where basically is a catalog when say like, please give me this and the signal, and then we transfer the data to, for example, either another middle tier service or an open digitizer UI, which is still work in progress, but is designed to function like a distributed oscilloscope or spectrum analyzer, providing real-time monitoring and diagnostics. The key here is because we have to be very flexible, and sometimes we have to have provisions for the unknown. So some of the facts we can't forecast. I mean, we have a strategy, we prepare most of our data processing chain, but sometimes you have to adjust on the spot to meet a given problem or challenge. And the key here is that we use GNU Radio not just in the digitizing front ends, but also in the middle tier service and in the UI. So if somebody in our control rooms want to experiment, they first could try this in the UI, and if they say like, oh, that's a nice flow graph, but I don't have enough processing power in my end device, please shift it to a middle tier service, or if it's very high performance and I need processing on the level of 250 or 500 megasamples per second, then we can shift it further down to the front ends. And if this is not enough, something that we're working on that we can even like dynamically shift it onto an FPGA on the fly. And this allows also serving with the same device multiple users at the same time because they all look at the same data and reuse the same device. Part of that is our open common middleware, OpenCMW, which implements basically a major domo pattern, providing a common abstraction layers across multiple transport and serializer protocols. Like in a nutshell, it's an open source and streamlines get set, pub sub communications with our open digitized infrastructure. And the main reason is there are many middlewares out there, but this one is designed to be adaptable, that it can wrap different transport protocols and serializer protocols and provide the same high-level user interface for writing services so that you don't have to reinvent the wheel and adapt from MQTT to different REST services through 0MQ and so on. So yeah, key is one is like the transport layer, but for example, GNU Radio is then used also as one of the workers, and the serialization is implicit, can be explicitly specified, but the user doesn't have to care for the how the data is getting in and out. This is taken care by the OpenCMW middleware that we have, and exists both in C++ and Java. Yeah, looking ahead, we're working on expanding cross-platform support to make this user interface more accessible and customizable, and to work also natively, not just on the desktop, but also on the web. And this allows us to modify signal processing analysis both on the UI and the remote front-end controller. Maybe this is not maybe as fanciful as Luigi's example that he showed, but our focus was mostly to provide like a dashboard-style a view of not just frequency data, but also scientific data with units. And the idea is that it's like has to be adaptable. So you can modify this on the fly, and yeah, it's available on the mobile platform. These are just some screenshots from the devices. So basically, you have the possibility to modify the blocks on the go with the standard GNU Radio blocks. So these blocks, in order not to intimidate people, we try to reuse the same look and feel of the existing GNU Radio companion, but in C++. But underneath, it's the same, I guess, the IMGUI node editor. So this can also be made look more fanciful. But we deliberately choose a traditional look so that people have a better relationship to that, or that they recognize the structure. And yeah, there we can both have modify the visual layout, but also the flow graph, and then also create a catalog where you have standard views that can be stored in a catalog and then recalled for different users and applications. So why did we invest into this? For us, GSI FAIR user supports and promotes FAIR. That's the standard, so we do open science and FLOSS. And part of this FAIR acronym is also the interoperability and that R stands for that you can recreate and revalidate the results. So the idea is like, in Germany you say like, okay, if you make the measurement once, it doesn't count. It has to be repeated also by others and verified that this is not a systematic or instrumental effect. So this interoperability and repeatability is key of open science, and it's also part of our mission, and that's the reason why we invest into not just open science, but implicitly also like open source and free source. And particularly for GNU Radio, this aligns with our primary goals. I mean, we contributed not just for the sake because we had not enough time to do, but this solves for us a very specific purpose of high performance continuous and event-based signal processing, also event type data processing, which turned out to be very similar to packet radios. And yeah, with this visual flow graphs, this helps us to bridge the technology gap between people who are experts in their respective domains, signal processing or particle physics, nuclear physics, and the people who know research software engineering, where unfortunately we don't have enough staff that can cover both areas in equal measure. So this helps us, and yeah, to have more staff and users to contribute to GSI FAIR. But our contributions are not just within FAIR. We also have an active engagement with industry and other public organizations. And this helps us reinventing the wheel, simply by co-investing, sharing, maintenance effort. And what's important for us, also as a, let's say, as a state-funded organization, is that we want to invest into open standards, because that is can be very costly things if you diversify, And this helps us also like to build up competencies, because we do state-of-the-art development and working not with legacy standards that are 20, 30 years old, where it's very hard to motivate people, because people know we work with C++20. We have 2 members that are core members of the C++ standardization committee. People come to us and say like, oh, what you're doing is cool, and can I work for you? So in the beginning we had a hard time recruiting, finding the right people, and now basically we don't have to do active recruiting anymore. People apply to us and ask, do you have a position open? And I think that's also like a very powerful experience, I guess, for the industry and other labs that are in this room. This signal flow graph processing concept is not very new, it's very old. I mean, like I looked into what was the origin. It started actually with Bell Labs, so it's always surprising how much was developed at Bell Labs. So there was originally Bloody, and the people built this tool for the very same reason that we use it today, because they said like, it's too expensive to build a hardware, let's do some prototyping first in software. If it works, add more and more components to it, and then in the end, if we need to combine this, we take this knowledge and build the real hardware and standards to be sure that it's viable. And based on this idea, directly spawned also like SPICE, also flow graph based, and other companies like MathWorks or National Instruments also opted for a similar approach, and Siemens. What is maybe important to note is GNU Radio arrived in the early 2000s, but the main thing is, compared to all the previous solutions, is that's open source. So it's unbiased, it's free, everybody can use it, and it's vendor neutral, so you don't have this vendor lock-in, and you don't have to reinvest over and over again into the same idea, same technology. And it's continued being used also like in gaming industry, like Unreal Engine and Unity, and our hope was like to modernize it and make it ready for the next decades to come. So just to explain this, I'm like now in most of the communities, the reasons why we invested is, I'm like many of you use it to express certain ideas. They have a conceptual idea and say like, okay, how can I transfer this into a concept, using flow graphs as an expression as a first starting point, and then you basically iterate back and forth, use it maybe more as a simulation tool. Once you know that the simulation works out, you say like, oh, let's build a basic prototype, which we also do. And there, I should point out the mechanical sympathy was for me very appealing, because I'm coming from RF engineering background in physics, and seeing all these little connectors on this block, say like, ah yes, that's like a LNA amplifier that you can buy off, for example, mini circuits. So that helps also like our RF engineers to connect to this concept much more readily. But then sadly, like the traditional sense was like, there was like a barrier. So whenever people develop the prototype, they say like, okay, let's take that knowledge, throw everything away, all the years of prototyping that we had, and write everything from scratch. That's costly. That's costly. Maybe you get a better integration, but you wasted lots of investment that you put in. And for us, the GNU Radio goal, zero goal was to remove these barriers from going from a prototype to an industrial operational deployments and to achieve a wider public adoption. And then if you want to do this, this is only possible through showing that you get better performance and functionalities, but also help it make it a dependable system that can be used in 24/7 operation. Why invest into GNU Radio for zero, and particularly why to implement a lean, clean, and secure coding practice? That should be self-evident. So when you ask people, yes, should your code be clean, should it be lean, and also secure? Everybody would say like yes. Who would say no? I guess I don't want to put on the spot. Everybody, I guess this we can all agree. But unfortunately, often it isn't, because either collectively we said like, okay, I have to get a job done and I have to move on, and then we only look at the cost at hand that are immediately in front of us. And there's like a very nice IEEE article. This is linked below. I invite you to look at this. This is referencing an article that is 30 years old, and internally you have another article that is 50 years old. The problem that we're facing today is the same problem 30 to 50 years ago. So Melvin Conway wrote a paper already in the 70s, and I make it feel sad that somebody who wrote about this well before I was born and said like, this is a problem we need to address. And we haven't managed to be able to address it. Why? Because people think only at the immediate cost and they don't look at the total cost of ownership. There's a price of doing something, but what many people forget is also a price for not doing something, to omitting doing it, because this will come back. If you don't write clean software, you have certain challenges and risk. For example, if you have a code base where you just add to it, the larger the code base becomes, the more non-secure your code base increases, and this also increases the cost and risk for maintaining this code base until it blows up. And the standardization effort is very important. Was recently an NSA lecture released to the public by the late Admiral Grace Hopper, who worked on standardization across different fields, and that she said like, also there's a price for doing something, also for not doing something. And she said like, what is the most scariest thing you can do? Who are the most scariest people in the US that you can ask? And she went to the Congressional Budget Accounting Office, and they looked into what is the cost of having a heterogeneous standard. At that time was like COBOL, but I think it applies also today to other standards. And they figured out by having not vendor-neutral implementations costed the United States $240 million every year. We're facing the same thing, the same problem today. Maybe this were like 1970s cost, now they're much higher. And on top of that, there's a risk also in terms of security, because using software is ubiquitous, especially software-defined radios is used in many applications, also safety-critical application. And the risk for critical infrastructure, we know that the Eastern Pipeline is a good example. Recently, we had like a major incident with Microsoft that shut down half of the world because of a simple coding bug. Now you can say like, win of the job, not my job award, and maybe I try to hide and blame it somebody else, and say like, was not my fault. Or the other thing is, and which I think is the right thing to do, is to step up and say like, take charge. We have the possibility to address this problem and work together. And so I don't want to be too gloomy, but I think there's a great opportunity in GNU Radio to share in this responsibility. I mean, like, nobody is alone. Nobody asks you individually, oh, you alone have to fix the world's problems, or you have to do everything in GNU Radio. But if we pool our resources together and work together, we can mitigate some of the costs for having a continuous improvement and keeping our code base lean and clean. Also that if it's lean and clean, it's easier to audit. and get security certifications. It also helps to improve the bus factor and burnout for core maintainers, because that's one of the biggest risks, that people say like, no, I don't want to do it anymore, and then just leave. And then you lose a lot of corporate knowledge and expertise, and also motivation. We can do something against it together. And the idea, that's my message, I want to say like, let's promote GNU Radio as a free and open industry standard, where we all rally behind and say like, we invest together into that. Because if we don't, their governments, both the US White House, the White House in the US, but also the European Union, have already legislation that says like, if you don't take care, please be proactive. Both in terms of the Cybersecurity Act in the European Union, but also in terms of product liability. If you're not proactive, the legal system will tighten up the thumb screws more and more. And I think this is unnecessary, because we don't want to get the government involved in terms of legal aspects, because they have ultimately no clue about how to regulate low-level technology. So, yeah, for GNU Radio to be used in a critical public infrastructure, or I believe any real-world commercial applications, it must meet higher standards for safety, cybersecurity, and product liability. And I encourage you to take charge and do something about this. So now a bit like the technical highlights. I have to go through this a bit faster. Sorry if I skim through some of the details. I mean, I started everything like, not in the mid-2002, sorry, it was mid-2022, when Derek Kosel and Josh Mormon, basically whatever is good, it's their responsibility, and they approach us, oh, you use GNU Radio? Why do you use it for particle accelerators? And at that time we used GNU Radio 3.7, and we had some issues and tried to do some workarounds. And then both Derek and Josh said like, why? It should be easy to solve. And Josh, single-handedly, within 2 weeks, he solved the problem of this compile time reflection of being able to use GNU Radio just in C++ without the necessary Python binding. And we thought like, wow. And then they came back, and maybe that was a mistake. Josh, please, I'm sorry, was if you had the chance, were there other things you would like to change? And then we said like, well, since you ask, we have this concept of event-based processing, and after some discussions we realized that's the same problem as packet radios, that what Danny now is implementing. And so like, oh, that's the same problem, why not work together? And we had many more discussions on the GNU Radio architecture channels, and then basically highlighted some of the pain points that we thought like with the GNU Radio 4.0 we could address. Importantly, we said like, we don't do this alone, but we do this together in a collaborative spirit. And said like, okay, let's look at the buffers and computer-related performance, help making asynchronous event processing basically a first-class citizens of GNU Radio, and also the scheduler to be able to make it more flexible, so that you don't have like just one way of how to run and schedule processes, but that depending on the application you can tune between throughput and latency. Also, the idea is to make it easier for integrating vendor-neutral hardware, but also heterogeneous distributed or embedded computing, and also to help the GNU Radio community to grow, to make developing blocks easier, safer, leaner, and cleaner, and easier to maintain on the long run. So community building is very important, but also the building up a technical also while maintaining a technical relevance. I think we didn't want to create something that is not GNU Radio, so that was always core. And there were like certain underpinning things that needed to be done, like reliance on true hardware, real hardware or true industry standards, reducing the cognitive complexity, because now the learning curve getting to GNU Radio, once you're in, you say like it's easy, but getting into it is very high. And work together, not just academia or science, but to do this all together with the government and the industry. Important, if it's worthwhile, it has to be technical relevance. That's the reason why performance was key. And the next few slides I showed what were the performance gains that we were able to achieve now with this, with the GNU Radio 4.0. So I'm not just going through. One is like safer, leaner, cleaner API. We moved from a framework where basically where you have a prescriptive framework where you could exchange blocks, but they always had to have the same shape, but maybe different colors, to like more modular approach. I call it like the Lego assumption approach where you can, which is performance and functionality focused, where you only have to pay for what you need. That's like a part of C++, which is free to extend and modify, but also that is compatible and auditable, and that can be used with a public infrastructure. So I think the important part is like to preserve the concepts. And what we did together in the architecture team, this was also led by Josh and others, was to highlight what is a block, because we didn't want to have something completely new. So we thought, what are the key essence? What is a block? What is an input streaming port? What are tags? The same thing, you have the output ports. So we tried to not define new, but to select to sharpen the definition. What is each of the different components supposed to do? And how can we implement it most concisely, most efficiently in the different domains so that it's composable and that you can exchange also the implementation. And also looked on standardizing what the message port, which used to be like a control port, where we said like, okay, let's get rid of some of the heterogeneity and make it more streamlined. And that's basically the result. If I need to teach how to write a block in GNU Radio 4, that's one slide. That's not slideware, that's actually part of our production code, part of our unit test. That's all you need to know. You need to describe the input ports that you want to have with the type, the output port, and your processing function, where you say like, I get my input data, and you write a pure mathematical function. Anybody who can understand math or write basic physics can write a function that executes the processing that you need. And because it's lean and clean, it's easy to learn, but it's also easy to audit, and can be also used better by compilers to optimize the whole chain of how you string those functions together. There's often also the possibility to extend it to heterogeneous computing, like for example SIMD. Or if you say you want to have more like the traditional sampling aspect, you can also have process bulk functions where you get chunks of data, input and output, where basically the rational resampler is a first-class citizen. So this is like let's say, a more advanced level of API. And then you can also make it even asynchronous. You can declare how many samples you consume or you produce. This is not slideware, this compiles. So we also try to keep conventions with the GNU Radio companion in order to produce YAML files. Describe this topology. On the left side, you can see a topology for basic flow graph. The blocks in the top, connections in the bottom, and within GR4 you can read and write those definitions and execute it. So any integration in UI should be simple with that. And but while we have like let's say, a UI for our purposes, I think this UI and UX integration and Python bindings need to be community driven. So this is somebody from you has to step in and make a proposal how to do this best. Similarly with Python integration, for us was always important that we can also integrate it with Python. There are two ways: either you have Python within C++, or you use Python and you call C++ from that. So there's two paradigms. This is an example where we have a Python block which you can instantiate in your flow graph, and the processing functions are written in Python. So this is not for Python plumbing, but for the part where you can use NumPy and other features to derive your features. Everything is compile time reflection based, so single source of truth. We don't have a separate documentation of code and explanation. Everything is in the source code, and you can generate automatically documentation. If you want to know more, there was recently like a workshop with lots of good tutorials, and you can find it on YouTube, both on the GNU Radio YouTube channel. Okay, buffers, important. If you think about like mechanical sympathy, that's a concept that we followed. You don't have to be engineered to be a racing driver, but you do have to have mechanical sympathy. So more general, in order you want to optimize your processing, you have to understand on how the machines you're working on itself work to be able to get the best performance out of the machine. And that means basically you have to know how do chips and CPUs work, and how does the architecture look like? Because with this way you can get a better performance and structure your code in a way that you get the best out. I think I skip over this. Everybody knows what the difference between bandwidth, latency, and throughput. if you need lower latencies, basically you need either higher I/O memory bandwidth or minimize the critical data sections. There's an example between like what is concurrent and concurrent parallel. Typically, the latency is defined by the longest time it takes to execute a certain functions. This is in the ideal world, but often you have like certain overhead due to context switches and systematic overheads due to the different constraints you have in your operating systems and your CPU. And typically, the classical paradigm in GNU Radio 3 was you minimize the impact of this context switches and overheads by just computing more and more data so that you have the calling of the functions higher, as low as possible. But the problem is that this is a very bad strategy for latency. So if you want to decrease the latency, you have to tackle actually what are the sources for these context switches, or maybe avoid them at all, that you don't need them. So that was the main goal of our redesign of the low level and looking onto the different caching strategies and optimizing it. We don't have to go into this, there are some links. So for the buffer, basically it has the same thing, but it deploys these principles on a much lower level. Maybe two noteworthy things is there are new features. You can now safely and efficiently propagate both unstructured safe data types, so no more null pointers or void pointers, so that should make it safer and more secure. But the new buffer also allows to transfer structured data types. So that is like used for the event-based processing. That, in addition, yeah, because of using a log-free programming, which is SIMD and also CPU optimized, we could achieve a 10 times performance just for the buffers compared to GNU Radio 3.10. We also moved away from virtual inheritance and went to strict typing and CRTP concepts. I don't want to go too much detail, but the way how we write code is easier to optimize by the compiler, and that's one of the reasons why the performance, just because of this move, is also like yet another factor 10 faster. And yeah, the best buffer, if you want to go for low latencies, the best buffer is if you don't need a buffer at all. So we introduced like a merge API where you can combine functions across different blocks into one block without paying extra overhead, but still retaining the syntax and the meaning on what is the logical functions that are concatenated. Yeah, just some performance figures. Yeah, you can see like in red, this is like a factor. You're going from something 250 mega samples per second. We achieve typically with this runtime polymorphism up to 500 mega samples per second, but now with certain flow graphs, we get even like in the order of a few 10 giga samples per second. I think that was not yet possible in the GNU Radio 3. Yeah, let's go. Okay, asynchronous event-based, I think I skipped this over because I think that is, clear that structured data can be used to basically do multiplexing and chopping the data out of the data stream. Key takeaway can be used to process any structured data type, and this you can also develop feedback loops or packet radios very efficiently. And the idea is to extend this further also to the UI level, where you can program certain feedback loops similarly to what you find, for example, in the gaming industry. Data synchronization, these two clock problems, is also solved via standardization of the triggers on the tags. I think that's clear how that works. I think what is maybe more important, what many people ask, like the scheduler, it was very important. There were like basically two limiting factors in the GNU Radio 3 design. The main pain points and reason why the GNU Radio 4 development started. One was that every block is also like a Stutz thread, and their processing function is basically managed by the system scheduler. And the problem is that basically all the blocks were competing for resources. So you had 10,000s of blocks, even though the CPU could, or your system could only execute 4 of them at a time. And then invoking those threads and checking out, can I run and process data, was wasteful, and basically you lost a lot of performance just because of that. And also because the blocks in themselves didn't know about the topology they were embedded, so most of the blocks took a maximum, couldn't take the maximum minimum buffer data into account, and this created undesired latencies because they tried to ingest as much data as possible and produce as much data as possible. And yeah, this is just an example. If you go, for example, a data source produces, this is like a graph where each block can process only a certain number of samples. And if you, for example, produce 1,024 samples, but the next block can only ingest a certain limited number of samples, basically you have to oscillate between the blocks back and forth and check, can I produce data? Yes, no, I don't have enough data. And until the point where you have all the data ready, and then you can go to the block 3. And this context switches is a lot. And then the same thing happens also between block 2 and 3. And if you continue playing this, you get like to a latency, the minimum until the first sample gets out of 19 cycles, but for the whole processing, you can see like 2 lines in order to just illustrate the execution order, what you have. And now the thing is, if you look at this, you think like, okay, there are lots of white and blue boxes that I don't care for, that waste performance. Couldn't I do this just by reordering this way to have like a bit more smarter scheduling of the work? And here you, for example, you have a throughput optimized where within 18 cycles, you get more data out. Or you can also select no latency is more important. You would order in this way, and then you get like a latency of 11 cycles. This problem is not new. This has been documented by Matt Ettis and also a prototype developed by Derek. And they basically created like a scheme like with floodgates that inhibited the number of samples that go into a flow graph and so on. And what we did is basically we went from this. Basically, the directors of each of the blocks were initially implemented inside the blocks themselves. And also in the GPU domain, for example, we're inside blocks, and we said like, okay, these blocks can't make the decisions on their own. Let's move that logic out to a central instance. We have like a scheduler that is global or per domain, and where all this logic is basically implemented there, and that allows, I know this. Is in there. So with this strategy, you go from a microservice-based scheduler to a work-based scheduler where you're much more flexible on how you handle this resource constraints between latencies and throughput, and deploy also like a lot of mathematics, like in terms of graph theory. Here's some examples for the flow graphs as a challenge that are challenging for the present scheme or impossible, especially with these feedback loops. And I leave it to you like as an exercise to go through what is the best or correct, best and most efficient way how to execute these orders. Because while we implemented like 3 types of schedulers, these are just to demonstrate the API that is necessary to write your own scheduler. But there are many, many other possibilities that you could implement. And what we would like to start maybe for the next GRCon is to have like a small friendly competition to find the best default scheduler that has the best real-time throughput or latency performance for a given benchmark topology. So please have a look and maybe think about like if you would write a scheduler, what would be the best way to do so. Yeah, okay, this is just like in the end, we are supporting the Public Money, Public Code campaign. Have a look. You can also sign up individually, not just as an organization, but if you sign up individually, please convince also your boss or your organization to take part and also follow up this thing. That's very important. We want to drive further the community engagement because that's vital for this project, but we also have some improvements for the core library and user experiences that we're now ironing out to bring GNU Radio from a beta stage to a production stage. And also we have some ideas how to add a more vendor-neutral integration for GPU, FPGAs, and other TPU and other processing topologies. So the 2 open questions that I would like you to ponder until we maybe meet again this afternoon is, what would it take for your organization, institute, or company to publicly adopt GNU Radio 4.0? And the second question is the present license still too restrictive for GNU Radio to be used in a public organization or industry? And yeah, that concludes my talk. Thank you for your time, your patience. Sorry that I took a bit more of my time share than I supposed to. I apologize, but I guess we have like 1 or 2 questions. If not, then please come this afternoon for the general Q&A session, and we can talk in depth about each of the different aspects in detail.
Thank you very much, Ralph, for your presentation. You've already heard it and maybe noticed we went over our time budget, so we take a short 10-minute break, and there will be a Q&A session. I'll a real long one this afternoon. It's in room 301B, starts at 1 p.m. So if you have questions, join Ralph there and have a healthy discussion. Thank you, and that concludes the session, and see you back soon in the room here.
Yes, there are.
actually created to be like the ultimate SigMF tool. And as far as companies using it who are kind of public about it, Muon Space is doing some awesome stuff, bringing raw RF from orbit down to the ground, using SigMF for the metadata, DeepSig, Airbus, and then I found recently this open source threat intelligence tool called MISP supports it. And then MATLAB does have a SigMF function, but unfortunately it's like the sigmoidal member function. It has nothing to do with SigMF. So, yeah. Now that being said, if you're in any language, you can always read in a binary file, like with NumPy, you can do from file, as long as you know the data type. Pretty much every language has a way to read in JSON. So you don't need your language or your framework to really support SigMF in order to create or read in recordings. And this is kind of the, it's not a minimal example. The minimal SigMF metadata would be like just sample rate data type. But this is kind of a short example of what a metadata file might look like. So we have the global section where you have fields that are common to the whole recording. So sample rate. Now with SigMF, we don't support changing the sample rate in a single file. If you have information about the hardware that was used to record it, or whatever you want, there's additional fields besides what I show here for global. And then captures is meant for when your frequency changes mid-recording or you stop and start the recording for disjoint time. That's how you would record that in the metadata. See, the captures is an array, and you would just add new items every time you either change your frequency or start and stop. And once again, there's extra fields that aren't shown here, like geolocation and stuff. Now, annotations is how you would mark up a recording, kind of like adding a comment to code. They're essentially, each annotation is a bounding box in time and frequency. And you can put a label on it, you can put a larger description, and you don't actually need the, I think the frequency is optional, right? Yeah, but I typically, I always use both the time and the frequency domain when I'm adding an annotation. Now, as far as the data type, as you may know, binary IQ files, or the samples coming out of your SDR, could be floats, integers. This is SigMF's kind of key for how the data type field is formulated. And this is actually not the entire set, but it's the common ones for complex samples. SigMF also supports real samples if you're doing direct sampling or anything like that. But these are the most common data types that you'll see. Now, as far as where to find the specs, that's one thing that's kind of changed, because in the past there was a single markdown file in our repo that would have the specs and a bunch of description around it. But in the past year, we moved things because we started refining our JSON schema, which a lot of folks requested. And we realized we don't want information in two places. So now we have everything living in the JSON schema, like both the actual schema and the description of each field. And the specs is now rendered from that schema, as well as a little markdown file with some introductory text. And we render both an HTML and a PDF from that schema. The HTML is what we host at sigmf.org. And then the PDF can also be found. I think there's a link to it on the GitHub repo. And yeah, I mean, it's nice as far as maintaining the specs now. Everything lives in one spot. And we can really work on refining the JSON schema that a lot of the software folks focus on. So I mentioned there's the core SigMF specs, but there's also a group of kind of extensions that live in the main repo. Maybe calling them core extensions is misleading, but there's kind of refined extensions, and I have a list at the top right here. So for example, if you are trying to add like GeoJSON, like lat-lon to your either your receiver or an annotation, there's the spatial extension. Yeah, and then we also have a community this is actually pretty new. We have this community extensions repo, and that's where you would sort of propose a new extension, or maybe if you're using one internally, like at your company, and you think it would be useful for other people, you could make a PR in the community extensions. And then if we find that a lot of people are using the same extension, we have a process for moving it into the core, the main repo. But we do want it to be used by at least more than one group by the time it moves to the core, the main repo. Because even if your extension's awesome and perfect for what you're doing, if it doesn't really apply to other people, if it's too specific to what you're doing, then there's no real notion of like software interoperability, because other software is not going to implement and use those fields. So you're free to keep using the extension yourself, but there's no point of making it this big main extension. Okay, so as far as GNU Radio goes, we currently have the minimal blocks, which is the most basic SigMF functionality you can imagine. They're pretty much just wrappers around file source, file sync. We added them a while ago just to get something in GNU Radio. And I'm glad we did, because when we lock down like Ubuntu's release every 2 years, it's nice to have something like this. But in the long term, we really want a full gr-SigMF. Now, the other kind of out-of-tree module that you might want to look at if you're doing a lot of SigMF in GNU Radio is Jacob Gilbert's utility here. It includes a lot more functionality, like actually adding metadata as stream tags, and in reverse, making metadata out of stream tags. The actual file source block has like type conversions, which the minimal blocks don't have. You have to specify the type, I believe, when you use the minimal block. And by the way, I forgot to mention, Jacob Gilbert and myself are sort of leading the SigMF like leadership, I guess, within the GNU Radio organization. But there are a lot of folks involved. Now, there's also our Python package. So separate from GNU Radio, if you're working in Python, you have the option of using our SigMF package, which lives in our main organization. It can read SigMF, create recordings, and it has a validator that uses the schema to validate your SigMF metadata. It has a lot of functionality. It can deal with collections and archives. And a huge thanks to Kyle, who maintains that repo. But there are many contributors. As far as collections and archives, this is a part of SigMF that some folks may not be as familiar with. So if you have a bunch of recordings and you want to logically group them, in this example, it might be hard to see, but I've got 4 recordings, which means there's 8 files total. There's the data and meta for each one. What you can do is create this .sigmf collection file. And it's essentially just a quick way to say that all these go together. Now, this is different from archiving. So when you make an archive, that's tarring all these files. And that's what we call a SigMF archive. It does not include compression. Right, a .tar does not actually add the compression. If you want to add compression yourself, you can choose whatever you want. SigMF doesn't really specify that, and we get that question quite a bit. And that's called an archive. Now, as far as updates over the last year, so version 1.2 was released earlier this year. There actually weren't a ton of changes to the core spec. We added a UUID to the annotations object. There were some tweaks to the spatial extension, but mainly we were improving language and making it easier for people to understand when reading the specs for the first time. And we're now also officially recommending collections as sort of the go-to method when you have multi-channel recordings. So if you're doing any sort of like array processing, whether 2 or more receive channels at the same time, some folks in the past had been using num channels, which was originally added more for like not as much RF-related reasons. But now our recommendation is to use collections where each channel is a separate recording. And that way you have a lot of ability to load those files into all sorts of software, because each one is a single IQ file. There's no interleaving of channels, which like most software doesn't really support that out of the box. Now the downside is you have a lot of files. So if you have like a 16-channel receiver, now you've got 32 or 33 files, and that's where the archives come in. You can tar them into a single file, make an archive out of it. As far as next steps for the project, so SigMF.org now has our HTML generated specs, but there's no landing page yet, so we're going to look into making one. The closest thing other than the README, the GitHub README, would be IQEngine.org/SigMF is kind of like a one-stop place to go for all the SigMF resources. It includes a learn SigMF in 5 minutes sort of read through with some examples. Another thing we need to do at some point is actually make JSON schemas for all of the extensions. That way they can get included in the rendered documentation. There were some ideas for a VS Code extension. There was one in the wild, but it really only did validation with the schema. So there's some ideas there for like graphically being able to edit the metadata. And then we're hoping to get our Wikipedia page approved soon. And by the way, we're actually not, we sort of moved away from using SigMF as an acronym. Initially, it stood for signal metadata format, I think. But now we're sort of just trying to call it SigMF, like you see here. And yeah, but we're in a pretty stable state, so that's why there hasn't been a ton of changes. And more folks are using it each year, and we highly recommend it. If you're using binary IQ files already, it's a very, very tiny step to start using SigMF. You don't need any software. You can just open up a notepad file and manually fill in the JSON. There's a bunch of examples on the README and on IQEngine with example metadata that you can copy paste and then just change the fields you're interested in. So it's not a huge leap, especially if you only have a few recordings. And with that, in order to get back on schedule, I'll ask that any questions be directed to the SigMF channel on Matrix, which is where we have discussions. And I'll go ahead and give it over to the next speaker. Thank you.
All right, next up we have Progressing 802.11ah implementation in GNU Radio with gr-halow.
Okay, got this working. All right, good morning, everyone. My name is Sam Miller. I'm excited to be at my first GRCon presenting my progress in an open source implementation of Halo, which is otherwise known as 802.11ah. It's a substandard of the Wi-Fi spec. If we could all hold questions to the end, I know we're getting close to lunch, but I'll do my best to save some time for any questions you might have. All right, so at home, I like to play with SDRs a lot, obviously, like many of us here. And I like playing with Meshtastic devices, other IoT nodes like Zigbee, Bluetooth, and others. And one day I stumbled on Halo devices. And I thought it was pretty cool because it offered a good trade-off of data rate and distance. For those of you that have used Meshtastic, it's a great long-range text messaging, mesh-based communication, but there's some capability to be desired if you want to send images or maybe even have like more of a traditional like IP-based mesh network scheme for something like maybe cameras or higher throughput sensor nodes. So I thought I'd give Halo a shot. And when I bought my nodes, they advertised WPA3 encryption and everything, and I was like, well, if this is an open part of Wi-Fi, let's take a look at it with an SDR. And see how much I can learn from it. But unfortunately, kind of like I have stated here, like what's the main problem? There weren't a lot of devices available. There weren't a lot of open source repositories to be able to already decode Wi-Fi Halo. So for a protocol that was supposed to have over 8,000 devices that are able to connect in the network at one time, or be an IoT standard that has ubiquitous access, there just wasn't that ubiquity just yet. So the then straightforward but ambitious solution was to try and create as much as I could towards a full transceiver architecture in GNU Radio. And this is just so anyone with an SDR that might not want to invest in the commercial Halo devices that are out in the market today could just pick up their radio and start giving the Halo network a scan to understand and interact with it a little bit more. It also provides a good third-party debugging device if you have a Halo network working and you just want to kind of step aside with just a software-defined radio and analyze your network. So just trying to open up the use towards everyone. And one key benefit of Halo versus the legacy Wi-Fi, so I consider that 802.11n and before, is that its bandwidths are well within the range of even the most inexpensive SDRs. So you're looking at 1, 2, 4, 8, and 16 megahertz. So even something like the RTL SDR can pick up the smallest channel bandwidths available. Furthermore, some of the data rates are well achievable with commercial processors. As few as 150 kilobits per second over those 1 megahertz channels, but as you get up into the higher channels and the MIMO processing, you can get up into like 80 megabits per second, which is pretty substantial. And then lastly, kind of just like I said before, sits in that middle of that data rate and distance trade-off. So it's pretty useful for some applications where you might have like distributed sensing, like on drones, or if you're there's one application out right now actually that's pictured on the screen for the Amateur Radio Emergency Data Network. That company is Teledactics, and they set previously in July the current Halo distance record from what I could find at 66 miles with a 30 dBm transmitter and a directional antenna. So pretty impressive achievement on their part. Okay, so then what's my approach going to be in taking this ambitious leap towards an open transceiver architecture? It was a threefold step. First and foremost, I kind of wanted to have something available for people to run at the conference if they were interested. And so how that manifested itself was in the Halo activity scanner, which I'll go into detail shortly. I did try and take a step towards the full receiver implementation. I have some elements of that working, but as a whole, it isn't working yet. And we'll also cover my shortcomings on the full receive implementation. And then once I was able to do that, my ideas were to go full transmit, so we could just have bidirectional transmit and receive functionality. And I also want to take this time to thank Bastian Blossel for his contributions to GRI-EEE 802.11. I use his repository as a huge leaping point and foundation for 802.11ah. And while my repository and his aren't compatible right now because I made some breaking changes to 802.11 in my fork for AH, eventually I would like to get it merged into GRI-EEE 802.11 so you can start to use A, G, P, AH, whichever sub-protocol you're interested in, but that does lie down the road. Okay, so first, like I mentioned, I'm going to detail my activity scanner a little bit more. This is just an overview of the GNU Radio flow graph as a whole. I'll break down every component in here and then culminate in a video demonstration. And right now you can access the code up on GitHub, so if you want to give it a shot. So the first obvious modification I had to make was to the channel lists. So 802.11ah works in the 900 megahertz ISM band in the US, and it uses fewer channels across 5 different possible channel bandwidths pictured there on the screen. And in the experimentation that I was doing with some actual Halo devices, I found that annoyingly some of the manufacturers didn't stick to the IEEE specification when it came to the channel numbers. So I just implemented a JSON configuration file where based off of whichever channel format that you're used to seeing, you could pair that with the frequency and the bandwidth of the channel that you're expecting, feed that into the scanner, and it would parse that configuration file in order to tell the radio which channels to look at for Halo activity. This is a fairly straightforward change, but necessary one. The next major change I had to make for AH was in the timing. So in legacy Wi-Fi, it was pretty convenient because a lot of the ratios were constant. So the number of subcarriers stayed the same across the different bandwidths, but also the ratio of the channel bandwidth to the OFDM symbol time was constant. So you always had 80 samples per symbol no matter which channel you used in the old Wi-Fi. And that made it easy in the implementation of GRI 802.11. You can just either pound define, samples per symbol as 80 or just hard code that 80 value in there. But the switch over to Halo was a variable relationship in all those factors above. So you start to see the number of subcarriers increase for each of the respective channel bandwidths. You also see that the symbol time is constant across all channel bandwidths, which means as you increase the bandwidth, you get fewer and fewer samples per symbol. So the key approach that you'll have to take there in implementing IEEE 802.11h is doing more or less an object-oriented definition for each bandwidth, so that when you're going into your receiver, you can reference the variable within that object to determine what your samples per symbol will be, and also the number of subcarriers you'll have. But for my scanner, I just focused on the 1 megahertz channel for now, kind of set the stage for that object-oriented approach, but I really wanted to get the full thing working with 1 megahertz, so I didn't see much value in trying to get all the channels working if I wasn't sure if the whole implementation was going to work right away. So this is the result of that fix. You see before on the left side of the screen where I hadn't applied those timing corrections. The flow graph was trying to tag the beginning of a Halo packet, but the tags were just kind of appearing erratically throughout the packet. But after applying the timing fix in the middle, the tags were showing up reliably at the start of each packet. So now I could reliably determine whether there was a Halo packet on the channel you're interested in, and when the start of the packet was, as well as the rough frequency offset of that frame. However, I did see that on adjacent channels, whether this was just due to poor channel rejection of the device I was using or just good autocorrelation properties on that that side channel, I was seeing some like false alarm detections. I was, on channel 1, but truly there was some Halo activity on channel 2, and I was getting some false alarms. So this, in and of itself, wasn't enough to be able to build a robust scanner. So I had to then add in 2 additional blocks here. So these are just embedded Python blocks. The one on the left is the main scan controller. So this is pretty standard. It takes the bandwidth available to you for the SDR that you have plugged in, and it will parse in that JSON configuration file that I mentioned earlier in the presentation and determine fixed windows that it can place your center frequency and your bandwidth so that you can see the maximum number of Halo channels simultaneously. Then it uses a frequency translating FIR filter to sweep through each of those channels with a given loiter time that you have for that channel. We'll get into this in the video demo, but I did notice that longer loiter times had better chance of reliable detections, but obviously at the trade-off that you're lingering on channels for a little bit longer. And then the activity detector was really the way to try and solve the issue where tags might show up for adjacent channels. And just from some of my observations, I saw that generally a lower frequency offset correlated with the fact that you're actually seeing a packet on your channel. I noticed that if I was getting false alarms, my frequency offset would be higher. It would try and correct for that some more. So I used that as one threshold. And I also used the power average as a threshold. So on a certain, on the actual Halo channel, you typically saw, higher power than you would on adjacent channels. And what you see pictured at the bottom there is a successful test where the Halo scanner was moving through the different channels, And then on the channel where my devices were already pre-programmed, it was receiving packets. And for the time being, I was just outputting to the GNU Radio serial console there, so I was just getting a detection alert every time I detected a packet. So that was good news. And at this point, I was able to go do a test outdoors to see, just really how well this would work. And we're going to try and pull up a video here just to show that test. Okay. All right, so first obviously started off in setting up my Halo network, and then I was scanning everything with an SDR, just have a little mock-up of the network there, but the first thing I had to do was kind of go in and verify my network settings. So this is just doing a little bit of a sanity check, making sure my laptop's getting an IP address from each of the Halo routers that I have. Then I'm going to actually serial into each of the devices in order to verify some of the device settings, make sure that they're the same version. These devices do run OpenWRT, which is convenient. And then actually modifying a setting in the radio to turn rate control off, and also fix a given modulation coding scheme. So I'm pretty much telling it to transmit BPSK, which in this case is modulation coding scheme index 0. And I'm just verifying the settings there on the screen. And I have to do the same thing for the other device, but before I do that, I'll navigate to the web console, because on there it'll actually show if there are other devices that are actively connected, as well as verify the channel frequency, bandwidth, and power settings. So that'll pull up on a nice convenient little dashboard here, and I can see that there's one MAC address of a connected device, and all the other settings matched from the command line interface app that I saw before. So everything looks good on device 1. Now I'm going to go repeat the process on device 2, just another sanity check to make sure everything's constant, and that I can actually establish that Halo network. I am doing a little bit more here than you would need if you were actually trying to run this device network. I'm just trying to be verbose about making sure my test conditions are the same. So again, setting the modulation coding scheme to 0 so these devices can communicate. And then the final sanity check is going to the configuration dashboard of the second device and ensuring the settings are the same and that it sees the first device that I went through before. And great, second sanity check passes. So the Halo devices are now communicating with each other over just a simple iPerf test, and I can now scan the Halo network. So you see the flow graph pulled up here. It's time tag-based detection on the time plot, and in the bottom you can see the Halo activity. So I got a success there when I was actually scanning past the channel. And then here I'm going to repeat the process for just a faster loader time to show that it actually skips over the desired channel a couple times before getting a final good detection on like the last sweep. So just illustrating a little bit of the trade-off that I saw between the longer and shorter loader times. And then here was the actual like distance testing I conducted, just roughly yes or no, did I receive Halo packets or not? So at my really short 18-meter distance, I got detections 50 meters away through some trees, was still able to get some packets. Even 100 meters away, I was getting reliable Halo detections, which was awesome. But about 200 meters away was when my signal was just not making it back to my receiver, my software-defined radio anymore. So that's just to illustrate a little bit of what like the Halo network is capable of. And now we'll kind of go through where I fell short in implementing the receive implementation. and maybe get some ideas for how I could do better in the future. Okay, so the full receiver doesn't really add much on the end. It's now just trying to take the OFDM signal, take it into the frequency domain, and actually decode some of the packets after equalizing and synchronizing. So the first modification I had to make was Halo applies a different training field sequence to the packets in order to equalize in the time domain. So just as the 802.11 spec showed, I just applied an inverse Fourier transform on the Halo packet in order to get that proper input into the equalizer. But then again, I was using BPSK, so the equalizer shouldn't have a significant effect here. I will say that this will probably have a better effect when the rate control brings higher order modulation schemes into the picture. But this I felt was still a necessary step. The next step was modifying the physical layer protocol data unit format, or PPDU format. The signal field of Halo is actually way more verbose than that of legacy Wi-Fi, so I was actually using this as my litmus test to determine whether my receive was actually working or not, because as I showed in the video, I was setting the exact modulation coding scheme. So I was expecting to see that exact same modulation coding scheme in one of these signal fields. And then there's also a length field in here, so that would have provided an additional sanity check in saying, well, did my length field match about roughly how long this packet I received was? So while I did get the deserializer for this written up in C++, I wasn't getting reliable receive detections, which was telling me that there was something earlier in my flow that was going wrong. So somewhere between detecting the Halo packet from the scanner and for taking it out to bits in the signal field. But I did see that if I was able to get reliable bits out into the signal field, that it would have been fairly straightforward to then take that a step further and get actual information from the data field. And I was testing this all with unencrypted data, so I should have been actually able to kind of see this in plain text flying over the air. And another point I'll mention here, kind of in a similar vein to how the Halo timing was variable and needed a object-oriented approach, the PPDU format is also variable between various Halo channels. So there's a great variety in the signal field, even between the 1 megahertz, 2 megahertz, and 4 megahertz channels. So this is also going to need a very catered approach for decoding all the different available channels on Wi-Fi Halo. So here's where I think I could really do better. I was trying to kind of like rush to get a solution, but I'm reminded that being more deliberate is the correct and most thorough approach. So I think by implementing more intermediate tests in that frame equalizer block, I could try and isolate where my problem is. So realistically, and I have it pictured up on the screen in the bottom left there, the Halo equalizer is trying to do four things. So breaking those steps out and kind of being rigorous about looking at the inputs and the outputs to each block, testing each one to make sure that it matches what I would expect, and see where I'm going wrong. Like I mentioned before, I'm doing BPSK now, so equalization shouldn't have that much of an impact, but where I do believe something might be throwing me off is in the polarity of the fixed pilots and the possibility of traveling pilots. So I might just be implementing the polarity of fixed pilots on Halo wrong, and that's affecting my ability to synchronize to the actual data that's coming over the air. But also, Halo in the standard says that it can either have fixed pilots or this concept of traveling pilots, where the pilots will, the subcarrier index will actually vary with each symbol. This is to try and get a better characterization of the OFDM channel. So I'll probably have to, branch my code off into different branches to try and implement fixed pilots in one, traveling pilots in another, to see which which approach wins out. Unfortunately, I did try and dig into the configuration of my Halo devices, and I wasn't able to control the traveling pilots like I was able to control the modulation coding scheme. So this one I might just have to brute force a little bit more, but those are the two areas I think that might just be throwing the receive off a little bit. Yeah, here are some of the resources I used. I want to thank Marc for helping me out earlier in the week. I made about like 12 SigMF recordings of my Halo device. So you can scratch off the upload to IQEngine as pending because it's actually there right now. And you can play around with some Halo recordings if you're so inclined and want to check them out. I made recordings in the 1, 2, and 4 megahertz channels at 3 various modulation coding schemes. So I guess you can call it a race now to see who's going to decode Halo first. And just some other resources I thought were really helpful and helped me get a better grasp on the protocol, and dig into it more. And I will say the specification is free and open by IEEE. Even though it's 4,000 pages, there's only one chapter on Halo, so it's a little bit more digestible than you would think. Yeah, just thank you for attending. I'll stick around for any questions you might have. And if you want to see the Halo devices, like in person, how they work. Otherwise, give me a follow on some of the socials if you want to follow along with my progress. And yeah, I'll take any questions if you have them. Thank you.
We've got time for one quick question. And if no one has one, we can thank our speaker one more time. Next up, we have our lightning talk block. So would the first speaker please come to the front?
All right. Hi, everyone. So I'm Ben, and I'm currently a master's student at the University of Victoria, and I'm just going to give a quick talk on a little SDR project I worked on. Clicker. There. Okay, so first off, the motivation for this, we had a talk earlier about this modular CubeSat radio we're working on, and the main takeaway for this talk is we're basing it off of the open source Hermes-Lite 2 SDR. It's kind of a bit of background. It's an HF SDR, and it's just like a direct digital conversion SDR. And the main limitation we kind of needed to overcome is the transmit bandwidth on it was only 48 kilohertz, and that's just based on like the duck chain in the FPGA, so it can be changed. So that's kind of what I did for this little project. So first off, a little bit of background. Probably can't make out too much of the details on that, but the rough idea of how the existing DSP chain on the Hermes-Lite works is you feed in like a 48 kilosample a second IQ signal, run it through some interpolation filters, run it through a mixer and NCO to like frequency shift it to the output you want, and then that gives you about a 80 megasample a second real signal that you send out to a DAC. So kind of main motivation, probably most of you have an idea of this, behind interpolation is you want to get rid of spectral images, sort of like analogous to aliasing when you're downsampling. So if you just upsample a signal without doing any filtering, you get some spectral images. So you basically need to add a low-pass filter, but you're running these filters at pretty high rates, so you want to do some optimizations. Kind of the first thing you can do is do a polyphase FIR filter, which basically, since after you've interpolated your signal, a bunch of the samples will be zero, so there's not much point in computing the values of them. So the polyphase filter is just kind of a clever way of not doing those zero multiplications. So you can reduce your number of multiplications, and like as a result, the FPGA resources you need by quite a bit doing that, but you still need a fair bit of stuff because if you have a high rate signal, you're still doing a lot of multiplications. So usually you can do the bulk of the interpolation with a CIC filter, which is basically just like a boxcar moving average filter. So an FIR filter where all your coefficients are 1. And that basically means you don't have to do any multiplication, but the cost is like the frequency response is pretty bad. You've kind of got a not very flat passband and wide transition bands, so you need to do some initial filtering. So kind of with that in mind, what we actually did for the Hermes-Lite was, it's fairly easy to adjust the filter rate. You basically just take the CIC filter, reduce how much it's interpolating by, so you get basically a wider bandwidth. So basically reduce the interpolation factor of the CIC filter by 4, and then before that you've got a polyphase FIR filter. And just to kind of keep the hardware resources the same, I reduced the length of that filter just because the FPGA was pretty full. So you end up with like a quarter the filter, a quarter the length as it originally was, which just kind of keeps everything the same in terms of processing requirements. Of course, the cost of that is you have a slightly wider transition band on your low-pass filter, but that worked out fine for us. So kind of one sort of interesting thing you have to do with your FIR filter, it's not just regular low-pass filter. You want to add a bit of droop compensation, since you could see previously the CIC filters have sort of like a sink-like response. So you want to kind of make the passband of your low-pass FIR filter the inverse of it. So you can see on the left there, we've got the passband of just the FIR filter. On the right, it cascaded with the CIC filter, so you've got a flat passband. And then if you kind of implement that all in the FPGA, run a frequency sweep, you can sort of see what happens. So if you just do it on the left without an FIR filter before your CIC interpolation, you can kind of see you get the results you'd expect, a bunch of spectral images and kind of this. You can sort of see the top of the sink-like response of the CIC filter. Then if you add in the FIR filter, get kind of our increased about 200 kilohertz bandwidth, so 4 times the 48 kilohertz, and the spectral images are all suppressed. So that's all I've got, pretty short presentation. There's a GitLab link there that has the modified FPGA gateware and a modified GNU Radio block for it. If anyone uses the Hermes-Lite and wants a wider transition bandwidth, you can do that. So anyways, thanks all for listening. That's all I've got. If there's any quick questions, I can probably answer it. Otherwise, I'll hand it off to the next person.
All right, let's thank our speaker and welcome up our second lightning talk.
Testing. So I believe we moved our lightning talks to make room for lunch. So we're going to go ahead and continue with lunch, and then later today there'll be more lightning talks. Oh, yep. Well.
Guys, I was asked to give you a few quick announcements. At the help desk, there are t-shirts and merch. Grab it, it's limited in quantity. So also there's the Women Plus social lounge in the rotunda over there, and
sound of the beast. That's the sound of the police. That's the sound of the beast.
Can I do this? Hello? Hello? Can you hear me? This is CQ VE3IRR from KX4TH for the Hack the Microphones Challenge.
a strong field, for example, 1.5 Tesla. 2, you have gradient coils, which can create pulsed magnetic field gradients. This is actually how you create the spatial encoding. And 3, you have an RF coil. The RF coil is used both to excite the spin system and also to record the signal. Now, this signal is very weak, and because of that, the entire system, the entire room, sits in an RF cage. So you have a very pristine electromagnetic environment. The problem is that MRI is very slow. Each acquisition takes several minutes. So there's a high risk that the data acquisition gets corrupted by motion. And to give you an idea of what kind of problems this can cause, we're looking at the cross-section of a pineapple here as an experimental setup. The bottom image is the pineapple without motion, and on the top you can see what kind of issues arise. There is blurring, there can be these duplicate ghosts or signal loss. And if you now think about the patient who's alive, there's so much going on. Blood is flowing, the patient is breathing, maybe the patient is shuffling around. So there's a lot going on. And this problem is as old as MRI itself. People came up with many clever strategies to work around it. One of these strategies entails that you use an additional sensor to record the motion state and then correct for it. And for that, you can use ECG or cameras, all kinds of sensors. And we believe that the radar is an interesting option here. Why? Radar is contactless. Radar can go through the skin, unlike optical light, for example. You can change the operational parameters at runtime. And I think this is where the SDR concept comes in, and it's very fast. Now, just to give you a very rough idea of what this could look like, let's say we have a transmit and receive antennas on both sides of the body, and if we illuminate the body with RF power, now a lot of the incident power will be reflected at the air-skin interface, but some of it will penetrate through the skin, depending on frequency, get reflected, bounce around, and will eventually reach the receive antenna. And the important thing is that the scattering of the electromagnetic waves inside the body is modulated by motion. Now, what are we actually doing? I think many of you know that there are different types of radar systems you can implement. Now, to get the ball rolling, we picked something simple, continuous wave Doppler. And this is our setup. On the left-hand side, you see the magnet room. We have 2 radar antennas for transmit and receive, which are connected to the SDR. Now, this is kind of a DIY prototype system, which is independent from the MRI scanner. That means that we have to synchronize MRI and radar in time. And for this purpose, we capture the RF pulses of the MRI scanner on the second channel of the SDR. Here's a flow graph. Now, I know this is small print, but we're going to zoom in on some of these details. At the heart of the matter is the Doppler calculation. This is unmodulated CW Doppler. So we take the reflected wave, we multiply it with the complex conjugate of the forward wave, determine the angle in the complex plane, and that's our Doppler shift. At this point, I want to highlight a presentation by Isabella Lenz and colleagues 2 years ago at GRCon. So if you're curious about Doppler radar for physiological sensing, I highly recommend that. Here's our hardware. We use an ATIS SCR and a Siemens clinical MRI scanner. In the middle, you see the scaffold that we use to mount our antennas. And I guess you can appreciate that we are very close to the subject. That means we operate in the near field of the antennas. That has some implications when it comes to how you calculate the Doppler shift, things like that. The antennas had been designed in-house for a different project. They have ultra-wideband characteristics. They are efficient approximately from 0.5 to 10 gigahertz. So we thought this is an interesting antenna. Let's reuse them for our radar system. And one thing we like to do in MRI research is using phantoms. A phantom is some kind of object that mimics certain parts of human physiology. the reason or the rationality is that it's a lot easier to work with a phantom. You can scan it for hours, you can iterate. These are things you couldn't do in a human volunteer. And here specifically, we have built a phantom that simulates internal body motion in order to develop and evaluate the radar system. This is basically 2 compartments. You have a water tank, and inside the tank is a pendulum that moves back and forth. It's driven by a stepper motor, which is controlled by an Arduino. Here are some first results. What we're doing here is that we put the phantom in the MRI scanner, and we're running a very fast MRI imaging technique. This runs at 11 frames per second. It's so fast because we only acquire a single slice, and we're doing some special tricks to make it fast. And you can see the pendulum moving back and forth. So the position of the pendulum serves as our ground truth to see what the radar is doing. So on the left side, you see the X position of the inner compartment, and on the right side, the Y position. And overlaid in orange is the Doppler signal. Now these curves, they don't match. That's because Doppler encodes velocity primarily, not position. But you can see that we can recover a motion signal from inside this phantom. If we jump to higher frequencies, there's still a signal, but it gets noisier. So you can already appreciate that the optimal parameters are kind of frequency dependent and might need tuning, optimization, depending on the application. Going one step further, now we are acquiring a 3D volume of 40 slices. And this is a continuous acquisition. So the MRI scanner is running nonstop while the phantom is moving, and we record the radar at the same time. And then what we do is we take the raw data out of the scanner, and we, after the fact, we sort every sample according to the motion state as it was determined by the radar. And we use this technique, it's called binning or sorting, to kind of assign motion states to the raw data. And if you compare the top and the bottom picture, you can appreciate that this technique helps to get rid of the motion artifacts in the image. Going one step further, a different approach would be to have the radar running. The radar determines the motion state, and then you have the SDR trigger the scanner. So the MRI data acquisition is only active during a predefined motion state. Once again, we're using our phantom to test this. On the top, you see an image that was acquired without any triggering. And on the bottom, you see the same conditions, but this time we feed trigger pulses from the SDR back to the scanner, which results in a much clearer picture. I'm gonna skip over this in the interest of time. In a nutshell, we put together 2 custom blocks that allow us to feed a motion signal to one of our SDR transmit channels. Then we demodulate this signal. So it's basically AM demodulation in hardware to feed a TTL pulse to the scanner. Switching gears now, looking at volunteers. We're looking at a single slice that goes through the right chest. So at the top of this video, you see the lungs, it's a dark area. And below, the big organ is the liver and other abdominal organs that move up and down as the volunteer is breathing. And on the right side of the slide, you see the movement of the diaphragm, or the movement of the liver. Liver is moving up and down, projected over time. In orange, we overlay the Doppler signal from our radar system. So when we ask the volunteer to take deep breaths, we see a good agreement at 1 gigahertz between the image-based ground truth and the radar. However, when the volunteer is breathing more shallowly, which is kind of natural, you see that noise becomes more dominant. If we then jack up the carrier frequency to 4 gigahertz, once again, we have a very clean signal, even during shallow respiration. And I mean, one interesting thing is that, the so-called noise at 1 gigahertz, we think maybe this is motion from inside the body, maybe the heartbeat, some organs moving back and forth. So one of our aims is to decipher what we're capturing here. Now, as a radiologist, I want to know, can this be useful to actually, help us make better pictures? Here we are acquiring a 3D volume of the liver. Once again, we are doing continuous data acquisition on the MRI side and sort all these MRI samples after the fact based on the radar signal. On the left side is a reconstruction that doesn't use the motion information. On the right side is a motion resolved reconstruction. And if you look at the small vessels in the liver, or if you look at the diaphragm, the contour of the diaphragm, the lower panel, you just see a general boost in image sharpness. What's next? To be honest, we're just getting started. CW Doppler is a very simple technique, so we're excited to tap into more advanced radar schemes, see what's out there in the in the OOT world. Hopefully contribute some of our own custom blocks for medical imaging in the future. Frequency hopping is a topic, more antennas, always interesting. And one thing that we're excited about is to combine the strategy of using real-time, very fast MRI imaging with radar to kind of learn a patient-specific motion model, which can then be used for motion correction. Thank you for your attention.
Okay, thank you very much. Are there any questions? All right, well, thank you very much, Christoph. And the next presentation will be from Chris Stringer, Automating Systems Tests in GNU Radio Companion. Everyone, give him a thanks. Give him a hand. I'm awkward, sorry.
All right. Thank you for coming today. I really appreciate the chance to get to talk here at GNU Radio, GRCon. Been around GNU Radio for a little bit, never had a chance to really go into things, but today we're going to talk about our exploration at New Systems. I'll talk about that in just a moment. Our exploration into GNU Radio, but also we made some tools that we thought would be useful. It's so easy to just dive into code and then forget about the tests, or to want to develop something and to leave the tests on the table, but we didn't want to do that. So we're going to talk about that today. So who am I? So I graduated, let's see, did that, is it the wrong clicker? There we go. All right, so I graduated from Tennessee Technological University just down the road a few years ago. So I've done some software modeling of RF and RF and radars, things like that. I've gotten to work on more Internet of Things, research and development, and some communication systems development. And just kind of a fun tidbit, there's a theater not too far down the road called the Bijou Theater, and I've gotten to perform there with Irish dancing a few times. So if you guys happen to be in town for St. Patrick's Day, or you see Four Leaf Pete, the band around, highly recommend you go check them out. But also, who is New Systems? So we're a small employee-owned business in Huntsville, Alabama. Actually recently employee-owned as of earlier this year, 100%. So it's really excellent. We do a lot of systems engineering. We do some RF analysis and systems analysis. We're currently expanding our expertise in hardware, and that's kind of what led us to GNU Radio and software-defined radios in general. And just real quickly, shameless plug, we are hiring, so we're looking for a variety of things to help us grow our expertise in hardware. So check out newsystems.com/careers. If you're looking for challenging work and a great workplace and a company snack room, we've got that. So today we're going to talk about what do tests look like right now and how do we go about doing some unit tests specifically. Then we're going to go to what we called New Radio. It was just too perfect. We're New Systems, it's GNU Radio, it's New Radio. So too easy for that. We'll go through a step-by-step example to kind of motivate what does this new test workflow look like. Along the way, we'll go through additional uses of what we think our blocks can do. We'll have a bit of a video of a hardware demo at the end, and we'll go through some future work. So first off, I want to mention, what are tests? Why do we need them? And at a very high level, tests are just, we built a thing, we want to make sure that it continues to operate the correct way. We want to make sure it works the first time, and 2 years down the line, it does the exact same thing. There are a couple different kinds of tests that you hear about. Some of them are unit tests, and those are what's available inside GNU Radio right now as GR unit tests. So generally, that's a small block of functionality, a unit, and we want to test that, make sure that it works. The actual size of a unit is subjective, but we just want to make sure that it works very thoroughly. And the idea is that if we check all of these individual units and then put them together into a newer system, then everything, because it was all individually tested, everything will just work. That doesn't happen always. So we have system tests that work on larger collections of these. Now what we're going to be working on today is a flow graph test. It doesn't really fall into one of these into these other categories. It's just a matter of whatever flow graph you make, we're going to test that. And kind of why? Why do I need to do this? And my coworkers laughing in the audience, because people like me love to just write features and write features and write more features. And it's fantastic, so much fun, and just I'll test it later. I'll figure out what happens later. And along the way, I'm like, oh, there's some code. I can optimize that, or I can refactor that, or yeah, I don't like that. I think I'm just going to rewrite it. So I do that the day before a demo because it's not going to change anything. Everything's just going to work. And it doesn't work. It doesn't work at all. And we have to go back and figure out what happened. And all of this could have been solved if we had some sort of test that we could develop quickly. Again, we're trying to do these things very quickly, trying to get them out the door. So it needs to be something that doesn't take a whole lot of time. But we need some kind of a test to make sure that our stuff still works. So that's kind of the reason behind what we're doing. But let's step through one piece at a time. So here we have just one block. If I want to test this block, what do? Well, let's go back to our definition earlier, where we are giving some known inputs. We're expecting a known output. And then you can see over on the right, we have what that might look like inside GR unit test, where we do the exact same thing. We recreate the flow graph, we give it some kind of a known input, we make the blocks, we connect them all together, and we run, and we check the output. Great. So what if we have two? Okay, well, that's still not too hard. Let's just update it with what we've got. We take our known inputs, we put the blocks there in the middle, and we check the outputs. And it gets a little bit longer, but overall, not super complicated. The issue becomes, how do I do the same thing with this flow graph? This is a BPSK receiver. Some of you might recognize it. It's almost the same as one of the examples on the GNU Radio wiki for packet communications. But basically, we're trying to receive a BPSK waveform, depacketize it, and send some data out somewhere. But there's a lot of moving pieces in here. Each of these individually should be unit tested. But as a whole, how do I test this? Well, I mean, there's some ways we could test it. We could do the exact same thing we were doing before. We can take every block, define it inside Python, and run it. Or maybe we could do it kind of the smarter way in this case and just hit the convenient generate button at the top of GNU Radio Companion. And that would give us one time slice of what this flow graph looks like. But what does that look like whenever we make changes? Do we have to re-implement everything? Do we have to manually update things? Really, what it comes down to is, how do I test this? Well, I have a bad day, and it looks like my frowny face is off a little bit, but basically that's a lot of time spent for my day to figure out how do I test this, hook everything up, re-implement the flow graph in Python. And I'd really love if I could just test the flow graph that I made on the other side, the one I made in the first place. So that's where we introduce GNU Radio test. Now, this doesn't replace GR unit test by any means, but it provides kind of a faster way to get into testing, and a way that's a little bit faster in terms of time. It doesn't take as long to make it, but also faster in terms of you don't have to learn this entire other unit test framework. You can use the existing tools inside GNU Radio Companion. So that was our focus. We wanted to focus on making the tests inside GNU Radio Companion and running the tests inside GNU Radio Companion, but also we're not having to re-implement all of our work from one flow graph into the Python version of it. We just use the flow graph that we made. Now, granted, it will be a little more limited than making our own custom tests, but maybe we can combine the two, and we'll talk about that a little bit later. Maybe we can combine the best of both worlds. So ultimately, though, I have to be realistic. Whenever I go from writing these tests, it doesn't suddenly make tests super fun and I'm excited about doing them. It takes me from being very upset about writing these unit tests to them being tolerable And maybe that's all the difference. Maybe if I'm okay with writing tests pretty quickly, the test that exists is better than no tests. So let's go back to that example that we did earlier. Again, this is a BPSK packet receiver. And as we move along, we'll start adding blocks to this, and you can follow along in the top right corner and see what we've added. And also, I want to say a very special thank you to Barry Duggan, who has made so much work on the wiki that really helped us get started into GNU Radio. So really appreciate you. So first off, how do we test it? Well, let's take the first part. We said that we need to define some inputs and then define some outputs, and we want, for a given set of inputs, we want the outputs to work. So what do we do with that? Well, there's a couple things we could do. Sometimes maybe we don't want, sometimes we just want to use an SDR. That'd be great. But the problem is they're not repeatable. It's by default noisy. And that means if we run the same test 10 times, we will get probably 10 different results. I guess I can't rule out that it could randomly be the same, but we'll probably get different results. Or we could generate a perfect signal and pass that in. There's some benefits to that, but that still takes kind of a while. So how about we just take a file and we just record some input from the SDR or from whatever our generator is, save it to a file, and then run that. So that's what we're going to use for this particular example. That's not something new, but the new part is that if I want to do that automatically, let's say I want to run my flow graph normally with the SDR while I'm developing it, but whenever I start running my unit tests, then maybe I want to swap over to that file input. And that's where we start entering in the new radio test blocks, where we have the test enable and disable blocks. Basically, we'll get into more of the mechanism of how this works a little bit later. But whenever I run for tests and not just run for developing, then I can use this block to enable certain blocks, just like going over to the block, right-clicking and saying enable or disable, or using the hotkeys. I can enable and disable them there. They get moved out of the flow graph. And in this case, I'm actually using it to swap between using the radio and using the file source. So whenever I'm developing my test, I can just say, hey, whenever I'm doing my test, give me the file. That's great. So now, what do we do? There we go. So now, let's go on through the flow graph, just to the next stage. So like I said, this is a BPSK receiver. One thing about BPSK and any of the phase shift keying modulations is that they all lie on the unit circle. They should have an amplitude of about 1. So the symbol sync block that we had earlier, it relies on that, at least for this particular mechanism. And maybe we want to make a quick test to verify that our gain control, that's automatic, helps move it up, even if it's a very weak signal, help move the signal up to where we expect it to be. Maybe I want to make sure that the AGC is actually moving our signal level up to where I want it to be. So we made this block, this stream watch. So all it does is it sits and watches an input stream, as you might imagine from the name. And then it allows you to, anytime your signal goes outside of whatever bounds you give it, so it could be an upper bound, lower bound, or both, or maybe it's just you don't ever want it to cross a threshold. Anytime it fails that test, it will start writing outputs to a file, or at least tell you that there was an issue inside the console. This is a way that you can very quickly check instead of trying to catch it on a graph that you're using. It's a way that you can see very quickly if it fails, and something that we can kind of automate as a test. One thing I also want to say, we could also use this to measure like the settling time of the AGC, or we could use it to just, in general, measure signal level. Let's go ahead and move on. So after that, we've got our signal. We pass it through our clock synchronization. Now, whenever you have, I said earlier, this is a BPSK signal. I used a QPSK graph here, but the example is the same. So you can see on the bottom right, it's really easy to tell whenever you've got a good clock sync. You have those 4 nice constellation points there. And you can tell when it's really bad, or you just have just about nothing in there. That's really easy for us to see with our eyes. If we wanted to write a script to analyze that, we could absolutely do that. It wouldn't take tremendously a long amount of time, but it's so much faster to just take a picture of it. So that was kind of the idea behind the screenshot block, is that just automatically, one time and then multiple times if you would like it to, you can take some screenshots just of your screen. Wow, it's an amazing concept. But it allows you to look at these plots in particular, and you can just visually see this worked or this didn't work. There are some other uses that we thought about that maybe you could use, including if you have a hardware status monitor. We'll get to why we were developing all of these in a little bit. But if you have some kind of a hardware status on the side, like another configuration menu, you can record that as well as your data. So you can record what happened. And also, if you would like, one thing I thought of this morning is you could log user inputs. I don't know how many of you have messed around with a GNU Radio flow graph and moved some QT ranges and decided, wow, these are the exact settings I need, and then you close it and then you forget what you had. And you have to try to recreate it. So an idea would be, what if we just take screenshots every couple seconds, and then whatever that setting happens to be, it'll be permanently recorded, and we can go check that out later. So next up, with all of these things, even screenshots that we're able to do, sometimes you just need more. You need a little bit more advanced functionality. So let's just write a script for that. That's kind of getting away from what we wanted to do with GNU Radio test, but sometimes a script helps. So you're able to just hook this up, and then at the beginning or end of a flow graph, whenever you execute it, you're able to just run some other script or some other command. It's not super revolutionary, but it is very helpful for kicking off additional analysis or for doing some hardware setup. And we used a hardware channel emulator, and we used this kind of functionality to configure it before each run. We were able to run multiple times. And so we'll get to that a little bit later as well. But there's a variety of things you can do here. The sky's the limit, but that is not the focus of what we're working on with this. We wanted to keep everything, if possible, inside GRC. So let's go back to these other parts. Now, I just talked about, we had a hardware channel emulator, and we used that last block, the run command block, to help configure it. At the start of every flow graph, we told it to change to a different set of parameters. But how did we do that? Well, that's where we introduced this variable change block. It's not super crazy what it does. Every time we run a test, it will take the next item in this list. In this case, I say it starts at 0 and goes to 10. It's just like a regular range. So it'll go 0 to 9. And then every time it makes it'll make a new flow graph from each of those, and then it will set that variable to 0. And then next time it runs, it'll set it to 1. Next time it runs, it sets it equal to 2. Or you can set that equal to, I want to use QPSK this time. I want to use BPSK the next time. Whatever it happens to be, you're able to repeat a test if you want to, either using a different number or the same number each time. But that's really where the automated test portion comes. We're not just testing one thing. We want to test a variety of options. We want to test different features, or in this case, maybe we want to test multiple files. And so we can change the file every single time we run, just a different recording of the SDR. We can check different signal levels, different channels, all of those things. Now we need to kind of put everything together, because we could run the test, we could do whatever we want, but we want to make a descriptive name for it. And we'll see, that'll be important. Whenever we run these tests and we save them, we use this name to kind of help you figure out which one is which. And there's a little bit more features that we can do. These help group all of the other blocks that we've developed into, well, by this test. And so you're able to, instead of manually enabling and disabling all of the different test features, you're able to just use these to kind of group them together and pick which ones run when. So now we get to the automated portion of the automated test. So we've just developed our flow graph, and we put things together, and now we've put in all of these other test blocks, and we could just hit run and it would work. It would be fine. But maybe I want to run, like with that last one, maybe I want to change that variable over the course of the run. So that's where we have the test run tests. And there's a lot kind of packed into this one block. But essentially, it will take all of those other settings that we've configured. It will generate a new flow graph from each one, and then drop it into its own folder, and then run it in place. So all of the outputs, so the screenshots, and in this case, we have the console being logged as well. Anything like that gets saved locally to that test. That opens up a lot of doors where we're able to run a variety of tests. We're able to, say, tune a variable, or we're able to test out, like I said earlier, different channel conditions, and we're able to see, without having to manually change those each time and click play and then stop and then play and stop, it will run all of those for us, and then we can go right to that folder and see what the output was. Yeah, so I think it's been pretty useful. It's also kind of helpful that it allows you to use embedded blocks because it's not just it's just using the exact same process as GNU Radio would. It drops it into that folder, runs grcc to compile it into Python code, and then it just executes that. So something that was also hidden in that block that I didn't mention is that sometimes we just run the the block or the flow graph to stop after some amount of time. If I told it to run some automated tests and go, and I wanted you to run 10 times, it would run one time forever. So I need to tell it to stop. So what this does, it's kind of self-explanatory. It just stops the test. And this is wrapped up inside that last test, or inside that last block that we used. So overall, what did we change? We just tested that whole flow graph for a variety of things. What did we add? There's a lot of colors on here. There's a couple blocks that we added. But what I want to highlight is that part where we added 6 tests, 6 features for it. But each one of them only took 1 or 2 blocks for one. And some of those are just type conversion. So we were able to add quite a bit with very little work. And so that lowers that barrier to entry, that lowers that time barrier to maybe I would actually write a test for this. And I do want to say that most of those were written in GRC, or were implemented using GRC only, and not having to go to an external editor and write unit tests or external code. So there was one more feature that I kind of touched on, but didn't really go that far into, and that is that define test. Whenever you make that name, you can actually associate each of the different features, all the different test pieces, to a specific test name, just using a regular expression. So if I want to enable the SDR for certain tests, and I want to enable the file input for certain tests, I can use this regular expression, and all of the other ones will be automatically enabled and disabled per run, and they'll be attached to those names. And whenever it runs, it will take each of those names, drop it into its own individual output, and that way you'd be able to say, I want to go look at what happens when I change the channel model, go to that exact test, and then you won't have to worry about everything colliding with each other. All of it will just run as you would expect. So real quick, here's a list of features. I wanted to call out some of these don't require that you are using that run test block, and some other ones do. The run test block kicks off some other Python scripts, and it starts parsing the GRC file and doing a lot of stuff under the hood. But some of these features are just helpful, like running a command or telling the flow graph to stop at a certain amount of time. Some of those work just without any of that other process. So here, this was kind of the whole reason we did all of this. We were trying to test what happens whenever we have some communications waveforms, and we try them out with different channel conditions. We're trying to do very long-range communications in pretty harsh conditions, just generally being variable. And so one of the best ways that we need to do that was to get a hardware channel emulator and to use some software-defined radios. That way we could show not only ourselves, but show our customers that we've implemented things like fading, things multipath, all that kind of stuff. We're able to test all of that. And we didn't necessarily want to implement all of that. There's a lot of excellent hardware that does that for us. But we want to be able to run some automated tests to start stimulating that and change the channel for us, help us to test out all these different conditions in a way that that's easy, a way that we don't have to tell it to go every single time, and we don't have to spend 10 minutes setting the channel emulator by ourselves each time. So that's kind of why we did this. So we used an EDIS B210 and a TASC 4500 Flex channel emulator, this time using a QPSK communication. And what we were testing for, at least in this particular video that we'll get to in a moment, is that we just want to test that our clock was synchronized, and therefore maybe we could get some data. We'd also be able to tell a little bit about the channel, how good it was, or maybe we should just give up on that particular channel and try something else. So we have a quick video. I don't know if you're able to play that. You can see the TASC 4500 Flex channel model on the bottom there. And then this is a little bit earlier in the process. So we didn't have the run tests where you're able to just click play inside GNU Radio Companion. Do you know if you're able to play the video? It should be embedded in the slide. Thank you. So it'll be pretty quick. Here I'm just kicking it off. Like I said, this is a little bit older. But here we can see that we have a QPSK waveform. We set up our channel to something that's nice and friendly. And so we're able to get very good clock synchronization there. We're going to flip over to something a little bit harder. And there you can see it starts to spread a little bit more. Again, this is going through a software-defined radio and through the hardware channel emulator. And then we have one more that we'll go to. And this one, I think it looks pretty funny. It's a big X. It means maybe this is a bit of a harder channel. I'm impressed that it's able to resolve the 4 different sides of it. But yeah, overall, we're able to see here, using the same framework, we were able to develop some tests using our flow graph and then run them on some hardware. That was really the whole point for doing this. And let's see, there we go. Yeah, so just a quick review. So what did we make? Well, it's a test framework inside GNU Radio Companion. It supports some automation. I'm not going to pretend like it'll make all of the job easier, but it means that we don't have to leave GNU Radio Companion to implement some tests. And really, if you get creative with some of those other blocks, some of those tools, then you can implement quite a few. One of the big features of it is that it lowers the time that it takes to generate these tests. You can add 1 or 2 blocks and test some things. And it also lowers the skill requirement. You don't have to go learn GR unit tests or any of those other frameworks, and you don't have to leave GNU Radio Companion to start developing these tests. So especially for me, some of my coworkers are not as familiar with GNU Radio and Python, so I'm able to help them get ready for tests, make their own tests. It also reduces the code duplication that you have. Instead of taking your flow graph and re-implementing it in Python, and then anytime you make a change, going back and updating it again, it just does everything on the same flow graph. And we kind of envision this to be a complement to GR unit test as much as you can. So if there's a quick test that you can make, then hopefully that these tools help you out. If there's something really specific that you need, maybe the unit tests are a better way to do it. But we can test much larger sections. Now, where can we find it? So we have a GitHub that we set up specifically for this, which is super cool. Being able to open source this code. And hopefully it is helpful to you guys. I'd love for your feedback on it, or just what can we do with it. And finally, we have some future work. We weren't able to implement everything that we wanted to. One of them is that right now, whenever you change a variable, it will change it once and then run the entire flow graph, and then it won't change it again until the next time. We'd love to be able to automate, say, some user inputs on the Qt widget. We'd also love to be able to collate some of the outputs and put them together into kind of an automated report. Not necessarily a one-size-fits-all thing, but it would be very useful. So with that, thank you. Thank you for listening to me talk about automated tests. But do we have any questions?
Any questions for Chris? Okay, I'll ask one. How do you test it?
Sorry, what?
How do you test GNU Radio test?
How do I test the tests? Oh man, that's very meta. So right now, it's pretty ironic we don't have the tests in there, but the tests have been me just clicking it and going. So I clearly need another tool that will help motivate me to test the new test tools. But I appreciate that.
I had to ask.
I got a question.
All right, thank you.
Is there any possible way we could have this run on the examples within GNU Radio core as part of GNU Radio CI? Or would someone else outside the company have to come along and do that?
I'm not sure. Can we talk after this?
Yeah, definitely. Yeah, I think there's a lot of potential.
Yeah, I'm fairly new to the GNU Radio scene, so you'll find that a lot of these things, I might need a little bit more time to talk about it. But
And
yeah.
then quick follow-up. I'm curious, is there anything like PyTest's approx function where you check if the output is roughly equal to what it should be?
Not just yet, no.
Okay,
no,
yeah,
but that was something that I went in planning to do, just to even take one of those vector syncs and be able to check directly there using the same framework. But no, we weren't able to implement that.
Yeah, that will probably be really useful. I find myself using that a bunch for RF, end-to-end testing kind of stuff. Cool. Yeah, that's all I had. Any last questions?
No more questions? All right. Well, thank you very much, Chris. Awesome
All right,
topic.
thank you.
So the next presenter is Ruben Thill. Are you ready? Awesome. All right. So Ruben will be presenting OFDM-based radar sensing using compressed sensing.
So good morning, good afternoon, everyone. So my name is Ruben Thill. I work with the Fraunhofer FHR in Wartberg. This is close to Bonn in Germany, and I'm going to present some work my colleague Andreas Bartelt and I did in the area of joint communication and sensing and how to add a compressed sensing to it. So, okay, other clicker then. Yes, so to our background, so we are institute mainly focused on radar research, and In radar, for instance, especially in linear frequency modulated continuous wave, you have the nice advantage that you can create chirps in the analog domain, send them out, and have a very high bandwidth, which gives you a very good range resolution, and then you receive that sample, that signal back, do stretch processing, and you only have to sample the intermediate frequency to get the entire signal and the full resolution. And you can do some nice stuff with this, like for instance, SAR imaging, like in the lower picture, and 2, there's a sample image. But you not always want to deploy these kind of radar systems, or sometimes you don't have the resources, especially frequency is becoming a scarce resource. So there's the thing called joint communication and sensing, which is not new, but it's kind of new to us. And the concept is that you use, for our case, we do communication-centric joint communication and sensing, so we add some sensing capabilities to communication waveforms. In our case, multi-carrier waveforms, we could use anything like OTFS, but in this particular case, we use OFDM. And we have a monostatic setup as a beginning, and I linked some related work below, but I'm not going into that. So coming to our signal model, so we have transceiver A and a transceiver B, and transceiver A tries to communicate with B, and in the channel there are like 4 scatterers, and let's assume transceiver A also has an RX channel, and it also tries to receive its own backscattered TX signal, and that would be like just the TX signal convolved with the channel impulse response, where I just plotted the magnitude spectrums, like a sample of how it could look below. You can model it in the time domain, but also you can just take the impulse response to frequency domain and model your receive signal in the frequency domain directly. So we basically have, as a receive signal, the send signal, which has some phase variations due to the time delay introduced by the channel. So out of this receive signal, we can create a compressed sensing problem. So we have our received vector Y, and then we have a sensing matrix, which consists of 3 components. Matrix P, which is our selection matrix, where we select our subcarriers we want to send on. Then we have our signal matrix S, where our baseband signal is in, and then we have the matrix B, which is a Fourier-like basic matrix, where we also have the phase delay put into, which is introduced by the respective subcarrier. And then we have the vector X, which is our scenario we want to see. So those are our range samples, basically. It's a grid, and we just assume that we only have a few non-zero components there, so only a few scatterers in there, and the rest of the signal is then buried in noise. And then we have an underdetermined system, which we can solve with compressed sensing. In this particular case, we have an OMP-based method like orthogonal matching per seat. And to give you an intuition of what we want to do, so like as I already said initially, our resolution is related to the bandwidth we have. So the higher the bandwidth, the better the resolution. But in communication, you don't want to use the entire bandwidth just to do some sensing, because you would be denying the spectrum to other users within there which also want to use it. So our scheme is to randomly select carriers across the available frame and synthesize that together so we get the full resolution we would have using the entire bandwidth, but not actually using the entire spectrum. So as a starting point, we did a simulation, and in the simulation we kind of used the same parameters as we later used
with the test setup. So we had a sampling frequency of 200 megasamples, center frequency of 6 gigahertz, and a cyclic prefix of 128 samples. And we assumed that all the backscattered signal from the scatterers within our scenario are within that time period of the cyclic prefix to maintain the orthogonality of the OFDM system. And we have an OFDM system in this simulation with 512 subcarriers, from which we can use 400, and the other ones we leave empty. And out of those 400, we selected 30 active carriers, and we had a sparse scenario with like 2 strong scatterers in the scenario, and we assumed that the rest of the signal is buried in noise. And as you can see, this OMP method already works in the simulation, but we want to bring it to the real world. And for the real world, we need a kind of OFDM system first. I know there is several out-of-tree models like the OFDM radar module, but I decided to implement it myself again, so I can tinker with this system and do what I want. So the OFDM system is very simple. So you have an input stream of symbols, you parallelize them, and then you allocate them to the selected subcarriers you want to use. And then you do the IFFT across those subcarriers, and you get your time domain signal. You add a cyclic prefix to this and serialize the signal and send it out into the channel where it's then prone to multipath and noise, and you receive it back at your RX. You parallelize it, you get rid of the cyclic prefix, and you convert it to Fourier domain. And nice feature which is like presented in this relatively old paper from Sturm et al. That you just can do the convolution of your received signal with a send signal, and you get back your range positions. And the nice thing is that OFDM is already a frequency domain modulated system, so we can also do the correlation in the frequency domain by just dividing the initially sent symbols of the received signal. So, this OFDM system I built around the SDR, so I can really stream the samples into real world. And I just did a very basic GNU Radio flow graph with a USRP source and a USRP sink. And I had a vector source and a vector sink, unlike here in this flow graph, but you can also use the vector source and sink, where I then streamed into the data from my OFDM system. And what I didn't know initially is that the TX and the RX are not necessarily in sync. So I added a second RX stream to circumvene that fact and get back my timing delay. So the idea of that, what I did is pictured here. So I send out a chirp via the TX of the USRP. So I'm using both daughter boards in my X310, and I send back the signal to the RX1, and I do the convolution, and then I get a timing. And if I do the same on the second channel, and I have the same cable lengths, L1 and L2, on both sides of the power divider, then I can verify that the RX1 and RX2 are actually in time sync when I get the same time delay for both. And I did, so I can use this as a reference. So I just, on one channel, I directly stream in the TX to the RX1, and I use the second RX2 to recover the signal from my scenario. So here's a small setup in my office. So I had the USRP X310 there, and then I sent the signal to the corner reflector and then recovered it back. But actually, this was taken, this picture, before I knew that TX and RX are actually not in sync. So later on for the measurements, I used the cable because I already had returned back that corner reflector to a colleague. And so here are the results of the measurements over that delay line I then used. These are basically the same parameters as before. I
have a sampling frequency of 200 megasamples, 6 gigahertz center frequency, 128 sample cyclic prefix, and 512 subcarriers, from which only 30 were active. And the sparsity, since I only had one delay line, was 1 in this case, but it still got back the signal correctly. So the traditional OFDM radar aligns pretty well with the OMP method. And as a future work, I really would like to use the RF knock signals or time signals to convene this 2 RX channel setup I have, so to synchronize TX and RX. As far as I understood, I could do this using RF knock if I use the replay block and then implement everything with RF knock. That also would give me the possibility to offload some processing to the FPGA and make it real-time capable. So I was really glad to hear that Martin Brown announced that the usage of RF knock is going to be simplified in the future with UHD 4.7. I really look forward to look into this and to make this working. And additionally, like on the long term, I really would like to do use this joint communication system to integrate it into something like SAR imaging. And as a last bullet point, I also have the 410 in my office, but I didn't get it to work at full sample rate yet. But as soon as I do, I will enjoy the enhanced resolution. So thank you for listening, and if there are any questions, I'm happy to answer now or via email later.
Thank you, Ruben. Any questions?
Thank you. Great talk. I was just curious if any of your code for this was open sourced.
No, so far we didn't publish it open source. So you can see the algorithm in the paper, which is linked in the slides, but then you could redo that algorithm in Python. It's not so complicated, but maybe we can also talk later.
Thank you.
Fine.
Anyone else? Okay, thank you, Ruben. Okay, the next presenter is Davide Cavion. Hope I pronounced that correctly. Design your own SDR in 101 easy steps.
Yeah, it's actually 53 steps, sorry. So this is a very different talk than what you are used to be hearing about, I think, because it's not extremely technical, so you might not learn too much from it, but I truly hope it's interesting. So how do you design a completely new RW platform? And you need to start from a new chip, in this case, the NXP9310. It's basically designed to be a software-defined radio platform. It's incredible. It has 160 megasamples per second ADC, 8 DUCs, DSP, and PCI. The only issue is that you cannot buy it. So how do you design a product around something you cannot buy? And let me introduce you to the idea of access agreements. So basically, you are a hardware manufacturer, like a chip vendor, and you want to limit the number of customers that use your chips. Basically, you ask them to purchase a house from you before they even have access to the reference design. And of course, I couldn't afford it, so what do? I simply spent 6 weeks being very nice to them, and it worked. So I got access for free, and I was the first person ever to get access to this chip for free, so that was incredible. And you're beginning to think, oh, we might be up to something here. This might be actually be serious, right? So we have a chip. What do? We go to a conference, right? We was talking people to a conference. Sounds familiar? Probably the best thing I've done for that conference was sending a selfie of me outside of the conference to my field application engineer. And ever since then, we've been best friends. So, send selfies of yourself to your field application engineer. It might work out. Now, lead times. The problem and the beauty of manufacturing is lead time, right? So basically, you have to buy your chips almost a year out for a product you haven't developed yet. Just based on an idea and a concept and basically a sketch on a piece of paper. Does it work? Can you actually do it? And where do you find the money from it? So how do you raise money? Do you go to an investor and tell them, oh, I'm going to be building defendable IP on top of a 9310. Please give me money to buy the chips. Doesn't work. Bad idea. But plot twist, NXP actually wanted to build a software-defined radio. NXP knew that they had this incredible and beautiful product. And rather than say, give me the project to an internal team that might have been, say, extremely busy, they gave it to me. So, how the flip tables, right? You go from needing to pay NXP to NXP paying you. That was incredible. The idea with this chip is that it's an IQ mixer. So, it's an IQ baseband interface. So you need to find an IQ mixer. And I got introduced to Actric Semiconductors based off San Jose. And the chip on paper was absolutely perfect. We would have built the best software-defined radio ever, up to 7.2 gigahertz, etc. Of course, they knew that NXP usually charges an access fee for their chips, so they wanted a share of it. So you say no because it's too expensive. And the second option is apparently the line chip, also has an IQ interface. And this works great, out of the box, no headaches. It's great. So that was daughter board number 2. And then you start lining up the suppliers, right? So apparently the moment you tell people you're going to be building 1,000 or something, people are actually interested in talking to you. You sign NDAs with NXP, Skyworks, Granita, and you buy the chip stuff out of China. 3 people visiting your home in Italy just because you want to buy chips is weird. Crowd supply. They usually use crowd supply. I mean, that's how you do the project, right? The issue is that they take 15% and then they say, constrain you on your supply chain if you have any issues. So I decided to shoot myself in the foot and went my own way. Following step, of course, is advertisement, right? So you steal Luigi's meme, this beautiful, absolutely incredible meme, basically describing how every single software-defined radio out there is based on the 9361, and exploit it to create something new. And we managed to get to the first page of Hacker News, so that was great. 1,000 people joined the mailing list. It's promising, right? So this is what happened first when the Discord server was still empty, and we only had one user on it. Basically, the user joins and wonders, why is the server so empty? I mean, is this a scam? And no, it's just, you're the first one. Welcome. User 1 has left the chat. March 2023, we're ready for manufacturing. Everything is looking good to go. Gearbells are ready to pull the trigger for a small demo batch. And then NXP wants to add something special. It is so special, it's so secure that it always delays everything. So it's a secure element chip. We only use it for the eSIM. It's inside the iPhone 15. And NXP themselves, like the people I was talking to, wanted to get me access to the chip. But it took like almost a month to do it because it's behind so much paperwork. And of course, it's usually sold by the millions. So if you want to buy 100 of them, then a poor person needs to hand program them in a lab, and it's like 10 different steps. So an absolute nightmare to work with, but we managed to do it. PCB manufacturing, if you know anything about it, the idea is you either go to China or you don't have a product pretty much. The problem with going to China, of course, is that baking to the price of manufacturing is the idea they're gonna copy the design. So if you're okay with that, go to China. If you're not okay with that, prepare your teeth for a PCB manufacturer like in Europe. I didn't want to go to China, so I tried Europe. Terrible idea. So they delivered a PCB that had a power plane short to the ground. And what do you mean you have a power plane short to the ground? How is that even possible? So you can see here there is a ground via on a power plane, and the gearbox is on the right. The actual copper is on the left. Mind-blowing. So how do you fix it? And the answer, of course, is you find a local CNC shop and you drill it out. So yeah, good luck with that. But it worked. Got extremely lucky. It worked. And that's just a picture of the tornado head at the assembly house because, I love SMD assembly, I guess. So side effect of designing some new hardware is that you get to design the PCBs, and if you have a lot of time to design the PCBs, then people like them just because they're nice to look at. Apparently, say, golden-plated copper is actually very cool to look at. So like, for example, a NARS professor from some kind of US university retweets it, only because it's beautiful to look at. The question is, I'm sorry, does it work as well as it looks? And the answer is unfortunately no. So apparently, he was the first person to ever pair the Granita chip with the 9310, and an internal design from Actric, I think, never actually worked. So no pressure. But eventually, I brute forced the SPI address. I know it doesn't make any sense, but I brute forced the SPI address of it, and I managed to get it working. People are shocked. So recap: it's August 2023. The motherboard with 100 vias is working. The Lime daughter board is working. The Granita daughter board does something, and the software is missing in action. So can I actually do the software in 2 weeks and come to GNU Radio last conference and show it? And it was the worst 2 weeks of the year, but I managed to do it. Met plenty of interesting people. People were actually excited about it, I think. And yeah, I mean, it's all looking good. So we opened pre-orders. We sell about 100 units, like 50K in sales. Like 30-something% profit. You do the math, it's not sustainable, but it's fine. Shipped in 6 months, looking good, right? So here's why I rant about the Granita issues. Number one is that the datasheet says that it goes up to 7.2 gigahertz, but it doesn't. It only does a 6.3 in practice, unfortunately. Issue number two is that to go between 5 and 6.3 gigahertz, you have to overclock your VCO, as in you don't have to provide it 0.9 volts. It has to be like 1.4 volts. And of course, that wasn't documented anywhere. Nobody told me about it. If you don't do it, only either I or Q of your phases are working. So, and you get plenty of noise. So absolutely incredible. And of course, I was promised continuous frequency coverage, which never really happened. I'm actually okay with the frequency coverage. I think it's acceptable. Like there is a slot around the GPS L1 frequency, which basically nobody uses. And you can see the progression over time for different software releases. So the dark, I have to move on, sorry. The Granita is also an harmonic generator. So 1/4 of your input clock is going to show up everywhere if you increase the low noise amplifier inside the chip high enough. So is it a PCB problem? Is it a U problem? What's going on there? And of course, a lot of finger pointing, and eventually we find out it's actually a clock generator inside the chip, and there is nothing you can do about it. Something absolutely incredible is that one of the phases of the IQ channel is off by 45 degrees. So, if most QEC cores don't really work well with a 45 degrees error, so that's another incredible problem. Not all of them, like some of the receive paths are actually okay. And of course, the low pass filter doesn't work. As in, you set it to 20 megahertz, and the minus 3 dB bandwidth is 80 megahertz. Even though the datasheet, which is in the bottom left here, specifies, 40 plus dBs of rejection. So I guess that's the foreshadowing, right? So back in March 2023, they asked me to swap the polarity on some IQ pairs, and I'm like, okay, cool. And I was very excited about it back then, but I was wrong. So the ADC inside the 9310 is an interleaved ADC. What does that mean? There are 4 ADCs inside. Unfortunately, there might be some, I guess, DC offset, and it shows up as a FS/4 noise. And again, nobody knows where it's coming from. Is it my board? Is it NXP's design? Is it the chip? What is it? Eventually, we managed to reproduce it on a reference design from NXP, so we finally figure out that this is a problem the IP core has. And the IP vendor doesn't have a fix. NXP doesn't have a fix. Nobody knows how to fix this, unfortunately. Eventually, the board starts shipping, and a guy named Sultan is actually very, very disappointed by this FS/4 problem. So what does it do? He actually just fixes it. So, bother the right person, and apparently magic things can happen. I was blown away by it. We actually have a proper ADC now. This is some data about PCI speed. We can now do 620 megabytes a second from IMX to 9310. Full-duplex is a work in progress. This is kind of interesting. So if you are a RFIC manufacturer and you have a broken low-pass filter, what do? You tell your customer to add a low-pass filter to the IQ lines, right? But do you think it's going to be Butterworth or Shell-Batsby, whatever? And yeah, it wasn't Butterworth. So you can see the effect of phase shift over frequency on the, say, above row. And then the moment you remove that, it becomes perfect. And of course, it's very, very difficult to correct for the result on the first row if you don't have a lot of, say, taps in your QAC. So big problem. This is, I guess, is a different story about how you can hop on a call with a, say, big IC manufacturer, and they can promise you something, and they send you a quotation for something that's completely different. But it was all good because the 5510 was a much better device. So 5510, can you do arbitrary clocks with it? Unfortunately, no, because we haven't cracked the CRC code of it yet. We tried, but maybe eventually we will. So we just have a very long list of possible, say, DCS sampling frequencies, and you can select from any one of them. So what kind of applications can you build on top of this hardware, right? Like, can you build a 5G UE stack? And the answer is yes. So you need microsecond accuracy. People were very skeptical this was going to work, but I designed it to work, so I knew it was going to work. I was very happy about it. This is just a small fix. Another PCB manufacturing issue is when your PCB manufacturer gives you a solder mask that is way too thick. Of course, that results in extra solder deposition. And if you have LGA chips, like small switches, and you have like 70 of them in a single board, and 30% of them look like this, then it's a nightmare. It's also especially funny when your PCB manufacturer delivers PCBs with varying layers of solder max thickness in the same box. So the first batch goes through just fine, and then you reach the bottom of the box, and everything becomes absolutely terrible. And this is the rework we had to do. Basically, every single yellow or purple line spot here is a reworked component. And some of those components might say kind of fail, but not really fail, so you need to test everything. It's a nightmare. So yeah, we had to calibrate every single board before shipping. Of course, you come up with a very, very convoluted testing plan, and then you just narrow it down because otherwise you're going to go insane. This is an example for the line board. This is 25 different line boards. It's all fairly close together, and I think it looks great. Again, about the UE stack. So this was a Computex. We have a fully self-contained 5G UE running inside the hardware. And I thought that was, I never thought that was going to happen. It was great. We got reviewed on RTL STR. The only issue is that the hardware is so complicated that not even this extremely geeky person understands it, right? Like, for example, they had issues with low frequencies not coming through as they would expect us, I would want them to. But the problem is that the, say, filter bank in front of the receiver was filtering them out because the frequency was selected wrong. So evacuate is something that's too complicated, question mark. Eventually, we get a nice working daughter board. This is from Metanoia. Does 2.5 to 5 gigahertz, and DVM is 3.7 on QPSK. This is just another example of how terrible manufacturing is. Like, you can trust the design from a proper, respectable SMA connector vendor, and it doesn't fit what you actually get delivered at all. So measure everything, test everything, and yeah, make sure you do that. So you have all of that. What do? You reduce the size by 95%, and you create a system on a module. And that's coming off the oven this week. And that's just a couple of pictures of, assembled board, assembled heat sinks, boxes, and all of the components I had to buy a year beforehand so that I knew I could make the boards. That's it. Thank you.
Thank you, David. Does anybody have any questions?
Thank you.
All right, thanks. Up next is Marc Lichtman to give us an update on IQEngine.
Okay. So, my name is Marc, and I will be giving a brief intro to IQEngine for those who haven't heard of it, as well as a few demos and an update as far as what the project's been up to over this last year. So, to get started with, IQEngine, it's a browser-based app for managing your RF recordings, including sharing them, analyzing them in certain ways, processing them, and it's all in your browser. So it's extremely accessible. There's nothing to install as far as using it in the most basic way. And it's easy for me to share IQEngine with other people because I just point them to a website, which I'll show you in a second. It's entirely built on top of SigMF. It started a few years ago, and the idea was to make the ultimate SigMF tool and make it browser-based, mainly for accessibility. Now, IQEngine.org is a public instance of the tool. It's what we use to show it off, as well as use it to share recordings. And I guess other people use it to share their recordings with the world. And hopefully one day it'll also be used to share RF functions, I'll call it. It's really broad, any kind of RF functionality that you might run on a set of samples. You could show off and kind of demonstrate as a plugin to IQEngine. And not only, so IQEngine.org, it's kind of like the public instance of the tool, but there's a lot of functionality at IQEngine.org for you to analyze your own local recordings. So even if you have a bunch of local, like IQ files, you can use IQEngine.org if you don't want to set up everything yourself. And kind of like you'd open it in Spectrum. It's a spectrogram-based viewer. So let me dive into sort of the basics of what the tool is. I'll try to hit all the specifics I wanted to here. Okay, so IQEngine.org, first off, I wasn't sure what the Wi-Fi would be like. Let me zoom way in. This is IQEngine.org after you go past the landing page. And you can see the Wi-Fi AH from the talk this morning. From Sam's talk, and then the GRCon CTF recordings are all here. So if you're someone who's not into the CTF, but you're kind of curious, like you just want a quick glimpse at it, like these represent most of the challenges in the form of a signal recording, and some of them look kind of interesting here, right? So, and the idea with each one is this lists all the recordings in that like bucket, but you can click on one of them, and you're brought to a spectrogram-based viewer. And the way it works, well, I'm on the Wi-Fi one. Let me switch to my local instance. Okay, so I'm running IQEngine on my laptop as well. And this will be a lot faster. So you can click one of the recordings, and you're brought to a spectrogram-based interface. So on the right, we have a mini-map, kind of like in VS Code, where it's the whole recording. This is just a few FM signals that stay relatively static. And the way it works is it's only downloading the samples you're looking at. So if I jump into the middle of the recording, it's going to download those samples. It's indicated on the right. This little gray box shows you what's been cached in your browser. And then everything else is done client-side in your browser, like the FFTs. And if you add any filters, there's a lot of different options. That's all client-side, luckily. And okay, so I said it was built on top of SigMF, but you haven't really seen anything too specific to SigMF yet. Let me jump over to a recording that has some annotations, like this guy here. So annotations in SigMF are used to draw a bounding box in time and frequency around anything of interest. So in this example, you know, there was some sort of classifier run on a portion of the signal, and they're using SigMF annotations to represent the classification results. You can have as many as you want. They also show up on the mini-map as little white boxes. And then within IQEngine, you can actually add an annotation manually. Most people, you know, have tooling around that, but if you maybe, there was something here that was missed, so you could like label it missed, and then what happens is everything you see here, it's all based on SigMF. So you have the SigMF metadata, which is shown at the bottom at any given time, the raw metadata here. So this represents this is the metadata file. We have the sample rate, the author, which is Jacob in this case, the hardware that was used to capture the signal. But then if we keep going down, we can get to the annotations. And there were already a bunch of annotations, but the one that I added, I guess it's at the bottom right here, is now added to the list of annotations. As you can imagine, you can download the metadata JSON. So that way, if you're collaborating with someone, the data might not be changing at all, but maybe you're, like, let's say you add a bunch of annotations, you can share the metadata only. You could even like use Git or whatnot to revision control the metadata. A lot of people will put the metadata in a database like MongoDB so that it's quick to query and search over your recordings. As far as the other kind of basics of IQEngine, you can add filters, change the color map, everything you'd expect. This Python snippet is pretty experimental, but you can run a little bit of Python on the signal before it gets generated into a spectrogram. And then lastly, let me show off plugins really quick. So if I go to the, back to the FM recording here, the way plugins work, you select a region of time that you want to send to the plugin, so a region of the samples in the file. And you can even edit this on the mini map if you want to send like the whole file. And then you scroll down to the plugins section, and everything you see here represents RF functionality that's running on the back end, not browser-based. So we support Python-based plugins, GNU Radio-based plugins. I'm going to run there's an FM signal detector that I threw together. It's like super simple. And the way it works is it sends the samples to the back end, which in this case is my laptop. And that one did not work great. But, well, there's multiple FM signals here. But let me do that synthetic signal. So this signal here has three examples, and I use this for my students a lot because it's like, it's kind of as straightforward as you can get. Back to plugins. So there's a detector plugin, very simple detection algorithm. And you can see it only processed the region of time that I sent. But it returns its results via a SigMF annotation. And as you can imagine, the annotation's now in the metadata at the bottom. Now the last part, I'll show you GNU Radio. Well, the GNU Radio-based plugins, they run exactly the same, but they're implemented under the hood as a Python flow graph. Okay, so that's the idea of the plugins. There's also time frequency IQ, and I'll get to the cyclostationary part at the end. Now, I'll mention the time frequency IQ right now, it's just Plotly, fairly straightforward. So I think as far as where IQEngine has to grow, a ton of work's been done to make this custom spectrogram screen that has all these different widgets on it. You can scroll down and it'll automatically fetch the next samples from the server or the cloud. But the time frequency IQ, it's really just sending whatever samples you're looking at over to Plotly, and then it's styled, but there's really not much else there. So I think having some custom plots there could be a nice next step. All right, back to the slide deck. Did I have it open? All right, so, oh yeah, actually really quickly. When you're in the recording list screen here, let me zoom out just briefly. You get kind of the gist of the recording, who was the author, what's the data type, how many samples. And then the ones that have annotations, you can click the little button above the annotations and it'll give you a pie chart showing the distribution of the labels of the annotations. So that can be pretty useful for RFML research and such. You also have a table of the annotations. I think the first 100 show up here. So it's a nice way to quickly skim through recordings. You can imagine if you did not use SigMF, you just had a bunch of IQ files, maybe your metadata is in a database, in a CSV file. Doing this kind of quick skimming of a new data set is not as easy. And it also makes it a lot easier to share stuff with folks because they can quickly get a look. So no longer do you have to like give someone an enormous zip file, like a 30 gigabyte zip file, and have them spend a whole day going through it all. You can share a data set. If you want to share a data set with somebody, you could do it much easier with this kind of tool. And okay, so now, yeah, I want to mention the Sam Miller's and the CTF's recordings that were recently added. I will say the GNU Radio repo, as we're calling it, the first category, is sort of a dumping ground for everything. The other repos on IQEngine.org So Daniel Estevez has a whole collection of satellite recordings. Airbus has a RFML data set. And I think these last three are all RFML data sets that were contributed by the company and universities here. So if you are at some organization or university and you're doing either RFML or really any RF work that has recordings, we're happy to add you on the side here if you have some interesting recordings to share with the world. Yep. Okay. Yeah. Is it 30? Okay. Next up is, I was gonna say, I was like, I'm only halfway. I think it's a 25-minute talk, but okay. So since last year, some of you, this may be very repetitive. Apologies for that. But since last GRCon, the biggest thing we added, and probably the most important for a lot of you, would be you no longer have to store your recordings in the cloud. You can now use what we call the backend data source, which is really just whatever backend server or computer is running the backend part of IQEngine. There's the backend, the front end, and then the plugin server. So as long as the backend can see the recordings locally, like a mounted NAS or whatnot, you can keep them there and then serve them. The other big thing is we now have SigMF converters. So it's now this kind of central location for open source SigMF converters. And I'll show them in a second. You can, within the client side, within the browser, you can do a frequency shift or a square function. The squaring is popular for like hackers to find offsets, center frequency offsets. So you can square the signal. And then the frequency shift, the way that works is you drag this line, and then the results are not immediately shown in the spectrogram. Instead, like the time version here will show the shifted. That's a bad example. We'll show the shifted version. So there was a massive overhaul to the browser page. It used to be that each of these categories on the left here, these kind of buckets of recordings, were like a separate, like you had to switch between pages. So Bernard helped a bunch with the UX design, and we now have this nice system where you can quickly switch between the different buckets. And then there's still the thumbnail and description for each one. The SatDump plugin was demonstrated at FOSDEM earlier this year. It's pretty simple. It only supports a couple pipelines, but it shows kind of the reason why you might want to show off RF functionality in a browser. So if you wanted to, if you were the maintainer of SatDump and you were trying to show it off to someone, and you were on like your phone or like a computer that didn't have it installed, you could go over to IQEngine, pick one of the recordings like of NOAA APT that you know works well, run it through the plugin, and then right now we're just kind of showing graphically the results, but it's a starting point. Now, like I mentioned, you can run your own instance of the tool. For most people, it's not necessary. In fact, I didn't show it yet, but if you go to IQEngine.org and you go to the local directory on the left, you can open a local directory on your computer. Anyway, let me use this one. I think it was already set. So this directory on my computer here had a few recordings in it. So it's pulling it locally. You can do this like right now with IQEngine.org. Everything's kept client-side. So like the thumbnail that just got generated, that was done client-side. If I go into one of these recordings, everything here is client-side. But I will mention if you run a plugin, that is going to send the samples to the server. So that would be the one situation where, if you had really sensitive data, you wouldn't be taking my word for it. But if you have somewhere in the middle, right, and you avoid the plugins, then yeah, everything's kept client-side. And in addition to the directory, you can open a pair of files, meaning a data file and a meta file. So data, meta, and then it just brings you to the spectrogram page for that file. And actually, while I'm here, let me quickly show off the frequency shift. So we have a tone. In this example, there's actually a weak tone as well that's hidden. But if I frequency shift over to the tone and then go to the time GUI, and then I got to zoom in a bunch. Zoom in. So you can see there's like still a slight offset, and then you can change the frequency offset down here on the bottom left manually. And if I make it exactly what it was, then the offset goes away, and you can see the DC signal. You can turn off the frequency shift, and then you're just going to get the high frequency tone. But okay, so my point is most of you don't need to run your own instance, but if you do, so if you're someone at an organization or a company or a school, and you want to share private recordings with the rest of your colleagues, it's very easy to run your own instance here. You can also use the server you're running it on as the place to store recordings, which was not true a year ago. Most of the work is filling out a single environment file to specify the source of your recordings and some other parameters, like you can skip the landing page, for example. Now, as far as running an instance locally, you can either use the latest published Docker image, and in which case, if you have Docker running, it's like one command after filling out the environment file. If you want to run from source, but through Docker still, there's a way to build and run, as you can imagine. And then what I tend to do for development is run from source without Docker, in which case you have to run the back end and the front end separately, and then you have to do all the pip and npm installs on your local machine. You also have to have GNU Radio running locally if you want GNU Radio plugins to work. So the Docker images are very useful for testing out stuff like the GNU Radio and SatDump plugins. You don't have to care about what kind of environment you have configured. Now, either method you use here, you would open up the locally running instance with localhost and then whatever port was set, which is exactly what I have running up here since I wasn't sure about the Wi-Fi. And in VS Code, it's going to be tiny, but yeah, so I got it running here, and then I'll show you a couple quick examples of the converter later. All right, back to the slides. Now, the other kind of cool feature that was added, I don't know how many of you have ever messed with cyclostationary processing. It's kind of a niche area of RF DSP, but now there's a nice, easy way to get into it. So the idea is there's this spectral correlation function where one axis is your RF frequency, just like a waterfall, and then the other axis is known as the cyclic frequency. And cyclic frequencies are caused by like a symbol rate will determine a cyclic frequency. OFDM has some built in, especially because of the cyclic prefix. A lot of different waveforms have cyclic frequencies because of the nature. I'm not going to get into how exactly cyclostationary works. I will mention PySDR now has a chapter on it that starts you from scratch and builds up with a bunch of examples. There's even an interactive, something just like on IQEngine, interactive SCF. Except on the PySDR, you can change the signal like symbol rate and stuff without having to make a new recording. But on IQEngine side, you can, so I made an example signal here. It's simple BPSK, rectangular, pulse-shaped with 20 samples per symbol. So it looks like you'd expect, a little bit of noise. It's a very short recording, so it doesn't fill out the spectrogram. But if I go over to the cyclostationary tab, right now you can choose your alpha start and stop, and that's the cyclic frequency. It's actually normalized from 0 to 1. And the way to think about this would be, it's like the inverse of your samples per symbol. So if I've got 20 samples per symbol, I would expect some a cyclic spike at 0.05 alpha, right? So the PySDR chapter goes a little deeper into how that works. And then you choose the resolution and calculate, and this is actually running in JavaScript client side. So it's the first client-side kind of JavaScript SCF that I've ever seen in the wild that I put together. And here we have the SCF of a rectangular BPSK signal. There's a huge spike at the frequency offset. In fact, I didn't point it out, but there was I think a 200 kilohertz offset. And by the way, you can use like the time cursor if you want to measure something here. So we can see there's 200 kilohertz, and that will show up in the SCF. So We can see the spike at 200 kilohertz, and then the y-axis is alpha. It's labeled at the bottom here. It's normalized alpha in normalized hertz. And we can see the spike at 0.05, like you'd expect for a 20 samples per symbol signal. Now, rectangular BPSK also kind of has harmonics in the cyclic domain, so you can barely see it, but right here, and it actually keeps on going, but the noise is hiding the rest. Are the harmonics. If you have a pulse-shaped BPSK, you're not going to see all these harmonics. And there's a link to the PySDR chapter if you want to learn how cyclostationary processing works. Check out that link. Somewhere around the middle of the chapter is the interactive kind of SigGen with the SCF. But we start from scratch. There's a little bit of math, but a lot less than every other textbook. There's a lot of Python examples. There's full Python implementations for everything, unlike some other resources out there. All right, last big demo. So Daniel Estevez, as many of you know, created Maya SDR, which is a special PLUTO firmware image, and it gives you a real-time waterfall. It does FFTs on the PLUTO's FPGA. It provides a web interface on the PLUTO's ARM core. So nothing's running on your machine. In fact, if you had a PLUTO Plus, you could have it networked, like connected to a switch. And it exposes this awesome spec-in that I'll show you in a second here. But what Danny did was added IQEngine integration. So he already had a way to take a recording. It stores it in the PLUTO's RAM. There's 500 megabytes of RAM on the PLUTO. 400 of that is free. So he's filling all that up with the IQ recording. Now you can download the recording to your computer through the web interface, or you can use IQEngine to view it without having to download it. So, and I want to point out how easy it is to install, like to get Maya running. In fact, I put the steps here. You pretty much download the firmware zip. You copy the PLUTO firmware onto the storage device that pops up when you plug in your PLUTO. And there are a couple like environment things to set when you SSH in. But once it's all set up, and you only have to do this once, you simply go to the PLUTO's IP address in a browser. So I think it's 192.168.2.1 port 8000. And this is my SDR. So it's a real-time, just a waterfall for now. And it's doing FFTs on every sample, but then it's averaging and decimating. You can also change it to peak detect. So let me go over to like maybe the 915 band, and there's something fun there. So let me, okay, now if we want to record the signal, we click record here, and it pretty much records until it fills up the 400 megabytes. Now you can download the recording. I mean, I'll click that, and it just downloads the file like it's any web download. Or you can click the view in IQEngine, and it's actually running IQEngine on the PLUTO, and it opens up the PLUTO's version of IQEngine, which is just, I don't know how it's able to run so much on the single core. Maybe. Oh, it's probably still downloading. Oops. Nope. It did not want to go. I think I shouldn't have clicked the download. It was probably, let me go back to it real quick, see if it'll work. So record. And then stop. You can stop the recording early. IQEngine. Yeah, so this is IQEngine running on the PLUTO, not using IQEngine.org. It's not using the local one that I was running. And this is the raw recording. So what it's doing is, it's grabbing the samples you want to look at, just like the normal version does. And you have pretty much every feature from the spectrogram page. So this was an awesome integration done by Danny, and I'm really glad to show it off here. All right, back to the slides. So the last little bit, we now have a place for SigMF converters. So if you want to create your own and share it with the world, I think this is probably the only real spot. I won't bother running through an example, but right now we only support WAV files and then Vita 49, but it's really only the Diffie variant. As a lot of you know, Vita 49 is a huge family. And I can't imagine writing a converter that would work for every Vita 49, like PCAP. But if it's a Diffie PCAP, it should work, at least off the certain digitizers out there that use Diffie. So big thanks to Simon and Roman from Airbus. They were the ones who did most of this work. And you can check it out for yourself. So the way it works is you can go to IQEngine.org, and then there's a little miscellaneous tools. In the top right, there should be a miscellaneous tools button. There's I recommend checking all of these out, but the converter has a web interface. So if you have a WAV file, like downloaded off SIGID Wiki, you can upload the WAV file, and then it'll give you back the SigMF version. Now, if you don't want to have your data uploaded to the cloud or wherever, you can run the same exact converter locally. So there's even instructions here for how to run it locally. But you'll have to clone, oh, no, that's a dead link. You'll have to clone the repo, and I've got it open here. So you essentially clone the repo, and then you run the top level. Each converter has its own top level script where you can feed it the WAV file or the Diffie file, and then it'll convert it and output the results in the same directory. So I think this was in temp. There should be some SigMF recordings now somewhere here. Yeah, there they are. So yeah, if you're into SigMF and want to kind of contribute more recordings, let me know, and I can kind of show you where to commit them to. All right. Lastly, so there's a Discord channel as far as the community, in addition to the GitHub issues and PRs. We have Google Analytics running on IQEngine.org. It's only really checking like that someone went to the site. It's not looking at the specifics, but I've got some screenshots here of those statistics. Quite a few unique users every month. And then as far as how to help, so if you're interested in contributing anything like major, definitely email info@iqengine.org to get some conversations started. Now, I already mentioned the whole like time and frequency tabs, I think have a lot of potential to be beefed up a bit. So I can imagine something similar to Universal Radio Hacker's interpretation tab, if you've ever used that, where you can pick different modulation schemes and such. I think it'd be really cool to have a web version of that. It would allow people who want to do the CTF to not even have to install anything. They might be on like some work computer with just Windows and not want to mess with that, and they could go a little deeper with it. Some of the CTF challenges are solvable to this, like right now, entirely in IQEngine, just a couple of them. And now, alternative to actually developing something custom, if there's a purely web or WebAssembly signal processing framework out there that like requires no backend, it would be cool to somehow integrate that so that it could be more of a dependency, and you could do the actual DSP from the browser and work back and forth. If anyone's interested in helping to organize the RF recordings, we're still looking for someone to be like the official curator. That's why every time I do these talks, the list of signals looks roughly the same. There's actually a lot that's been added, but they've all been like, added to different directories, like back to IQEngine.org, if it loads. Most of these were not here last year actually, but a lot of it's like buried in, like in space. You can see all these different categories now. So yeah, if you're interested, we could definitely use someone to focus on organization. And with that, I'll take questions, and you can show your support by starring our GitHub. Thank you.
Thanks, Marc, and thanks for the awesome work. Any questions? All right, awesome. What's the plan for the next year with IQEngine?
What?
What's the plan for the next year with IQEngine?
Oh, I don't want to. I actually had a bunch of specifics, and then I realized I think if the right group like had an idea and was able to sort of help contribute in a major way, it could really define the direction that IQEngine goes. Because there's a lot of different ways. It could go like more the plugins route, the pipelines route, like hacker CTF style. And I think it should be determined by who comes along to help with the project. Yeah.
Awesome, thank you.
So I give you a non-answer.
Great. Anyone else? All right, well, thank you very much, Marc.
Thank you.
So we're now going to go into the lightning talks. Before we invite Suzanne Eisenberg up to do hers, I'd like to ask Jason Merlo to go to the AV table to give them your slides. And then we'll ask Suzanne Eisenberg to come up to talk about RF interference around the Alon telescope array. Sorry to make you walk back and forth there. That was not the intent.
Does this clicker work to change the slides? All right. Can everyone hear me okay? All right. Hello, I'm Suzanne Eisenberg. I am a physics undergraduate at New Mexico Tech, and I worked at the SETI Institute RAU program over the summer with Dr. Vishal Gujar and Joel Ehrlicher on understanding the 1 to 10 gigahertz narrowband signal environment with GNU Radio at the Alon Telescope Array. So you guys have probably seen pictures of the Alon Telescope Array a lot during this conference, but the main goal of this telescope is to look for technosignatures. One of the biggest problems is that there's often a lot of interference from local technology. And so a big subject in radio astronomy is essentially figuring out how you can filter out those extra signals or document them to make observations easier. And that's what my project focused on. So I had 3 main goals. The first one was creating a radio frequency interference or RFI database for SETI searches, doing real-time RFI detection, and creating a process that was easy to repeat for future projects. So I did this primarily through GR Turbo SETI. You might recognize this as having been presented by a summer student 3 years ago at GRCon 2021. This software, or this out-of-tree block, is mostly designed in order to find drifting signals, so signals that change in frequency over time due to the rotation of the Earth, and also finding signals that are narrowband, and that's what we're primarily looking for in this project. So the updates that I did this summer were making this work for live signals. I essentially combined the block that did the buffer matrix that went into the main block with the actual processing block in order to make this work. So it finds the drift rate and it finds the frequency of hit, and this can also be used for other projects and is linked in GitHub later. So these are the main inputs. You take in frequency, time step, FFT, integrations, drift rate, and signal to noise ratio, and then it outputs for each integration a .dat file of the top hits with the frequency, drift rate, and index. And if you're interested in checking out this updated version, you can scan the QR code right here. So this is a very basic flow block that I used for taking the live observations. We essentially set up this system on the GNU Radio USRP and set the sample rate. We then did the FFT, and then we did the finding peaks and main data processing block. A lot of this project was sort of figuring out how to integrate the telescope with GNU Radio with the out-of-tree block, and figuring out sort of what data rate we could take in without it overflowing the out-of-tree block, and sort of balancing those things. And that's something that I would guess a lot of people at this conference are familiar with, that process of sort of working with data and your instruments and sort of figuring out how to integrate everything together. I found this to be a very valuable experience. As someone with a physics background, it really taught me more about how the radio aspect of the project worked. And so I enjoyed doing that this summer. We did 3 main types of test data for the actual RFI survey. You might recognize some of these from Luigi Cruz's talk, but the first one was a recorded data from Voyager 1 taken by the Green Bank telescope. This was in order to make sure that we were finding the peaks. We then did live data in the form of the TAN-1 lander on Mars, and so this was sort of pointing it at that and seeing if we could detect what we expected to in the right signal range. And then finally, we did an azimuthal survey with the wideband global SATCOM satellite to make sure that it was detecting things correctly across different azimuths. Due to the limited time from integrating everything together, I focused primarily on L-band, and so this is where a lot of technology is, but it's also really important in radio astronomy because it has the 1420 hydrogen emission line, which is a protected band. So we're hoping to not see a lot of RFI right there. Okay. Well, the results are missing, but essentially we saw what we expected. The 1400 area was pretty clear, so people were doing a good job with those FCC allocations. And the 1600 area is very messy, as you would expect with the signal range. More importantly, we were able to get detections of drift rates, and so this means in future projects when we're trying to figure out the drift rate of the signal, we have a program to do that that's integrated with the Allen Telescope Array. So future work could include filling in missing azimuth and elevation values, doing varying times of day, expanding it to different bands, and also improving the real-time detection, allowing it to take in a bigger sample rate and process more data at a time. I would like to thank everyone from the SETI Institute, everyone from the Allen Telescope Array and Hat Creek Radio Observatory, everyone on the GNU Radio team, and the National Science Foundation for funding this research. The QR code links to the GitHub repository, and if you have any questions, feel free to reach out to me via email or LinkedIn. Thank you.
Thank you, Suzanne. Next, we will ask Jason Merlo to come up.
So hi, my name is Jason Merlo. I'm a PhD student from Michigan State University in the Distributed Electromagnetics Theory and Application Research Group, or DELTA, and I'll be discussing some of the work we've been doing on a distributed network radio framework. So just to kind of give an idea of what is the Delta framework, what we've been calling it, our tagline kind of says it all. It's a collection of software tools and libraries which enable simple configuration and deployment for short-lived distributed radio networks on distributed compute nodes, designed to enable rapid iteration. So really helpful for research and development applications. So the goals of this framework were to enable scalable deployments for tens to hundreds of radio devices. So we want to be able to easily deploy that from a centralized location, like a developer's laptop, and be able to deploy that over bandwidth constrained links. So we want a efficient deployment process that only transfers the files that have changed. And of course, we also want to be able to deploy this on resource constrained devices. So we don't want to be recompiling everything. So we want to preserve build caches and not overwrite that every time as well. We want to be able to easily monitor this from a single location, from a control node. Need not necessarily be the developer's laptop, but is often the case. And then the other major goal is that we want a scalable software interface. We want to still be able to do our Delta coordination. The utils are the block the coordination aspect is for coordinating the time, frequency, and phase of the distributed radio network. And finally, we have the Delta Python package, which is kind of the framework for the Delta coordination package, or the underlying software for that. And so today we have the DA Pro Tool published, and it can be certainly run without any of the additional packages, but we are planning to release the Delta utils in the near future, and then the coordination and Delta Python package at some point in the future. So just to give a quick example of how this might work, say we wanted to create a distributed network spectrum monitoring application. So in this case, we have 3 hosts, each running, and we want to have a spectrum monitor controller running on one of those hosts. Each of them is connected to a USRP. We want to monitor and control that from a dev laptop. So we'd run DA Pro Tool new proj, the spectrum monitor. It's going to create a folder that looks folder structure similar to this. In the config file, we'll have hosts, and that's where the IP addresses of the hosts and what scripts want to be launched on each node, and which radio resources are connected to each node live. We have the libraries, so where those files on our laptop are, and folders to exclude and installation commands, how we want to install that, and then some of the radio resources. So we'll run To create the controllers, we can run add monitor node, and that'll create the controller there. We have templates to generate the arguments. That's the Mako file, and then the GRC file. Similarly, we can create the monitor tool. Say we fill those out, we want to deploy those. The deploy tool will run rsync, build that, and then run it. And so we have a quick demo here. We have the 3 embedded computers connected to B205 devices. And so if this will play, yeah, there we go. We just run deploy here. It's going to synchronize all the files, build on each one of the devices, the second step. And then the third step is going to launch over SSH all of the scripts. So we're running no GUI on each one of the USRP or node interfaces. Then we're running the spectrum monitor in centralized locations. This is just the 2.4 gig Wi-Fi spectrum centered around channels 1, 6, and 11. And then, yeah, so after this runs, we can close it out and check the log files. There's different log files for the deployments to make sure the deployment's processed correctly, and then finally, also just log files for the running of the code. So yeah, thank you for your attention. And if you want to see any further details, the wiki at this link has more details and the source code that you can download for this as well. Thanks.
Thank you, Jason. Up next is the famous Barry Duggan to talk about AV setup.
Hi, Barry Duggan. I've been the lead on the AV team. Am I on 2? Yeah. Okay. And thought I'd give you a little overview of what it takes to put together the AV package back there. And looks a lot like a flow graph, doesn't it? And as a matter of fact, this was drawn with GRC. I wrote a little out-of-tree module to create these generic blocks, and it specifies how many inputs, how many outputs, and a name. That's all. It's just a YAML file. So this is my out-of-tree module, and it makes it real easy. Makes it real easy just as a generic drawing tool, because when you move the block around, all of the connections follow it. And I had not found any other just plain out drawing program that would do that. You could move a block, but then you had to move all the connections separately. That was a mess. So let's look at the pieces of this diagram. We have 4 possible inputs from computers. We have 2 MacBooks, and we alternate between your 2 presentations on those, and then we have possible one up front here. And then there's an RPi that is continuously running the sponsor slides. So anytime there's a break or lunch or whatever, we switch over to that, and it's just blindly repeating. So next, those are fed into a 4x4 matrix switch, which feeds the streaming, the captioning, and then the ones on the left and the one up front here, those displays. The audio is pretty straightforward. We have microphones, and we have a pickoff from the Zantac switch if someone's presenting with audio. Goes into our mixer board, and then that goes to the streaming, the captioning, and the room speakers. Streaming to YouTube, we have a fixed camera up here, no cameraman, which is why I put the chairs here to keep the speaker in bounds of the camera. And then we have the video feed from the 4x4 matrix switch, and we have the sound from the soundboard, and that goes into a computer that's running OBS and doing the streaming to YouTube. And then the captioning is on a separate computer, so it gets the video and the sound, and on it I'm running OBS to compose what comes up over there, and we're using Maestra captioning, so live captioning that they've made available to us for our use here in-house. And then the room displays I'm feeding into the equipment supplied by HP Video. And so we've got the projector and that monitor, and up front here, I'm looking, so I don't have to go around like that. I've got a monitor here. And then the captioning computer is feeding this side where we've got 3 monitors. And this is the team. Marc and I did this back in DC, basically the same. And Seth and Tom, August, Toby, Scott, Yannick helped us in DC, and he's in Virginia right now, I think, and watching remotely, and I'm there. So I got questions for you before you ask me any. How many people prefer the big projector screen over the set of monitors over here? So how many like the big projector better? Wow, okay. Okay, second question, how many people need or like open captions? More than I could guess, good. I always use them at home. I'm hard of hearing, among other things. Okay, so any questions for me?
Coming over. Is that coax cable to an HDMI converter that's driving the TV monitors?
Oh, this monitor,
yeah,
and that one are all fed from the captioning computer.
Okay, it's not HDMI though. I noticed it looks
Well,
like RG59 or.
I present HDMI to them, and they switch it to SDI.
Okay.
And then all of those are in a chain for SDI. Anything else? Okay.
All right. Well, can we please give Barry and team a big round of applause for the awesome work they've done all week? Thank you so much. All right. You'll notice that some people are streaming back into the room, even though we're about to go on break, and there's a special reason for that. I'm not going to ruin it, but I will invite Dylan up, or Ben.
Okay, so if you attended the RF Knock workshop or you've come by and you've talked to us, you entered yourself in a drawing for a USRP. We've got a N210 to give away, and so I'm going to pick the winner right now. You do have to be in this room, so if you can hear my voice from outside and you want to win a USRP and you're at one of those things, y'all better hurry. So let's see. We're going to give away, grabbing a card, drum roll. All right, yeah, there we go. David Diaz. David Diaz, are you in the room? Going once. David. Going twice. All right, we'll try it again. Drum roll, part 2. Here we go. Zachary Hicks. Zachary Hicks, come on down. Woohoo! All right, thanks everybody, appreciate it. Thanks for giving us the mic.
All right, thank you to NI/Emerson/Edis Research. All right, we will now go.
Before we go to break, just a couple things. I want to remind people that Capture the Flag will end at 4 p.m. today, so make sure you go check out the room, get some help some other teams, please. It's always a nice thing to do. And also check out the merch that we have as well over at the table. Thanks. Have an enjoyable break.
All right, we'll resume sessions in 15 minutes. See you in 15 minutes.
They mute me? Oh. Okay, who thinks, of those people playing capture the flag, who thinks you're gonna win? Has everyone gotten the registration desk flag? You should go do it. Has everyone found all the foxes? The stationary fox, the one that doesn't move, there's a bathroom over there. It's not in the bathroom, but if you walk towards the other bathroom, you may find it. All right. Any more hints I should give, Clayton? Is that already too many? It's already too many. Read the SigMF meta files. Okay, sounds good.
So, welcome back to the afternoon session. I'll shortly be a bit louder so the hall hears me. This is really relevant to all the capture the flaggers out there, to all the people that observe the spectrum and all the people that want to know what goes on with their radio devices. Please give a warm hand of applause to Jason Bonior. Sorry if I murdered your last name. About reverse engineering a consumer wireless device.
Hello, there we go. So, as he said, I'm Jason Bonior. I'm with a signal processing engineer with Redwire Technologies. And I was hoping to give a short talk on going through and reverse engineering a wireless signal. So my goal here was to really gear something towards people who are a little bit newer to GNU Radio, or at the very least new to analyzing a wireless signal that they haven't seen before. And at the end, to have a little bit there for those of us who come that they're interested in maybe doing something with the data, but aren't necessarily focused on the radio side itself. They just want to be able to get some data to perform some other sort of analysis. So when you're looking at a signal you've never seen before, or you're approaching some sort of a device, you're going to go through several steps. The best is always going to be to start with some sort of a documentation. From there, you're going to move on. If you can't find the answers you need, looking for it in the frequency, modulation, coding, and so on. When we get to the end here, I'll talk a little bit about the flow graph I have and how I went to display it, and hopefully give a live demo. But we'll see how that goes. So as I said, the first thing you're always going to want to do is look at documentation. Has somebody already done it? In a lot of cases, there's really good out-of-tree modules already out there. If you go look on SigMF, there's tons of stuff that's already been done, and it's great to start from that and kind of move forward. Sometimes there's other libraries that exist written for other tools. You might find something, there's a project on GitHub called RTL433 that has a lot of radio applications. Sometimes, even if you're not going to be using that particular library, the source code and the comments in the community there can also be very helpful to get you started. And in some cases, you can just apply a wireless tool, like a Flipper Zero, for things like key fobs and so on. A lot of those protocols might already be programmed in. And if nothing else, it can tell you what the packet, that data is actually supposed to look like, which can kind of give you a target to work towards as you're looking at your signal. And finally, failing all that, there's always, assuming you're within, the device is made to be sold within the United States, there's the FCC ID. And if you look that up, from there, all the documentation that they have to supply is going to give you your operating frequency, a basic operational description. You have access to testing reports to show compliance for the device. And in some cases, if you're really lucky, I've seen some with schematics, bill of materials, even board pictures, block diagrams. A lot of times they will file paperwork so they don't have to share that. But every now and then you luck out and you basically have everything you need. So, as I said, first step, you're going to want to find the thing in frequency. So in my case, I was playing with a little barbecue thermometer. Goal here to see if we can get the temperature values that are being transmitted over the air. In this case, it does have an FCC ID, which helped me narrow down where to look. If you don't have that, best places for things like this is you're going to start with a lot of the common bands, 433, 900 megahertz, 2.4 gigahertz, and kind of look around. If you can mess with the sensor, turn it on and off, so on, you can verify what it is. In my case, once I've managed to narrow down where it was, in the 433, next step was to go on and see if I could figure out the modulation. So you can kind of see, I should have mentioned before on the other slide, but you can see in the bottom there, it's just got one really strong peak, which usually implies some sort of ASK. And sure enough, if you take a magnitude, use a complex to magnitude block and look at it in a time domain plot, you can see that we get nice spikes going up and down. Heavily implies that it's going to be ASK again. So zoomed in a little further, and sure enough, you can see those are really nice looking on and off, really nice ones and zeros. And if you look at it, there's something else you'll notice. There's a really nice pattern to that data. There's not a lot of there's never more than 1 or 2 ones or zeros, which would usually imply something like a Manchester encoding. So in this case, going from a 0 to a 1 is a 0, a 1 to a 0, a 1. So if we try applying that, we can then look at the bits that come out, vary the temperature by messing with the temperature probes, and then we can start looking at the packet to try and find out what's actually going on in the packet. But I ran into one little trouble here, and I don't know if you guys can notice the pattern to all that data up there. I only ended up with hex values of A6, 5, and 9, which looks a lot like Manchester still, which led me to think that maybe something was wrong with the block. Went back through my block. It appears to be demodding. I went so far as to print off the time domain plot you saw there and go through by hand and decode it. And sure enough, this is what you get out of it, which left me a little confused. So decided to try just doing it again and see what comes out. Ended up with data that looks a lot more reasonable. I don't know about anybody else here. I've not encountered double Manchester or maybe some other encoding, and I just got lucky with that. But in the end, I ended up with a packet that looked much more reasonable. So, as I mentioned before, the thing to do would be to vary the, here, I'll back it up. Vary the, in this case, vary temperature, or in some ways the sensor state, so that you can see what kind of changes that produces in the packet. In my case, the numbers you can see on the left are going to be your, are the temperatures of the two things, or the two temperature probes in Fahrenheit, and then the resulting packets. Playing with that a little bit, I found that the first nibble of the packet is always going to be a 2 or a 7, a 2 under normal operation, a 7 if I push the resync button on my thermometer. The temperatures always seem to vary in those same, in the next 5 characters, and the last 4 appear to be the checksum. And those in particular narrow down on being the checksum, because as varying the packet values, a change of 1 bit would change those 4 nibbles quite a bit. So my first assumption would be some sort of a CRC. And I don't know if anybody's used CRC, I would say Revenge or reverse engineering. It's a nice command line tool where you can plug in multiple packets and it will calculate or basically brute force and tell you what CRC algorithms fit. So I took a few packets, plugged it in, and got nothing. So that was very frustrating. So my next assumption was, okay, it's some sort of an XOR mask, some sort of a checksum, other checksum that's being applied, and I started collecting packets. When I ran into another problem, you can see I have 2 packets up there. The packet type and the temperature data are all the same, but they have different checksums. That one really confused me as to how you would possibly get it wrong. So, do I have something else going on there? But those 2 different checksums come from when you press the resync button on the thermometer. Every time you push it, you'll get that 7 I mentioned for a resync message, and that checksum will be different from that point forward, even for the same data. Now, at this point, I was getting pretty close to the conference, so I went Googling around to see if I could find, following my first point there with documentation, see if anybody else has done this. Found some other people trying to different projects, playing with the same thermometer. And on the Adafruit forums, I came across a user named Nibbler who has a great post explaining how they worked out what the algorithm for this checksum is. It's actually an XOR mask that changes, it's calculated from a linear feedback shift register, and that's applied to the data, and the result will give you a session ID, which is how the thermometer syncs to its receiver. I was going to give a quick overview of how they calculated that, but there is so much there, and it's so well written that if you're interested, I would encourage you just go find it. I have the link at the bottom and at the end of the presentation. They put a ton of work into that. And anyway, as we took that, rolled it into the flow graph, and so I end up with the final flow graph. Taking the data in, taking a complex to mag, slicing the bits. In this case, I'm then the multiply by 2 and subtract 1 is to make the bits differential. That way I can feed it into a correlator and look for that preamble pattern at the beginning to line up to wherever the packets are. Once I have that, I feed it into a Manchester decoder, and that data then goes into a parser I wrote, which takes the data out, breaks the packets apart, and passes it on as a PMT to another block, which is the packet to 0MQ, which formats the data in a nice JSON format, serializes it, sends it out over 0MQ to a web server, which is then updating a web page so that we can remotely monitor what the temperature is. There's just a little quick picture of the web server running there. I'll bring up an actual demo, though, as opposed to just a screenshot of it. But as I'm trying to bring up the demo, if there's any questions, the code for both of these or for everything that I did here is available at Redwire's GitHub page. The link at the bottom is the one I talked about. It really is a great article talking about how that individual reverse engineered that checksum. It's worth a look.
So everyone think of questions to ask after the demo.
Not having any luck so far with it, but worst comes to worst, I will have it set up over at our booth in the expo hall. Have it running there. I guess jump straight to questions then if it's not gonna.
Okay, are there any questions?
The problem's probably on my end. It doesn't look like the laptop's even recognizing that it's connected. Anyway, sorry about that.
I do have a question. So when you get the data out of your flow graph into your web server, how do you do that? I thought that was a standard ZMQ thing, or how did you integrate the ZMQ into your self-written block, or how does that work for you?
I'm sorry, I don't think I understood.
I understood you had the visualizations on a website, right?
Yes.
And you got the data out of your flow graph into the website using ZMQ.
Yes.
So how do you format the data to go over that ZMQ?
Oh, okay. So I found I just found a JavaScript toolbox that had a graph that could be updated real time. It's just running a Flask web server in Python, and then I'm using WebSockets to send it over to the website. And that is the web server itself is included in the apps directory of the out-of-tree module for this.
Okay. Thanks. That's pretty handy. It also has like a high reuse factor, right?
As we were hoping to, as I mentioned, like sometimes you get people. I've worked with some people who are like, I don't really care about the radio side, dude. I need the data. So here's a simple example of getting data out somewhere else.
Yeah. Thank you.
Yeah.
I see no other questions, so please give a warm hand of applause. So up next would be Jon Kraft, I think, and Jason. You guys. So, we will be talking about, hopefully, yes, radar support into GR plasma with Jon, Flane. Justin is not here. Sad. So, please welcome our speakers.
Thank you. We're going to be talking about how to take a PLUTO or phaser board and turn it into an easy-to-use, real-time radar system. So my name is Jon Kraft. I'm an applications engineer for analog devices. I'm just going to do the first couple slides, just going over the hardware, and then I'm going to turn it over to Shane from University of Oklahoma. But we also want to thank Peter and Dr. Metcalf for their work on this project and their help. It's always the last one. So real quickly, we'll just talk about the hardware, and then I'm going to turn it over to Shane for an overview of his GR plasma auditory module, and then the changes that he made to GR phaser to get the phaser implemented, as well as the PLUTO implemented into his radar software, and then we'll show you some examples of that. So I think everyone's familiar with PLUTO. I hope you are now. And actually, right after this talk here, I'm going to do another talk updating you on some of the new features of PLUTO and where we're at with that. So I'll save that for later. But not everyone might be familiar with our phaser. It's our X-band phased array exploration platform. It's specifically intended for educational and some prototyping uses in the field of phased array radar and comm systems. This is a full 10 gigahertz system that has 8 channels of receive where you can adjust the gain and the phase of each of those 8 channels across the array. It has 2 transmit ports. They're switch transmit, so you could be one transmit or the other. And it uses a stretch LO system on the mixers, LO, to implement very wideband chirps, up to 500 megahertz FMCW chirps. So you get great resolution out of it. So this system has been released now for about a year and a half. It's available on our website, analog.com. We have oftentimes been out of stock on this system, but we just got in a big stock now. So it is actually, I'm happy to say it is in stock now. We have drivers and examples on how to use this system in Python or MATLAB, but what we were really missing and what we really wanted was an example or a system to use this with GNU Radio, to take advantage of all the features of GNU Radio and its processing power to use this in a true radar system. And so with that, I'm going to turn it over to Shane to talk about his work. Thank you.
So, hey everybody, I'm Shane. I'm a PhD candidate at the University of Oklahoma. I'm going to start off this talk talking a little bit about GR plasma. For people who aren't familiar, this is an out-of-tree module that we developed at the University of Oklahoma a couple years back. And the main utility of it is doing real-time radar processing at really high sample rates. So we've tested this on GPU-accelerated processing specifically. So we've tested this on just a pretty standard desktop GPU of 4080, and we're able to get several hundreds of mega samples per second real-time throughput just doing your range Doppler processing for your pulsed radar. So one of the big kind of architectural choices we made for this repository was to implement everything using the message passing interface. So each block is going to take as input a PDU, which is just a metadata dictionary and the IQ data that you actually want to process. And it's going to spit out another PDU that's done the operation you want to do. Another thing that we wanted with this repo is we wanted it to be as hardware agnostic as possible. So we have support for CPU backends, CUDA backends, OpenCL backends, and you can specify in each of the blocks, there's a little drop-down menu for which backend you actually want to use. And in the past, we pretty much only supported the UHG radios. So at the bottom here, I've shown just a couple of the blocks that we've implemented so far. So on the left, you have like just doing a monostatic radar with a USRP. So take an input, transmit waveform, output what you receive. We also have things like pulse Doppler processing, like I was talking about before, you know, a match filter and a Doppler FFT. And we also have several waveform generators in there. So your linear FMs, polyphase coded waveforms, and various phase codes. So we wanted to take PLUTO and Phaser and port it so that we could use it with Plasma. You know, take the processing backend that we already had and add new hardware. So to do that, we've introduced two new blocks. They're both shown on the right. One of them, the one on the bottom, is the PLUTO radar, and that just takes the PLUTO standalone. And the top one is the Phaser radar, which has a PLUTO plus your Phaser phased array board. And for the Phaser radar, there are two operating modes. First, you have your pulsed mode, which is you send an arbitrary digital waveform through that input port. And the limitation of this is that you have to actually sample that waveform, right? So you're limited to the sample rate of your PLUTO. And this is the only mode that's supported in the PLUTO radar at the bottom. But if you have a Phaser, it has hardware on board for doing FMCW waveforms. So you can in hardware generate high bandwidth chirps, and before you actually have to digitize it, you can do stretch processing, which I'll talk a little bit about next, to reduce the amount of data that you actually have to sample. And another cool thing about doing things in the message domain is that it makes control super easy. So one thing that we've added in this block is if you want to steer that phased array, you can just pass in a control message to change the angle, making it super simple. But you can also do things like real-time waveform adaptation or other parameter changes that I'm not going to talk about here. Right, so I'm going to just give a brief overview of the Phaser radar block. The PLUTO block is pretty much the same, just with fewer options because you're not controlling a phased array. I don't know how well that shows up there, but for the most part, the parameters are what you would have seen for any other radar or radio block that you've already used. You know, you've got your sample rates, your gains, that type of thing, which channels you want to use. But we've also added a few other useful options into this block. So for example, if you're processing pulses, it's a lot of data if you're trying to process an entire PRI of data, right? You might only care about a specific range swath. So we've added several options in there to where you can actually dice up your pulses to process only the data that you care about. And then on the right there, I have just various examples of, with the Phaser block, you can specify your array weights, your gains, like if you want to apply a taper, and so on. And then on top of that, it has a bunch of radar options. So there's a little drop-down menu where you can specify if you want to operate in FMCW or in pulsed mode. And from there, you can tell it how many pulses do I want, how often do I want to send out pulses, what is my pulse repetition interval. For FMCW, I can specify how wideband I want that chirp to be, how long I want it to be in time, and so on. So yeah, just giving a very brief example of how you would apply this in FMCW mode, I have a flow graph shown here, which is a video. And like I said before, the Phaser generates these in hardware. It has an oscillator on the board. And before you actually get the data on your SDR, it's going to apply stretch processing, which is just a simple multiplication on the board. And if you take your high bandwidth waveform, you can apply stretch processing and get back a beat frequency, which is proportional to how far away the object is. And this beat frequency is going to be a sinusoid that is a relatively low frequency and easy to sample. So hopefully it shows up well. Yeah. So as a simple example, going back a little bit, one thing I want to point out before I actually play this video is that I don't actually have anything connected to the input port for FMCW mode, right? It's just generating it itself. So when I start the flow graph, I can have my FMCW parameters on here. Again, I'm not sure how well it shows up. It is a 500 megahertz chirp over 100 microseconds, sending out 5 chirps. So I run this flow graph. Right now I have an antenna pointed away from the radar, a pretty directive horn antenna. I pull up the time domain after I sum the beams together on the Phaser. And when I start pointing the antenna towards the Phaser, I get these nice beat frequencies, which is just a sinusoid, plus a little bit of junk at the end because of some hardware like overshoot when you're actually generating the chirps. But I can move the antenna around and I can see a little bit of phase shift as I do that and slight changes to the waveform. But overall, this just verifies that, yeah, with the radar block, I can get nice update rates on however many pulses or chirps I want. So a similar thing I'm going to show in pulse mode. And the only real difference here is now I actually have 2 sides of my flow graph, right? On the left side of that Phaser radar block at the bottom, I have the waveform I want to transmit, which is its own block. In this case, it's just a chirp that's transmitting over 20 megahertz, within the PLUTO sampling range. And on the right side, I'm only going to show the plot from the bottom, but what I'm doing is I'm taking the beams from the phaser, summing them together, and doing a similar time domain plot as I did before. So a similar example, again, just showing off pulsed mode. I'm sending out 5 pulses at a PRF of 10 kilohertz. So I start up the flow graph again, give it a second to boot up, and I get similar plots. You see, I'm sending for a small amount of time, getting the waveform I want. When I point it towards the antenna, I can see those chirps nice and clearly, right? And the way that I'm actually getting this nice, precise timing with the phaser is something called the TDD engine, which is pretty new and something that Jon will talk about soon. But yeah, as I move the antenna around, you can see that I'm getting shifts in this waveform, and again, a nice update rate for real-time processing. So after I'd verified that I'm getting good data off of this, I wanted to go out and actually test it. So I set up an over-the-air live demo with the phaser. So I have my little test bed that I put together in the bottom left. All it is a laptop connected via Ethernet to the phaser. I have that horn antenna I was using earlier, which is about 18 dBi of gain. And what I did was I set up the cart along this road, and I had one of my friends drive their truck all the way down the road. And the goal was really to see how high quality we could get the data and how far away we could get without any kind of external amplification, right? So we're just using the amplifiers on the phaser and on the PLUTO. And the main data product that I wanted to get out of this is what's called a range Doppler map. And if you're not familiar, a range Doppler map is just an image where on the y-axis I have the range, which is how far away you are from the radar. And on the x-axis I have the velocity, which is just how fast it's going towards or away from the radar. So as the truck drives away, I would expect a dot that goes further away in range and increases in velocity, stops, and then turns around and comes back close to 0 range where the radar is. So I recorded the data on a flow graph. I did all of the processing in GNU Radio and saved it to a file so I can make a pretty plot. And here's what that range Doppler map looks like. So when I first start off, this is, I think, the first processing interval of the radar. But when I first start off, you see that bright dot close to 0 range. So when I start it, he starts driving. You can see that we maintain that dot all the way up until about 150 meters when he turns around and comes back towards the radar. Don't do that conversion from meters per second to miles per hour. I promise he was going under the speed limit. Yeah, so you could see a very clear dot, a very clear image of where that truck was throughout its course. So this says that, hey, we can get good range Doppler data up to about 150 meters with no external amplifiers, which is pretty good. So yeah, that is the main thing. All the processing, like I said, was done in gr-plasma. If you only care about getting a radar, you just want to see pulses and you want to do something with them, you don't actually need gr-plasma. All you would need there is what I'm calling gr-phaser, which has both the PLUTO and the phaser radar. But really the idea with this was just make it as easy as possible to, if you have a PLUTO or a phaser, just download this and instantly have a radar. Yeah, and if you would like to see more, like see the processing in action, just see us how fast it updates. Analog Devices has a demo at the expo hall, and I can walk people through that if they would like me to go through it. But that's all I got, and I'm happy to take any questions.
So are there any questions? I will ask some if you don't, so you better ask. See, that works.
Just great talk. I just wanted to ask if in the interface for, I guess it was, I might get which one mixed up, I guess it was gr-plasma, if the independent receive channels are exposed when you're using the phaser board.
If the what?
The separate receive channels from the array. They said at the beginning of the talk that I think there were 8 receive channels. Yeah. Are the separate receive channels exposed, or is that all handled inside the block?
So what happens is the phaser actually beamforms those down to 2. And the block outputs, when it outputs its IQ data, it outputs those interleaved, so it'll have beam 1, beam 2 stacked on top of each other. And if I go back a little bit, I was only showing, let's see if I can get a better picture. You see that at the output, I'm actually summing the beam before I do anything. So yeah, if you want to do something with multiple beams, you can just not sum them and do whatever you want.
I don't see any other questions, so please give another round of applause for Shane. So,
okay, thanks. I want to thank Shane and Dr. Metcalf again. That was just, it's really impressive work. And if, for those of you working in the radar field, you know how intensive that signal processing is, and to be able to do it real time is very impressive. So yeah, thank you to you guys again. So again, my name is Jon Kraft, applications engineer for analog devices. I want to give you some updates on our PLUTO software-defined radio, kind of some new things, a correction on something, to look for and possibly fix on your PLUTO radio, and we'll go over that. I also want to thank Marc Thorin. Did his name get cut off? Sorry, Marc. That should say Jon Kraft and Marc Thorin. I want to thank Marc Thorin. He contributed to these slides, and he's always great to work with. That's always the one I don't pick up. All right. Okay, so just a couple things that I want to talk to you or go over today with this PLUTO. First, what is PLUTO? And specifically, I think everyone's aware of now, there's a Rev C that's been available for a year or two that exposes the second transmit and the second receive channel. So I'll just give you a quick look at that. And then I want to talk about how to incorporate Pi 80 IAO into GNU Radio. So this is our Python interface that you use in Python, but it actually works really well as if you incorporate it in a block in GNU Radio, and I'll tell you why you might want to do that or why that would be interesting. And then the TDD engine. So Shane talked about this cool TDD engine that's going to synchronize the transmit and receive buffers. This has been a long asked for feature of PLUTO, and so we finally got it working really well. And it's what makes these kinds of radar things possible, where we can synchronize the transmit and the receive waveforms. And then I want to talk about a little issue with some PLUTO ESD diodes, how to test for that, and then how to fix it on your PLUTO if it is a problem. And then finally, a very cool context port forwarding. So if you have a bunch of PLUTOs or really a bunch of any IAO devices, how you can group those all together and transmit them all over one Ethernet, so you can control and stream data back and forth over one Ethernet cable. So PLUTO, I think everyone is aware of PLUTO. It's our little software-defined radio using the 809363 transceiver chipset. Natively, it's one channel transmit, one channel receive. There's a frequency expansion hack that you can do to increase its frequency range from 70 meg to 6 gigahertz, as well as instantaneous bandwidth up to 56 megahertz. It all communicates over USB 2.0, so it's a little bit slower for streaming data, but it does have quite a bit of memory on it for storing data, and then you can download that to your computer. With Rev C of PLUTO, we expose the second receive and transmit channel, as well as the oscillator input and oscillator output. There's some videos on YouTube on how to access those channels and how to modify the programming, including the Python programming, to take advantage of those channels. I'll say though, when you do expose the second channels, the output data rate drops in half because we're using a slower data interface on the PLUTO to the FPGA. So the output data rate gets halved when you do this channel expansion, but we're still using the 809363 transceiver, so none of the hardware has changed at all. It's still using this 809363 transceiver, but we're just exposing the additional channels that it has. Okay, so what are some ways that we can control PLUTO in GNU Radio Companion? The classic ways, and ways maybe you've done, maybe you've seen before, is to use the PLUTO source and sync block. These are very easy to use. They're very robust. They're installed by default when you install GNU Radio 3.10, and very easy to use. Another way to interact with PLUTO or any IIO-based device is you can use the IIO attributes to assign attributes and then to stream data or to send data back and forth to any IIO device. The flow graph starts to get a little unwieldy because you have to set up all these different attributes. And so if you are going to go that route, I would highly suggest you take a look at this presentation from Michael Henrich from a year or two ago, where he introduces the message to IIO dictionary block. Great presentation, and a much more elegant way to implement these kinds of functions for any IIO device there. But what I want to talk about today is how to use Python with GNU Radio Companion to control PLUTO or really any of our devices in this Python library. So why would you want to do this? Why not just stick with Python? If we're going to use Python, why not just stay in a Python IDE? Why combine it with GNU Radio Companion? Really, the reasons that I like it are really the GUI objects in GNU Radio Companion are fantastic. When you drop down a slider bar, it is so easy to add it into a Python program versus trying to build your own in tkinter or Qt in Python. It becomes just very cumbersome. Your whole program just explodes. And the way GNU Radio does its multi-threading, it's just a very smooth, seamless operation. The plots update quickly. It's a very slick, it's a very great user interface that is very, very easy to do. Why not to use it, or maybe some of the pain points, and this could be because of my own ignorance in GNU Radio. Maybe there are better ways to do this. But one of the pain points is the input-output buffer size, or at least the way that I implemented it. Shane implemented it a much smarter way using message passing, and that's the right way to do it. I didn't do it that way, but I do want to thank Wiley for his help and his advice on sort of what is the easiest way that I could do this and put this together. But the buffer size, the output buffer size, you just have to be aware of it, and you kind of got to work around it, but I'm sure there's better ways to do it. And then the other thing is that the IDE for Python and GNU Radio, there really isn't one. So I do everything in a text editor, and maybe there's a better way to do that, but it's very difficult to debug a Python script in GNU Radio. So I do most of my editing in Spider or PyCharm, and then once my Python script looks pretty good, then I import it over into this GNU Radio Python block. So how do we control any device from Analog Devices in Python? We use this PyADI IIO library. You can download it here. It's great. In Python, it's just import ADI, and that has all of the ADI objects, whether it's an accelerometer or a software-defined radio or a synthesizer or a precision ADC. Whatever it is, you're going to find that object in this ADI library. And then you just create an object of whatever you care about from that library. So if you're doing PLUTO, it's just ADI.PLUTO. You can also give it a context, like a USB or an IP address. And then you assign attributes to that object. So here we're assigning the transmit and receive LO frequencies, and they're both set to 2.2 gigahertz. And then you either send or receive data from that object. And so here we're just getting a buffer of data. So it's very easy to use. It's very human readable. There's no weird names or anything in here. And it's very consistent across all of our Analog Devices products. So once you do it once and you switch to a different product, even if it's a totally different product, it'll be very familiar to you. So then you can take that Python code and you can put it into one of these Python blocks in GNU Radio Companion. So you can see that block there. All the other blocks are just GUI blocks I was talking about, like they're slider blocks or they're graphing blocks. And so kind of all the work that is done in my flow graph is in that one Python block, and then everything else is just a GUI object. So it's super clean. You can take a look at this code in flow graph. It's on my GitHub page if you want to, but again, with the caveat that I am neither a Python expert or a GNU Radio expert, so I'm sure there's better ways to do this, and if there are, I would love your help or contributions to kind of do these kinds of things. Here's what that flow graph looks like. If you just click run on that flow graph, that's on my GitHub site. So I'm sending out 4 FMCW chirps in the Python program, but you can see just how easy it is to use it's very fluid to use the slider bars, and it updates very quickly and stuff. I mean, it's not like a super impressive demo, but like to do this in Python is much more clunky. And it definitely clutters up your Python code, whereas I don't have to put any Python code in around outside of the actual work that I'm focusing on and that I'm doing. And so here's a time domain plot. You can see those 4 chirps going on there. And to learn more about how to incorporate that kind of Python code into these Python blocks, I highly recommend Wiley's presentation from a couple years ago. I have gone back to it several times. Great presentation, great information, and you can take a look at that. I've also created a wiki page for how to install the PyADI programming Python library into your GNU Radio installation. So I've tried it out and done examples for Windows using Radio Conda, Ubuntu 24 Linux, and then our Kuiper Linux on the Raspberry Pi. So if you go to this site, you can see step-by-step instructions on how to install GNU Radio, but more importantly, how to then incorporate the PyADI IIO Python library into your GNU Radio implementation so that you can call it from this Python block. And then just a quick slide. If you do that, here's how you can check your installation, and you can make sure that you really have installed it and all the paths are correct and everything like that. Okay, so that was how to put Python into, or how to use our ADI Python library with GNU Radio Companion. Hope that was helpful. Now I want to talk about the new TDD engine. So when I ran that last flow graph, we did 4 FMCW chirps, and it looked like this, and they were all just kind of dancing around the screen. And if you've used PLUTO before, you're used to seeing things like this. But check this out. Same program, one change though that we made, but now look, everything from the transmit buffer on the top row is synchronized with the receive buffer on the bottom row. So everything is time aligned and stable, and this is what allows us to do that kind of radar implementation. Okay, so how do we do this? We use this new TDD engine that's in PLUTO. There is a TDD engine in Rev 0.38 of PLUTO, but we're actually tweaking it and improving it a little bit. There was some timing things that we wanted to improve on, as well as some syntax that we wanted to change. So if you want to try this out yourself, download it from this link that's on there for now. And I think very soon, maybe in a month or so, there'll be a new version of the PLUTO firmware that will have all this incorporated into it. But essentially, how do we set this up? We create a TDD object. We assign attributes to that TDD object to control the timing. We trigger the start of the TDD engine, and that's going to then align our transmit and receive buffers. And then we read back those receive buffers and just do whatever we want with that data. I want to thank, in particular, Unit for all of his work on this TDD engine and stuff. I really appreciate it, and he's done a great job with it. It was a lot of work to figure all this out and put this all together. This TDD engine, this is what it looks like in Python. There's a bunch of attributes that essentially control the timing. The default values that I show here are pretty good values that if all you want is just to align the transmit and receive buffers, these values are going to work out well. A couple of caveats in there. You must be in cyclic buffer mode for transmit. This means you load the transmit waveform once and then it just repeats over and over. So you must be in that mode. When you're making changes to the TDD engine must be disabled, and then you re-enable it after those changes are done. A couple of notes in there if you want to read through them. And this is what that modified code now looks like. So it's the exact same code that we had run before, but now with that TDD engine included in that Python block. And this is what the whole timing profile looks like. If you really want to get into it, there's all kinds of, I suppose, kind of cool things that you could do with timing, including outputting pulses from PLUTO, outputting GPIO pulses at a specific time or at a certain rate or a certain number of pulses, and I'll show you how we use that in a couple of slides. So there's actually quite a few things that you can do that are fairly powerful, more than just aligning transmit and receive buffers. You can trigger this TDD engine either from a software command or from an external GPIO. So here's a case where here's how you would do that triggering with external signals. You can You can trigger it on pin L12N of the little PLUTO 14-pin GPIO header there. And if you have configured it to output pulses, which you do with these commands here, if you've configured that, those pulses will output on the next pin adjacent to that pin. So why would you want to do this? Why would you want to output pulses? I suppose there could be any number of reasons, but the reason that I want to do it is because I can then feed that pulse train into the ADF4159 has a trigger input called TX data. And when TX data receives a trigger input, it will execute something. It will execute some frequency ramp or FSK step or something like that. So for radar systems, I can set that up so that it executes some 500 megahertz FMCW chirp every time that it receives a TX data input. So this is very cool, and it makes doing multi-chirp, the range Doppler plots that Shane showed, makes those very easy to do. And here's if you put that all together with that external system and stuff, this is what it looks like, that range Doppler plot. Here's cars going past. And so this is 500 megahertz of chirp bandwidth, which we get, like Shane talked about, from that stretch LO processing. So this is what it looks like. This is with the TDD engine. And, okay, so let me move on now. I only have a few minutes left for the PLUTO ESD diode issue. We, in an effort to fix something that wasn't broken, we added these ESD diodes to all the 4 of the RF ports on the PLUTO Rev C. And it was a very noble effort. We thought, why not? Let's just add ESD diodes. And what we found out was that our manufacturer had a hard time with those diodes, and they tended to put too much solder paste underneath those diodes. And it was difficult for us to test this out because we do a lot of over-the-air testing. So the issue is that there could be solder paste underneath these diodes that essentially short an input or an output of these 4 RF ports out. And what that's going to look like is if you do a loopback test, if you loop back transmit to receive, you're going to see a much smaller signal. So in this slide, I've put just some parameters that you can try out on your PLUTO, and to give you an idea of what kind of amplitudes you should expect to see. And if it's very low, you can remove the diode. If it's around these numbers, you don't have to remove the diode. I don't know. I remove the diodes on all of my PLUTOs. They're really not necessary. It would be extremely difficult to ESD zap the center conductor of one of these SMAs. So I remove all the diodes anyway. But if you don't see a problem, I guess you could leave them in. To remove the diodes, it's very simple because they're so tiny. You just the easiest way I found to do it is I just scratch it off with my fingernail. It scratches off pretty easily. And then what's left over is a little bit of solder and a little bit of pads from the ESD diode. And so just take some solder wick and you can suck up that extra solder. So there's on the lower right-hand corner, there's a picture of what that solder looks like beneath an ESD diode. So sorry about that. Hopefully your PLUTO's okay, but if this is the way to check for it and hopefully fix it. And it could be on any of those 4 ports. The 2 transmitters, 2 receivers. In the last minute that I have left, let me quickly go over context port forwarding. This is a very cool feature. Say you had 4 PLUTOs a long way away and you wanted to connect them to your computer. How would you do that? There's actually a couple ways to do it, but you wouldn't necessarily have to run these super long USB cables. But a cool way to do it would be, why don't I connect these PLUTOs into a local Raspberry Pi, and then via Ethernet connection, I'll talk to the Raspberry Pi and it will control and stream data from all these PLUTOs. That would be very cool. And how would we do that? We do that by this new feature from libIO version 0.24 and above, where we have this context port forwarding. What is a context? A context is just a group of these IIO devices. So things connected to your Raspberry Pi through SPI or I2C form a context for the IIO devices. PLUTO has its own context through USB. It's just this group of IIO devices. Before that, you might have to plug in maybe a Raspberry Pi to your laptop, and you might have to plug in PLUTO to your laptop. Each one has a separate context, and then within Python or GNU Radio, you would address them and create objects. But now with context port forwarding, you can run an IOD service right on the Raspberry Pi that you can assign a port number to whatever IAO device like PLUTO and do that. This is what it looks like. If you just run this command on your Raspberry Pi, you can assign a unique port number to the PLUTO device that you have connected to that Raspberry Pi, and that will forward right out into your computer via Ethernet. And you can see that if you open up IAO Oscilloscope and hit refresh and scan for all IAO contexts, it will find that over that Ethernet cable, and it will report back to you. It is, in this case, it's called phaser.local :50,901. But you could do that with, but you can do that automatically. I'll share these slides. These are some scripts that Marc Thorne has put together to do that automatically at startup. It will start up the service. And of course, you could do that with multiple PLUTOs together. Here's 4 PLUTOs. Each has a different IP address, and each has a different port that we're forwarding it to. And all of these can be interacted from a long distance away from your computer running MATLAB or GNU Radio or Python or whatever. And it doesn't have to just be PLUTOs and devices like that. You can also do this with serial backend devices. Really, any IAO device, whatever context it has or way, you can forward it using this service here. Okay, so that's it. Just a quick update on PLUTO, some new things that we're doing, and hope that was helpful. Thank you.
So, are there any questions? There will be a test on the TDD engine after this talk, so you better ask now. Okay, then let's give another round of applause. Okay, so now I'm doing the very well prepared part where I... Oh yes, next up is Alon, and he's talking about enabling integrated circuit-based full duplex wireless in GNU Radio. Yes.
How's it going, everyone? You can hear me? Okay, perfect. Good afternoon, everyone. My name is Alon Levin. I'm a PhD student at Columbia University, and I'll be presenting, enabling integrated circuit-based full duplex wireless in GNU Radio. So this talk comes about as essentially a summary of the FlexCon project at Columbia, which is a research effort into enabling full duplex wireless networks from the IC level all the way up to the network algorithms and further. There we go. So when we say full duplex wireless, what we mean is the simultaneous transmission and reception on the same frequency at the same exact time. So normally you look at any other device, your laptops, your Bluetooth headphones, whatnot, they're operating half duplex mode. And the reason for that is that you don't want your transmissions to end up leaking back into your receiver, right? The relative power level is between 70 to 110 dB between your self-interference and whatever you're trying to pick up from the other node. So well, for a long time it's been seen as an infeasible problem to combine those functions, transmitting and receiving on the same channel. So the reasoning why we'd want to do that in the first place is a problem of resource efficiency, right? You have a lot of wireless devices right now in the network. Everything is trying to compete for the same resources. If you're able to remove the need to split up your transmit and receive streams on different resources, you're essentially doubling the amount of resources you have. To get over that, to enable that, you have to get over that self-interference problem. So what we do is you really just throw the whole toolbox at it, right? Spoke about this already. Essentially, what we do is you have sort of essentially 3 levels of self-interference cancellation that you could apply in your typical full duplex transceiver. First, you have your passive RF isolation, which is your antenna interface, whether you have a single antenna scheme, such as a circulator or an EBD, or you have a dual antenna scheme where you literally use the physical distance between the two for your isolation. That serves as the first step. Next step is your RF or RF analog cancellation. The reason you need that is because you don't want to saturate your receiver, right? If you saturate your receiver, you can forget any hope of picking up anything else besides your own self-interference. So once we reduce that down to the point where you're no longer dealing with those desensitization issues, finally you can clean everything up with digital algorithms already on the compute side of the node. So at FluxCon, we were investigating 3 different RF canceller classes, right? And this is just a quick overview of our history. First, there's the very simple phase and amplitude-based equalization, where you take a copy of your transmitted signal, you you play with the amplitude and your phase settings so that you have perfect destructive interference, hopefully, and just feed that back into your receiver where, again, hopefully you destructively interfere with your self-interference. Next step was to explore frequency domain equalizations, where essentially you have banks of passband filters, which again, you can play with a bunch of different configurable settings there. And finally, time domain equalization, which applies the same principle as before with the phase and amplitude-based equalization, except instead of explicitly modulating the phase, modifying the phase, you are trying to emulate the delays that the self-interference travels through. And essentially, again, your goal is to have as much destructive interference as possible. So we took these concepts, and well, our collaborators developed 3 ICs that do just that. I'm not going to go into how they developed these ICs. I'm going to leave that to the RF engineers and their magic, or I guess the RFIC engineers and their magic. But we developed these 3 ICs, and now the question is, fantastic, we have some sort of semblance of a RF full duplex front end. How do we build a whole full duplex radio around that? So we have 3 classes of ICs, therefore we have 3 classes of radios. The very first one, the first generation, uses that phase and amplitude-based canceller. It's very simple. The front end has only a single tap with 2 configurable parameters, your attenuation and your phase. You can configure it through GNU Radio, through Python, through whatever other means you want, using Ethernet to SPI interface. And what you get is about 42 dB of RF cancellation across a 5 megahertz bandwidth, with the rest being cleaned up by digital SIC, which again, we're going to cover later. The next generation sort of took that to the next step and added the passband filter banks to that concept. So now you have a lot more parameters you can play with, right? You have the center frequencies you can play with, the quality factor of your filters, and now it added the capacity to essentially have 2 passband filters in parallel. So now we have 2 taps instead of 1, which gives you greater flexibility in your cancellation. And that now enables you to have up to 20 megahertz of bandwidth that you can realistically get good cancellation, and therefore enable full duplex communication through. And now the next step, the current work in progress, is the 3rd generation full duplex radio, which is a time domain canceller, which consists of essentially 16 parallel RF taps, each with variable gain and variable delay. And whereas the previous 2 generations of front ends had relatively small configuration parameter space, right? It's something that you could fiddle with by hand in GNU Radio and find the optimal cancellation. Here you have a parameter space on the order of 10 to the 19th. So at this point, you need to start investigating configuration algorithms. How do we take what self-interference we measure and apply that so that we can find the optimal configuration to cancel that out as much as possible? And so here's the next question, right? This is the guts, right? How do we actually, fantastic. We have the front ends, we have our radios. How do we actually control this? How do we find how to configure them and such? Well, the answer's in the corner, right? We use GNU Radio. So the next sort of set of slides, I'm just going to go through the key processes that we developed throughout the years of the FluxCon project, and go over the sort of design considerations you need when implementing full duplex. So first things first, we have to consider there's the self-interference aspect. We still need to be able to sense that self-interference and make sure that we can still separate out the received packets from your own transmitted stream, right? So in order to do that, we essentially created an encapsulation system where we're agnostic to whatever standards you use, whether it's 802.11, whether the gr-802.11 block or 5G standards and such. We prepend to that a couple of pilot slots, 1 per dedicated device. In other words, even though your payloads are still synchronous in time, there's still a little bit of that quiet zone so that you can sense your own self-interference, and each device can do that. Well, fantastic. So we have those in place. The next question is, how do we make sure that, A, we know where our self-interference is, and B, how do we know that we can be aligned with the other node? So this is where our synchronization steps on the receive side come in. So, first of all, you need to have intranode synchronization. You need to be able to know that when your self-interference comes in, you can detect it, you can separate out your pilot slots, your payload. And if you want to have successful digital cancellation, you obviously need to know what you're transmitting. That is where all this synchronization comes in. You want to make sure that you have a good estimate of your self-interference channel. So essentially, I'm not going to go through the algorithms right now in the interest of time, but through a series of coarse and then fine-tuning, you can line up your self-interference stream with your transmitted stream and get essentially enable the next steps in the process. Bless you. Next, we add the next stage where you have two different nodes. You got to, as we said, they need to have their payloads overlap, otherwise it's not really full duplex, right? So similar idea, you have one node transmit out a initial packet, and the other node would synchronize to that. So that now you have each node knowing exactly which slot it's supposed to, which pilot slot belongs to itself, and the actual data is overlapping in time. Fantastic. We have those pilot slots. What are they actually used for? So as I said, because that is a quiet period when the node knows that the only thing transmitting during that time is itself, we can essentially recover the self-interference channel from that. And so there are different ways of going about doing this. What we ended up implementing was a simple least squares estimator. And that gives you a good idea for the, that can be used in two different ways. First of all, you can use it for your digital cancellation, which you should be. You need to know what channel you need to cancel out. But second of all, that can be used to then inform whatever configuration algorithms you need for the RFIC canceller optimization loop. Again, with digital SIC, there are many different ways in literature how to approach this. What we ended up doing was we essentially used a truncated Volterra series model to model the self-interference channel. So what that gives you is it's essentially multiple order filter that you use, you develop that filter based on your channel estimation, then you apply it to whatever signal you transmitted and can subtract that off from your received signal, and hopefully what you should end up with is just the received signal from the other guy. We found that very often using just a third order model is sufficient, and even then, the first order model as shown at the bottom is enough to get you a good chunk of the way. Now, to sort of keep track of all these different processes and everything at once, you sometimes have UHD errors, you sometimes have additional peripherals that are connected. What we ended up developing was for each generation of radio, there's one primary controller, which doesn't do any data processing of its own. It essentially just orchestrates between all those different sub-processes using GNU Radio's very handy messaging system. And what you could do then is whatever is going on in your flow graph, whatever data you're getting from your flow graph, can then be transmitted and used further down the line in those peripherals. So for example, the first and second generation radios are configured over SPI using that SPI interface over there on the left. Right? For the third generation radio, where the configuration algorithm is heavier, and that's offloaded onto an FPGA, the controller block provides the mechanism to transmit that channel estimate info to the FPGA. So that's sort of the logic and thinking that goes behind that. Is the video going to play? Yes, it will. Yes, it will. There it is. So what you're looking at here is actually what this optimization looks like, not in real time, a little bit slowed down. So at the very top is your transmitted signal power. In red is after RF cancellation. You can see that's jumping up and down, moving down as you're optimizing, then up again because we're restarting the loop each time, the optimization loop each time. And in green is just the noise floor, which is whatever is left after digital SIC is done. Again, this is looking at the channel estimates obtained from the pilot which does not contain any trace of the other signal. When this is applied to the payload, you will likewise see only the received signal coming from the other node and none of your self-interference at the end. And this is essentially a map of what, or I guess a timeline of what that cancellation looks like over time. And throughout the process, we've developed several different algorithms for controlling each of these 3 cancer types, RFIC cancer types. And whether the algorithm is run in GNU Radio itself or offloaded to external hardware, we can see that we can get cancellation down to the noise floor across all 3 generations, and that enables the actual communication step, which obviously comes next after the radio design. Now, not everybody has the hardware. We recognize that, but everyone can develop algorithms for higher layer experiments, or for example, for configuration for going from the channel estimate to the optimal configuration or digital cancellation algorithms. So what we did is we integrated these 3 generations of full duplex hardware into the Orbit testbed at Rutgers and the Cosmos testbed at Columbia. So over on the left, what you're looking at is a Gen 1 radio connected to a USRP N210. It's one of 100 nodes at Orbit, and that enables, for example, experimentation with hybrid links between full duplex and half duplex devices. On the right, you have also the Gen 1 radio, but set up in a mobile fashion, so that now you can take this outside, see, perform channel characterization measurements, see what happens when it's on the move. That's connected to a B210, and that's sufficient for a battery pack to power it. The 2nd generation radios, we have 4 of them set up in Cosmos in this grid fashion. So now we can start looking at, okay, we have links, what about actual network level communications? The 3rd generation is coming soon. As you can see, it's still in the anechoic chamber, so that should be enough of a hint that it's in the process. But the key point that we're trying to make is that this is open and available for anybody to use by just logging into the Orbit or Cosmos testbeds. It's entirely powered by GNU Radio. We have several experiments loaded already as server images. And it's open for anybody to come in and start playing with the full duplex hardware and building up those experiments and developing the standards and protocols to actually integrate full duplex further up the communication stack. And that's about that. Looks like we're at time, so I'm happy to answer any questions anyone has.
Maybe a quick question. We have one. We have one? Okay, cool.
Are there any prior works with like GNU Radio implementations and full duplex?
I'm sorry, I missed that. What was the beginning of the question?
Are there any prior implementations for full duplex and GNU Radio?
Nothing available to the public in this way. I know that LabVIEW has been used very often, but since our goal was to open this up to the public community, we went with an open source implementation instead. That said, there's also has not been, there have been some radio implementations, but nothing of this scale and nothing as IC based as this. So that's sort of, that was guiding the thought process behind the project.
Okay, thank you. One more round of applause, and our next speaker can come up on stage. Tyler will be talking about container-based development. And that's also our last talk of the day, so yeah, we'll take it away, and then that'll conclude the session.
Hello, everyone. My name is Tyler McCormick, and today I'll be presenting a container-based GNU Radio development workflow. So, quick little summary about me. So, I am a signal processing engineer at Oak Ridge National Lab, and I've been there for about 2 years now. And a few of my research areas include signal processing and software-defined radio. So, a little bit over the motivation. So, over the last few years, many of our GNU Radio-based projects have we've shifted development to use containers, and probably an obvious question might be why. Why would you ruin a perfectly good development workflow by adding, something complex like containers? So a couple main reasons why: reproducibility, consistency, easier deployment, and simplified development. And the purpose of this presentation is to kind of expound upon those and to kind of basically just show our workflow and why you might benefit from potentially adopting some parts of it for yourself. So before I dive into more of the actual workflow, I'd like to first clear up a few potential any misconceptions if you were to compare containers to virtual machines. So on the left-hand side is a very simplified view of how a container, where it sits and how it might interact with the host that it's running on. And on the right-hand side, I have a very simplified diagram of how a virtual machine might sit and how it interacts with the host it's running on. So overall, containers offer only process and resource isolation, otherwise known as OS virtualization. And because of this, when you're running a container, that container has very easy, simple access to a lot of the host hardware. Typically, containers will run a single process. And these single processes that containers usually run are also their host processes because the containers are running on the host. And because of this, these processes, there's very minimal overhead for most of these operations. So when you compare a container-based system to a virtual machine, so virtual machines have full hardware virtualization. This means that you're going to need to run a complete operating system with its own kernel inside the virtual machine. This provides very strict, very strong isolation when you compare to the kind of isolation that containers will use. And because of this, there can potentially be a significant overhead for guest processes and applications. So a quick summary, containers are not virtual machines, and containers therefore have very minimal overhead, which means you have near bare metal speeds for applications you might be running. You also have access, very clean access to the host's hardware within the container. And this container also is not required to use all of the kernel namespaces that the virtual machine might need. So virtual machines may provide a greater isolation, but this comes at the cost of increased overhead and limited hardware access. And so overall, you might say that containers provide better flexibility and easier deployment, along with better development and lower overhead. So quick little overview into a very popular container runtime, Docker. So what is Docker? So Docker consists of the daemon itself, and this daemon controls containers. It also consists of the idea of a definition file for building images. It also lastly consists of Docker Compose, which can be used for creating and managing services based on images that you've built. So Docker typically runs a single process inside of a container. It's important to note that images must have all the runtime dependencies and libraries necessary to run that process within the container itself, and that all of these runtime dependencies and libraries that you need to run that process are also independent from any of the runtime dependencies and libraries that you have installed on the host. And lastly, Docker tries to isolate the container from the host system as much as possible. Obviously not as much isolation as a VM might use, but much more isolation than other container runtimes that exist. So a quick little overview into how a container is built. So as I mentioned earlier, containers, or Docker, it relies on, it's kind of a recipe-based build system. And that recipe for Docker is called a Docker file. And a Docker file will have, it might have environment variables that you can define. It may have instructions to copy files or entire directories from the host machine to the container that you are building. It will also have to have commands that will be executed during the build process of that container. and it will also include a command to execute when that container starts if the user does not specify one when they run that container. So as a quick example, in red on the right-hand side, I have shown a very simple Docker file. And this Docker file, basically, first off, that from command, it inherits the Ubuntu 2204 base image. And then after that, we run a simple apt update. And then after that, we install the fftw3 library. And then that command that I mentioned that will execute when starting, that we are simply going to execute the bash shell when we start this Docker container. And so actually building the container, so that was the Docker file. And then so you then take your Docker file and you build a container. You start with the base image. And like I mentioned previously, the base image that we're using for this example container is Ubuntu 2204. And in your Docker file, you may want to copy files or projects into your Docker file. Here, I didn't do that, but it, of course, is an option. So something important that will come up again and again when you're working with Docker is that every single Docker file command will result in a brand new immutable layer that will be combined in your final image. And these immutable layers are basically just stacked one after another as the Docker build system just goes line by line through all the Docker file commands. And so, for example, in that previous example that I showed, so that base image that we inherited, that Ubuntu 2204 base image, that becomes a layer. After that, the apt update command also becomes a layer. Then the installing the fftw3 library also becomes a layer. And then that command that will run when the container starts also becomes the final layer to that container. So I don't know how easy it is to see that screenshot. So now that you've built your image, you can turn it into a container, and a container is nothing more than a running image. So like I mentioned, the image is immutable and cannot be changed. And so when you run your image, it becomes a container, and it basically takes that big pile of layers that we showed previously, and it adds one more writable overlay layer so you can interact with your running container. And so once you've run your container, or once you are running your container, you can interact with it, you can spin up processes or look around. So this little screenshot I've showed, so basically this is the client machine that's running that example Docker image that I showed previously. So the first thing I run is I check and see if the FFTW library is installed, and I have not installed it, and so when I grep for that library, nothing shows up. And so in that next command, I run the container that I just built previously, and then now that I'm inside the container, I then run that exact same command to check and see if the FFTW3 library is installed, and there it is, the output, so it is installed. And the purpose of this is to demonstrate specifically that like I mentioned previously, the libraries and dependencies of your container are always separate from the libraries and dependencies that are running on your host. So now to finally get into the GNU Radio use case. So when you compile GNU Radio from source, it's going to take up a few gigabytes of space. And it's going to take maybe 20 minutes to compile all the dependencies and all the and GNU Radio itself, as well as any other libraries such as UHD or anything else. And this takes a while to compile and install. And so what if we could compile everything from source, and but only do that once, and we could basically take that and put that into a base image, and then we could then take that base image, which is all made up of those immutable layers that I mentioned earlier, and then we could, if we wanted to add an out-of-tree module that we were developing, for example, we could just add that on top of the base image. Well, the resulting image would be it'd be very quick to install this this out-of-tree module we're developing, and it would be much better than having to download, install, and compile GNU Radio from source on every single development machine. And so the reason why this would be really advantageous is that any image that you make can be associated with a tag. And so when you're rebuilding or when you're building a new image that depends on that, on the previous image. So for example, if you're building a new out-of-tree module that depends on that base image that we showed earlier, that base image that we showed earlier, that's not going to change. And so we don't have to compile it again. We can just pull it straight from the registry. And so the only thing we have to compile is the out-of-tree module. And so this means that any layers that don't change, those are cached on the build process. And so when we build a new image, those are all cached, and it saves a lot of time. And this caching also exists on the client side. So when you pull an image, layers that have not changed since the last time you pulled, say, the previous version of that image, those remain on your computer, and you only pull updated images. This means that as long as your new layers that you build are not that large, then it is very quick to redeploy your images, so long as the base image doesn't change. And kind of the overall idea of this is that you can basically, compile once and then very quickly and easily deploy and run on multiple clients or endpoints. So, a quick little overview of the pros and cons of Docker. So, once you've built your image, to run it on another machine, all you have to have is Docker installed. You can install Docker, and that's a very quick, maybe 2 to 5 minute install depending on your machine speed. And then once you have that, then you just run a command, and you can pull down your image. Like I said, it's easy to deploy. I also mentioned the caching earlier. So, so long as you don't change the base image, it will be cached. And as I mentioned earlier as well, Docker also has the direct access to host hardware, which is great for USB or PCIe SDRs. And because of the recipe-based build system, it's very reproducible. The cons are that everything is isolated by default. And because of this isolation, it means that if you want to access, host folders or host files on the host system inside the container, you'll have to do volume mapping, which, while not too hard, can become tricky at times. And because of this isolation as well, it means that GUI software can be very tricky because of how the X11 server system works in Linux. And also, another unfortunate con is that images are somewhat difficult to move around if you're not utilizing a registry. And because every single immutable layer that we build up is a separate entity, it means that the images can be larger than you might be anticipating, just depending on what is inside of each layer. And also, if you're not careful, because the image is immutable, if you make some changes on a running container and then exit that container, all your changes will be lost. So that's something to keep in mind. So the next slide, I'll do a quick video demo of utilizing, basically taking a base image, and then that contains GNU Radio, UHD, as well as all the development and runtime dependencies. Basically, we'll take this base image, and we will add the gr-ADSB out-of-tree module to it. We'll push and run this new image on a client machine, and then we'll make a very small change in the gr-ADSB code on the development machine. We'll rebuild this image, and we'll push it, and then on the client machine, we'll run it. And this will demonstrate the caching and all the other benefits that I mentioned earlier. Play this. All right. So here we are on the left side. I have my development machine. On the right side, I have my client machine. On the development machine right now, I am going to build a new Docker image that is, and so this Docker image, like I mentioned, is going to inherit the GNU Radio base image, and it will copy into that base image the gr-ADSB module. It will compile it. And once it compiles, we'll have our new image. And that will not take very long at all. All right, now it's built. It's now, like I mentioned earlier, images are difficult to move around if you don't have a registry. And so we're going to push this image to the registry. And the registry is simply a server somewhere out there that its whole job is to simply just index and collect Docker images that you've made. And so now I'm pushing that image. As you can see, the vast majority of those layers already exist. And those layers that already exist, those are the GNU Radio base image layers that I made the GNU Radio base image from. And so look, it's pushed. So now on the client machine, now we're going to, so that is the command. We're going to run the, this is just running the base image. There it is. And then I'm going to just check the about, and this is GNU Radio 310 and maybe 12, I can't remember. So now we're going to close it, and then we're going to go up and we're going to change. Instead of running the base image, we're going to run that container that I just built on the left side development machine. And because that base image is cached, instead of having to pull down the base image again, which is fairly large, we're only going to pull down the deltas. As you can see, the vast majority of those layers are already cached, and there it is. There's our new base image. Not our new base image, but here's our new image that inherits the base image, and there's our gr-adsb module. There's the decoder, and that's great. So now we're going to close that, and then on the development machine, we're going to make a very small change to the gr-adsb source code, and by change, we're simply going to just make an additional import just to demonstrate how quick the rebuild process is. So here's the dmod, and all I'm going to do is just import time for some reason. And so now that we've made that change, so the Docker build system realizes, it knows that that file was changed, and so when I run this, when I build this version 0.2 of this image, it knows that the only thing that was changed were those files, and so the only thing that's going to rebuild or recompile is the part where we compile the gr-adsb module, and there it is, it's built. So now we're going to push that 0.2 version to the registry, and then once it's pushed on the client machine, we'll pull it down, and like I said before, because all that base image as well as all the original layers are cached, the only layers that are going to pull down are is that single layer that we rebuilt. There it is, it's pushed, and now on the client, we're going to instead of running 0.1, we're going to run that 0.2 image we just built. Here we go, and almost all those layers already exist, and there we go. This is that 0.2. This is our exact new version. And then we're just going to close it, and yep, that's it. So now to quickly look into another alternative container framework known as Aptainer. So Aptainer was originally developed as a high-performance computing environment tool. It basically, because of this, the purpose of Aptainer is for enhancing application portability rather than specific, process and file system isolation. And so this means that Aptainer has much less restricted access to the host system that's running on. And some additional features that Docker does not have is that instead of a big stack or collection of immutable layers, images are finalized into a single file that exists on your host's file system. Additionally, images can be encrypted, and this is really neat because Docker, you cannot encrypt your images unless you were to export them to a tar file and then maybe encrypt that later. But to run that image, you'd have to, decrypt that, untar, and then re-import it. Whereas with Aptainer, it has built-in encryption, so you can have an image that is encrypted. You can run it without having to do all those steps that I mentioned. Lastly, there's also very significant additional compression for images that Docker does not utilize. So for deployment with Aptainer, we found that deployment is much easier with Aptainer. So basically, once you've done all your development, all your pushes and pulls, your very quick turnaround cycles with Docker, deployment with Aptainer is where it really shines. So what's great about Aptainer is that you can, instead of having to reinvent the wheel, you can basically build an Aptainer image from an existing Docker image, which means that you can utilize Docker for your development. And like I said, once you have your Docker image, once you're happy with it, once you get to a stable version, then you can combine that into a working or a final stable Aptainer image. And so what's really neat is that the final Aptainer image is very small. So for the GNU Radio base image, and that includes GNU Radio built from source, all of the runtime and development dependencies, as well as UHD, that is 617 megabytes, and that's it. And that is like basically live compression. You don't have to unzip anything to run this image. All you have to have is Aptainer installed on your host machine. And so like I mentioned previously, some of the because Aptainer has less strict isolation, it's much easier to run things and access hardware and access host folders and files inside the container. You basically don't need volume mounts anymore. It just kind of has direct access to everything. And the idea is you basically can just push this image file to your host and just run it. So, few of the Aptainer pros and cons. That single file that I mentioned, it's an actual real file that lives on your hard drive versus Docker, which is this kind of esoteric collection of immutable layers. It has very minimal isolation, which means that running GUI apps is much easier than running, because with Docker, that means you have to map over all the X11 stuff, and because Aptainer has much more direct access to the file system, you don't have to do that. And all those, Aptainer essentially has all the benefits of Docker, including better compression, encryption. One big downside of Aptainer is that it does not utilize a cache build system like Docker does, which is why we found that it's much better to do your rapid development with Docker, and then once you've gotten to a stable version, and then you basically deploy with Aptainer, because if you had to rebuild your Aptainer image every time you made a simple change, you'd be there all day basically. So now doing a very simple Aptainer demo, I'm basically going to take the GNU Radio base image that I showed earlier, and we're just going to launch it and show how much easier it is to launch it compared to Docker. So here's the client machine, and so first I'm going to do an ls-lh to show, and maybe hard to see, but I promise it is only 617 megabytes. And so now, instead of that long, gross Docker command with all those volume mounts, it is simply Aptainer exec, the name of the file, and then the command you want to run. So here I'm running GNU Radio Companion, and so there it is. And like I said, this whole image is GNU Radio Companion, all the development dependencies, UHD, in 617 megabytes, and as long as you have Aptainer installed, you can run this. So, and here's a little more in-depth comparison. That's what I mentioned. There's that really long, gross Docker command, and the reason why it's so long and gross is that, like I mentioned, Docker has really strict resource and file system isolation from the host, and so anything you want to access, such as X authority files or other X11 required files, you have to specifically map over. Whereas with Aptainer, that is not the case. It already has access to that stuff. And so you can simply just run the container, and you don't have to worry about, getting your X11 volume mappings just right. So in conclusion, synchronizing GNU Radio development environments across lots of different machines, especially if they're running different operating systems or different versions of Linux, can be very tedious and is often non-trivial. And Docker can help with this by decreasing development time and simplifying distribution both during and after development. And then once you've done all your development, Aptainer further simplifies this process by applying that additional compression and decreasing image size and improving your host device access, so being able to access USB and PCIe devices much more easily than you can with Docker. Thank you, and if there are any questions, I'll take them. Yes, back there.
First off, thanks. I also maintain containerized GNU Radio for my team at work, so I'd love to compare notes. My question is, what is the process from moving from a Docker file once your image is finalized to Aptainer?
So what's really cool is that it's extraordinarily seamless. So thanks mainly to how well Aptainer was created. You basically you build your Docker file, and then it's literally a single command. You just run your Aptainer build, and then as a source, you just say, hey, instead of building a new Aptainer image from Aptainer's version of a Docker file, you just run it. You just utilize the local image you just built. But of course, you can also build it you can also build it with any image from any registry, any Docker registry. But to overall answer your question, very simple. Basically just it's basically just a one-liner, honestly.
Hi, thank you. I was curious if you considered using Docker Compose to simplify the build and run commands for Docker, and then also if you're planning on supporting VNC for our friends that don't have access to X11.
All right, so to answer the first question, the first part, we actually do use Compose on many things. The reason why I include that long command, even though it's long and gross, was just kind of to be able to compare on an apples-to-apples comparison. You know, here's a one-liner command for Docker, and here's an equivalent one-liner command for Aptainer. But yes, we do use Compose for most of our GNU Radio based containerized projects. And sorry, what was that second part of your question? Yes. Yes, we've definitely considered that, and that would be, I imagine, wouldn't be too hard to implement, because there are actually lots of existing really nice Docker images that do a very similar thing, like WebTop, or other ones that basically, you know, are for basically, you know, like you said, the VNC, the Linux version of a remote desktop. So yeah, that would be very, that'd be pretty straightforward to do. The only reason why I didn't do it on this one was because obviously, you know, installing all that stuff will kind of inflate your image size. And if you don't need it, if you know for a fact you're only ever going to run on Linux hosts, then you don't really need that. But that's a great thing to mention, because obviously, you know, sometimes people want to run Docker on Windows and Mac.
Great talk. Any experience if running GNU Radio flow graphs in Docker is compatible with real-time scheduling?
Sorry, what was that last part?
Is it compatible with using the real-time scheduling privileges, or
the real-time what?
Real-time scheduling, or in any other like insights on the potential performance impacts?
Okay, so that's a great question. So we have compared it. Now there are some. I do have some ideas for actually running some really specific tests because, you know, like I mentioned, you do get near bare metal speeds, but it's not 100%. It can't be, because there is a small bit of a hit, very small, for running your Docker container. We've not noticed any specific penalties or anything drastic. But to answer more specifically your question about real time, like you mean like real time kernel and stuff? Yeah, so we have not explored that, but I'd be very interested in the future to kind of do some, like I mentioned, some specific benchmarks to really nail down what kind of performance penalties you'll see. Because sometimes, as probably the reason for your question, sometimes those can actually matter a whole lot. All right, well, thank you everyone, and if you have any more questions, you know, please let me know. Thank you.
Thank you, everyone. I'm pretty sure that was the last presentation for today, and I can see that we now go to the Capture the Flag final. So, Clayton.
All right, Capture the Flag. First off, who had fun playing Capture the Flag? You're welcome. I'm so glad everyone had so much fun decoding so many weird and wild signals. So, first, a few statistics. We had 111 players sign up. 48 teams solved at least one challenge and got their name onto the scoreboard. We had 79 challenges in all, which is about as much as we had last year. So it was impressive people got so far, even though we were 1 day shorter this time. Total available points were 3,438. So there was plenty to do, and none of the teams really came close to finishing. They were closest were maybe about 2/3 done. We had in total 1,186 correct submissions, earning flags for those teams, and 2,691 incorrect submissions. Lots of desperate brute forcing and hoping that things would work. That always happens. And we had a really exciting and competitive event this time. It was neck and neck, one team ahead of the other right up until the very end. In fact, the last flag submission came just 1 minute and 58 seconds from the end. So without further ado, let's get to the winning teams. Drum roll, please. In third place, we have Team Radio Frikis. This is Daniel Estevez and a few helpers that he had. They earned 1,913 points. So congratulations to Daniel and team. And we'll try our best to get a prize to you. Next up, second place, drum roll please. Thunderbirds with 1,968 points. Come on up. So we do have a couple of prizes for the team. Congratulations again. And drum roll, please, for the first place team. Aerospace Team Platypus, 2,013 points. All right, anyone here from Team Aerospace? Oh, come on up. All right, Sam's got you covered. Pulled through at the last minute. Congratulations again to Team Aerospace Team Platypus. All right, so the CTF itself, competition period may be done, but tomorrow afternoon at 2 p.m. local time or 1800 UTC, we're going to have walkthrough sessions where people are going to show off all of the crazy solutions they came up with for weird and wild signals. And even if you didn't participate in the CTF, but you're curious what kinds of things were in the CTF and may be interested for next year, drop by the solution demos and have a look, and we'll show you what we got up to. And also, by the way, if you didn't join in up until now, all of the challenges are still available and still playable. You won't, so the scoreboard is frozen in time as of 4 p.m. today when the competition ended, but you can still download all of the challenges, submit flags, have your flags verified and everything. And we plan to keep the challenges online indefinitely. We have this year's and the previous 2 years all still available. So there's more CTF if you like that. There's also source code now available. So this is a repository with all of the challenges that I put together, and also some other people contributed challenges and are planning to publish their source code very soon. So I'll get the links up onto the CTF website as soon as that's possible. If you miss copying the link right now, you can just go to ctf.gnu-radio.org, and I'll have all the links to the source code and also to any challenge solutions that people publish. A lot of people like to write blog posts and things showing off how they solve things. I'd also like to thank a few people who helped out with creating the CTF this year. First of all, Daniel Estevez contributed some very cool LoRa challenges. Marc contributed a SigMF track to get people to learn how SigMF files work. Sam contributed some NFC challenges. And Aerospace Corporation contributed challenges as well. Lots of trivia and some image files for us to look at. And Oak Ridge National Labs and Seth and his team contributed some images that need to be reverse engineered. And there are plenty of other people who made all kinds of contributions. This is not an exclusive, or this is not an exhaustive list. There's lots of people who helped out in various ways. So thank you to everyone who helped make this CTF a success. And we hope you'll play online and join us in person next year. Thanks.
Right, and thank you so much, Clayton, for organizing the CTF. It really is a big part of this conference. So just a couple quick announcements. Social tonight, 6 p.m. Maple Hall. It's about a 10-minute walk towards downtown. So there will be dinner and drinks, and you don't have to bowl, but it is a bowling venue with other social space. So hope to see everybody there. The other announcement I want to make is that we still have lots of merch available, but get your t-shirts before they run out of your size. So t-shirts this year, it is a very cool design, and yeah, this is the one for this year. So it's got the logo on it, and then the GNU Radio logo on the front, and then
Also, it turns out, for those of you who are looking for the just regular GNU Radio t-shirts in a specific size, and you were told, we don't actually have any, we actually found a box that we didn't realize we had. So you may want to go and double check the shop, because there may be a shirt now in your size. And the other thing I want to say about bowling tonight is I'm planning for a tournament of sorts. Not everyone has to participate. There'll also be super chill bowling. But so I get an idea, how many people in this room would be interested in participating in the tournament? Can I see hands? All right. Good to know. Thank you.
all right, we'll see everyone over there.
6 o'clock.
6 o'clock.